Alrighty, good morning, everybody. So we're going to get started with our morning keynote for the day. Just a few announcements this afternoon. There isn't a keynote, but we have our annual closing ceremony where we'll do our community prizes, a couple other announcements, sort of thank our organizers and sponsors and volunteers and stuff like that. So be sure to attend that. I don't think there's any other immediate announcements that I have. If you're a mini organizer, be sure you're at your mini to session share. But otherwise, we can go ahead and get started. So today we have a fireside chat. Neither of our speakers really needs much introduction, but our chatter is Dr. Alan Edelman from MIT, one of the co-creators of the Julia language, and our chattee is Dr. Bob Metcalf with an E, who is the co-creator of Ethernet. So he graduated from MIT and with a PhD from Harvard, and shortly thereafter co-created one of the most important technological innovations of our time. He is also a Turing Award winner, founder of several companies, and currently is affiliated with the Julia Lab as a research affiliate. So let me introduce our speakers.
You first.
Right, there's the chatter and the chattee I just learned. So Bob, a biography is just a short description of some of the many things that you've done. Do you want to give us a bit of a longer biography?
Well, I'm pushing 80 years old, so the biography can get really long. Like you, I was born in Brooklyn, and we moved out onto Long Island, and I eventually went to MIT in 1964. I arrived. I studied architecture for a week, and I dropped it. And then physics, and I quit that because the professor was drunk. And
that could be a reason to take the physics course.
And then I switched to management and electrical engineering. And then I went to Harvard Graduate School, which was a huge mistake. And you could ask me about that if you want. And then I went to Xerox PARC, lucky me. And we all were planning to fill our building with personal computers, and they needed a networking guy to network them, and I lucked out. And so then I quickly recruited David Boggs, and he and I built the first Ethernet in 1973. And then we filled Xerox with an internet, not the internet. And then I left Xerox in 1979 to start a company called 3Com, whose mission was to build the Ethernet. And 3Com was very successful. They can't agree on how successful it was. Last night I saw market capitalization ranging from 38 to $87 billion. And I didn't even get half of it. And then I became a journalist, and for 8 years wrote a column in InfoWorld. I was publisher, CEO, and columnist in InfoWorld. And so this is before the World Wide Web. And so people would express their anger in emails to this columnist. And some mention has been made of I predicted in 1996 that the internet would collapse. Actually, I predicted it in 95, about 96, and then in 97 I had to eat my column because it didn't collapse in 1996. And then I became a venture capitalist.
He literally ate the column. You can see this on the web. He literally ate the column.
But there's a lesson in marketing there. I am more well known for having eaten my column in 1997 than inventing Ethernet. And so I'm coming into a series of careers. My modus operandi is to have a career for 10 years, and I've had 5 of them. I am now starting my 6th, which accounts for my being here. And then I was, for 10 years, a professor of innovation and entrepreneurship at the University of Texas at Austin. Y'all? There's at least one Texas hat in this room, but I can't see it at the moment. And then after that, I decided to become a computational engineer and joined CSAIL. It's funny, I joined CSAIL for the 3rd time. It used to be called Project MAC, and then it was called the Laboratory for Computer Science, and now it's called CSAIL, and I've worked in all 3 of them over a period of 50 years.
For those who don't know, CSAIL is the Computer Science and AI Lab at MIT.
Everybody knows that.
Maybe everyone knew that.
And I'm learning Julia, and it's not easy. And as a computational engineer, my first engagement is, what I'm involved in now, is modeling geothermal wells. Because I've detected that geothermal wells are going to save the world. Is that a long enough bio?
Up to you, but I think that was perfect. So in terms of format, I wanted to just invite everybody at any time to ask questions, and I think Ray and Avik will run after you with a microphone. And so Bob said that he'd like the ask me anything at any time format, not the last 5 minutes of the talk format. So
I think we have a question right there.
Oh, okay.
No, yeah, right there.
Are you pointing at Huda?
Well, she bragged that she had a bunch of questions.
I
So
think Huda's
fire
being put
away.
on the spot, whether she wants to be or not.
Maybe I'll start with a question, actually, to your introduction. So you said you went to Howard Business School and you invited questions around that. But my question was really, then you went to Xerox PARC. So from Howard Business School to Xerox PARC, why did they want to hire you and why did you want to go there?
I got my PhD from Harvard in applied mathematics, oddly. I spent a year at the Harvard Business School, but I don't have an MBA, so I'm not on the dark side.
I do have an MBA, I must say, but maybe I shouldn't say that publicly.
So I have a bachelor's degree in business, which is very unusual. And then I've recently discovered I actually spent a year at the Harvard Business School. I just didn't notice that I was at the Harvard Business School. And then I decided, I had to keep explaining to people that I was studying for a DBA, not an MBA, a DBA, Doctor of Business Administration. And after a year of answering that question, I decided to get a PhD, because no one knows what a DBA is, but everyone knows what a PhD is. And so it was statistics and stochastic systems, so to speak.
So I'd love to ask you about Ethernet. So I'm going to start with a really naive question. I'm going to ask, what is Ethernet? Is it that wire with those cute little clips at the end? Is it the whole internet? What does, maybe everybody here knows this, like everybody knows CSAIL, but what is Ethernet?
So that's a difficult question. And some people, the strict constructionists, believe that Ethernet is a CSMA-CD coaxial cable thingy, and a modern version of that is an RJ45 that plugs into a hub. But I'm on the other end, which is, I think Ethernet is a brand, and brand is a promise. And the promise is de jure standard, not de facto. Build it and they will come. Make it as fast as you can. There's no requirements document. Just go as fast as the semiconductors will enable. Be backward compatible. And enter a market of fierce competition.
If we change Ethernet to Julia, do we have the exact story here? Fast, people will come, fierce competition?
Yeah, so this meeting that I've been to before, but it wasn't a Julia meeting. It was an Ethernet meeting. It was an object orientation meeting. This is an important entity in the ecosystem for innovation. And we're in the evangelism phase here. I've never been here before, but I can see there's a lot of evangelists in this room. And that's important. It's part of and Ethernet had a lot of those meetings. Well, my favorite meeting of that type was back when object orientation was not a thing. And people were fighting over it. And I got invited to a keynote at a object-oriented conference. And for the first half of my talk, I talked about the paradigm change. And
Paradigm.
the paradigm. And of course, you can see, if you're a speaker, you can frequently see the audience, like I can see y'all. And the audience started squirming because their keynote speaker was mispronouncing one of the key words. And then halfway through my talk, I switched from paradigm to paradigm. And my message to that crowd was, do not insist on the world to make a paradigm change. Y'all need to make it paradigm change. And they did. And as you know, everything is object-oriented now, I guess. Oh, what question was I answering?
Oh, sorry, go ahead.
Did you want to ask a question, Viral? I can repeat it if you want.
No, I have a mic, yeah.
Oh, you have a mic, okay.
Well, but I didn't mean to interrupt. I thought you were done. So my question was
I was going to correct you on how to say paradigm.
My question was, you made a very interesting point about Ethernet being a brand and a promise. So I had a follow-up to that a brand promise means that, you have to meet it, like you have to back it up. And in the case of Ethernet, was it you personally? Was it the company? Was it a series of companies? And then the follow-up to that is what happens, like how do brands degrade? Is it, like you have a lot of experience with the journey of Ethernet, so I'd just love to hear your thoughts on that.
Well, Ethernet didn't begin as a standard. It was an agreement between DEC, if you remember DEC, Intel and Xerox, to build an Ethernet that they could use to connect Xerox copiers to DEC computers. But the lawyers discovered that these two companies were about to meet, and they refused to let them meet because it was a dangerous violation of antitrust law. So I called my fraternity brother, Howie, who was an expert in antitrust, and he gave me a list of 5 things, which I'm not going to give you, that you had to do to avoid antitrust. The goal had to be an open standard, like no marketing people were allowed because they might discuss pricing, like that. So I called up DEC, Intel, and Xerox, and I gave them this list of 5, and so they started meeting. Oh, you needed a government observer too, so we recruited a guy from NBS, National Bureau of Standards, to attend the meetings. But then it became a strategy for Ethernet to be an open standard. It was antitrust laws that did it. So then we created a project, IEEE 802, and began meeting at the Jacktar Hotel in February of 1980. And we published a book called the Blue Book, which was a spec for a 10 megabit per second standard Ethernet. We submitted it to the IEEE, assuming that they would stamp it with a big rubber stamp, but they didn't. No, IBM and General Motors showed up, and a bunch of others, but mostly those two. I told the guy from General Motors, why don't you build cars, and I'll build a network. And they didn't listen to me, and so they developed their own network, which failed. And then IBM showed up. IBM doesn't fail. And so they came up with an alternative technology, and for the next 20 years, oh, I forgot. So there was a 3-way war in the IEEE committee, 802, 3-way war. It was horrible. Name calling and lying and all that stuff. Not that I did any of that, but others. And the IEEE courageously standardized all 3. Ethernet, token ring, IBM token ring, and General Motors token bus were all standardized, and the IEEE said, go fight it out in the market, which we did. And so General Motors token bus almost died immediately, but IBM's token ring lasted for 20-some years. But we killed it in the end, too. So, and currently, the war is now, what's it called again? InfiniBand. Thank you. I keep forgetting it. So it's InfiniBand versus Ethernet. So I met with Jensen, and at the end of our meeting, he apologized for his company adopting InfiniBand instead of Ethernet. He didn't have to apologize, but he's a gracious guy. And I told him, we'll be back. Don't worry. A week later, NVIDIA announced their Ethernet networking package. Yeah, don't fight Ethernet. It's inevitable.
That's how we feel about Julia too.
But now Ethernet is a bunch of things, so it's being standardized at 800 gigabits per second now. And then you get into a fight as to what's Ethernet. Is Wi-Fi Ethernet? Not that it matters. But Wi-Fi's original name was wireless Ethernet. And then in 1999, they changed the name, wisely, I think, to Wi-Fi. But a lot of people say, yeah, Wi-Fi's winning and Ethernet's losing. And I can't accept that. So I say, no, there's Ethernet, and then there's wired and wireless, and you get to choose your medium. But the cool thing, on a personal level, is I walked into a Staples, and I said, I'm interested, and a young lady showed up at the front, and she and I were not members of the same fraternity, let's just put it that way. And, piercings and tattoos and everything. And I said to her, I'd like to buy an Ethernet cable. And she said, oh, yes, follow me. And I followed her to the back, and there was a whole wall of Ethernet cables, different colors, different lengths, everything. So that would be a good candidate for what is Ethernet. It's a bunch of colorful cables at the back of a Staples. Okay, I think I finished that one.
So regarding the invention of Ethernet, would you like to mention some, favorite technical stories that you might have in the?
Sure, and this is where computational engineering comes in. So David Boggs and I had to design a network that would connect a building full of personal computers, and that had never occurred in the history of Earth. Dumb terminals. Well, we were transitioning from punch cards to dumb terminals. And the Xerox CSL decided personal computers were next, and we were going to put one on every desk. And so David and I had to design this network, and at the same time, I was writing the operating system and the network protocols for a laser printer, the world's first, perhaps. Page per second, 500 dots per inch, 20 megabits per second. So RS-232 is not going to hack it. We needed a new network that was faster. So we chose 3 technologies. Gerald taps from the cable television industry allowed you to puncture a coax and grab hold of the semiconductor. And so we decided we wanted that because then you didn't have to cut the cable to install a PC. You could just puncture with it was called a vampire tap. The second protocol was Manchester encoding, which is the simplest of encodings. Every bit cell has the bit in its complement. So you would send a packet with Manchester. Only we used it in an odd way. We had on and disconnect. It wasn't on and off, it was on and disconnect. And it was during the disconnect periods that we could do collision detection. So we could detect whether there was interference by looking at the cable during the off period and see if it was on, in which case it was a collision. So that was the second protocol, the second technology. And the third one was Aloha Net. We needed a protocol for getting packets on, for the stations to take turns sending. And Professor Norm Abramson, may he rest in peace, built the Aloha network that used a method of you send the randomized retransmission. Send the packet. If it gets through, great. If it doesn't, randomize and do it again. So anyway, I found his paper, 1970, National Computer Conference. And the first thing I did was to try to recreate his model. He had a beautiful sort of Poisson-y process model. So I felt it, and it annoyed me, actually. His model was annoying because it assumed the network had 1 million users and that they would all keep typing even if there were no packets getting through. And those seemed like unrealistic assumptions. And so I decided to do another version of that model, only finite population, and you get blocked if you can't. You have to get that packet through. You can't just keep sending. So I'm writing this model. I'm simulating it. I'm using a language called BCPL, which is, I assure you, not a simulation language. But I wrote in excruciating detail how it would work because we were about to build it. And I didn't want to build something that wouldn't work. So I built a simulation of Ethernet. I didn't quite finish because we had deadlines, but I did enough that I was confident that it would work. And I discovered as I'm writing the simulation, I needed a random number, a randomized retransmission. I need a random number. And I look at Norm's model, and there's no mention of the random number. He had managed to make that moot. And so I wrote a line.
You didn't check GitHub for the code?
Did what?
You didn't check GitHub for the code?
We didn't have GitHub.
Didn't think
I think we barely had Hub, let alone GitHub. And so I'm writing the code, and there's this place where I have to do, what would you call it today? Rand, open paren, number, close paren. So I wrote, only this is in deep BCPL, I wrote the code, and I needed a random number, and this annoys, there are people who take randomness seriously. And I just grabbed the back plane of the mini computer and sucked some bits from the system clock and anded it against a mask and jammed it into a shift register, and there it was, a random number. No seed, none of that fancy stuff that you guys have. It worked, by the way, because there was a bigger randomizer. There was the randomizer in the microcode of the card that was the Ethernet. But if something bad happened, the operating system would be called, and that was random, because it had to come from a disk. And so there was a big randomization thing already there, and we just put a little one. So that was the...
I was just going to say that the youngsters in the room, I think randomized algorithms is like a new big deal. And
Oh.
there you are.
So Dave Boggs and I built this first Ethernet, and it's important, as engineers, we understand this fact. We had constraints. It had to be done in 1973 because the PC was going to be done in 1973, so we couldn't futz around. And we had a card that could hold 60 dual inline packages from the Texas Instruments. And so and then we had some microcode in the PC, and that was it. And so we had, by November of '73, we had it working, and it worked. But then the question was, how do you get adoption? Because there's a lot of competing connection methods. The first one you run into, if you're in the connection business, is SneakerNet. People will say, I'm not going to use your network. All I have to do is put my file on a diskette, put my sneakers on, walk down the hall, put it in the printer and print it. So I don't need to spend $1,000 or whatever it costs for your damn network. So SneakerNet is what undoes a lot of connectivities, but we didn't. We overpowered because I cheated. Have I mentioned that I was in charge of the operating system for the laser printer? So I set up that laser printer so that it could only print files delivered through the Ethernet. And immediately, all my colleagues had Ethernet on their desk. So the trick there, and it's a serious trick, is you need to motivate people to move on to your new platform, whatever it is. And you don't do it by wagging your finger at them. You do it by offering them a goodie. And in our case, it was a page per second. And this laser printer was really good. And in particular, it could do any font you wanted. And so for 2 years, Park was issuing memos that they were crass. They had like 11 fonts in them. And so they looked like a circus. But eventually the novelty wore off and people everyone chose Helvetica or Courier or something. How's that?
I was just wondering if Smiley Cat was, in that font.
I don't know. By the way, this relates to Steve Jobs, my good friend, who gave a famous commencement address in which he described the 3 factors in his great success. And one of them was a fib. He told the Stanford commencement, Steve, that fonts and graphics were an idea he got from his college. He dropped out of college as a freshman. But he took a calligraphy course at, was it Reed College? And he said, he told them that it was this calligraphy course that led to the Macintosh having all these fonts and stuff. No, he came to Xerox. He saw our personal computer with a bitmap display and all the fun. He saw it there. It wasn't Reed College, but we'll forgive him. And I do.
Do you want to switch now and say a few words? You see that? The word switch. Oh, okay.
Yeah, I want to ask, so like in miniature, in the open source system, ecosystem, I've made this experience that you write something, you want people to use it because you're excited about your idea and so on, but then people actually start using it, and then your mindset shifts a bit from, oh, okay, now they're actually using it, like I'm responsible now, and I at least sometimes focus more on the negatives of the design. And I wanted to ask if you ever had that moment where you were like, oh my God, everybody's adopting it. What if I designed something not as good as I could have, or something like that? If you ever had that.
So the thing we called Ethernet has been evolving for 50 years. And a lot of that evolution is based on phenomenon that is what customers do with it. For example, I had a card that would allow you to put your PC on an Ethernet. And it connected your PC to a piece of coaxial cable down the hall. Turns out our customers did not like coaxial cable. And yet it was standardized by the IEEE. It had been, there was the thick cable version and the thin cable version, and the thin cable was thin coax. So we realized, just as the IEEE is standardizing, we are discovering that we don't want it. And so we switched to twisted pair, which customers did like. And so that's the method used today. The RJ45 cable was the successor to the coax. So that was an adjustment to a customer response. Another one was we told people what Ethernet was good for, and we were completely wrong. We said, this will connect you to the internet. Now, there's no internet yet, but it's coming. And when the internet comes, it's going to be great, and you're going to connect to it through the Ethernet. And that's why you should buy Ethernet. That wasn't a compelling answer. So we made a 3-node trial network, 3 cards, strip of cable, and a diskette. We sold it for $3,000, $1,000 per PC. And if you loaded the software on, you could share a disk, which was important in those days because no one knew what to do with 10 megabytes. It was so much storage. And, or you could share a printer. The laser printer from Apple cost $7,000, so you wanted to share that baby. And so we sold these trials. People bought them. They worked. And they came back and they said, it did just what you said, except it's not useful. And I was head of sales and marketing at that time, and so it became my job to fix that problem. And do you want to know how we fixed it? I made a slide at Stanford. I went over to Stanford, and they had some of these PCs. The Alto PC is what was, and we gave some of them to Stanford. So I made a slide that said, the cost of the network goes up linearly like this, but the value of the network, which we'll say is the number of possible connections, is quadratic. It goes like this, and the quadratic eventually overtakes the linear. And you're way down here. That's what the slide said. And by the way, it was not PowerPoint. It was a 35 millimeter slide. PowerPoint was in 1987. This is 1980. So I made 6 slides. That was the size of my sales force. And they put them in their carousels. And they went and they said, the reason that your network is not useful is because it's too small. And if you want it to be valuable, you have to buy more of our products. And they did. And we went public shortly thereafter in 1984. And that, by the way, that slide is now called Metcalfe's Law. 1995, I didn't call it that. You're not allowed to name a law after yourself. George Gilder called it Metcalfe's Law. And so among all the other things I have to do, I have to fight to defend Metcalfe's Law. There's all these professors and grad students out there who say, quadratic isn't quite right. It's log n log n is the favorite. And see, the trouble with quadratic is it goes to infinite, and we all know that networks don't go to infinite values, so it can't be quadratic. So let's switch to n log n. Wait a minute, n log n goes to infinity too. So that didn't solve the problem. Anyway, so among my various hobbies is defending Metcalfe's law.
So if I can ask you to fill in the blank, let's see. So you talked about the invention of the Ethernet and how you sold your network cards. What made you start up 3Com and go, from Park to this thing that didn't exist, 3Com?
So that story could go way back, but I was working at Xerox in Palo Alto, and I'd been there 8 years, so I left. And the memo, I gave Xerox 7 months notice, never slam the door behind you, and decided to start 3Com Corporation because I was in Silicon Valley. And when you're in Silicon Valley and you're 20-something years old and you've been at Xerox for 8 years, what do? You start a company. And I did. The company didn't know what it was going to do for a while. See, it was founded on June 4th, 1979. But we knew what we were going to do by the end of the year, which was I convinced DEC, Intel, and Xerox to get together to make a standard. And as soon as I saw them moving toward the IEEE and all that, I said, there's got to be a bunch of need here. But it was an open standard, so my little company started with 100 competitors. And so that was difficult. So that's how it happened, sort of step by step.
Cool. So maybe I can fast. Oh, a question. Sorry.
I actually have two. One goes way back into things you said earlier. Why on earth was somebody proving theorems about networks with 1 million years or 1 million users typing all the time when there were no networks yet? So basically a question of like, what were the intellectual foundations that led people to even conceive of these as problems? And then the second one, fast forward sort of to the period where you're talking about right now, which is, you must have had at least one moment where there was going to need to be a pretty big investment in producing sort of next-gen hardware or something like that. And that must, what sorts of, let's say, decision-making did you have to apply about when to pull the trigger on, a big investment in something like that?
Well, it turned out whatever process I used, I was wrong.
That works for me too, actually.
But I was in Silicon Valley, and in Silicon Valley there's a machine. And you make a deck, and you go to the VCs and you show them the deck, and if they like it, they give you money, and then you recruit people, and then you sell your products. Have I oversimplified? Mm-hmm. And that's exactly what I did. A VC showed up at a seminar I was giving at Stanford. I was a Stanford professor in those days, and I gave seminars, and he was sitting in the back. It was a guy with a suit. By the way, this is a suit. And you call it a suit when the pants match the jacket. Okay, so he was wearing one of those, and pretty soon that became I sold a third of 3Com Corporation, which would later be worth $50 billion. I sold it for $1.1 million, a third of the company.
I thought you were going to bring from the past one of the 3Com cards. I didn't realize you were going to bring a suit from the past.
Well, I had to shave my beard, and I had to learn how to wear a tie and stuff. But it worked out. You had to impedance match with your customers. And so if you wanted to sell an Ethernet card to a Fortune 500 CTO, you can't be a hippie. You got to be all dressed up. And I could do that. It's easy. The hard part was your first question. And ask it again.
So, I mean, it sounds like one of the very early sort of seminal ideas you took from essentially a mathematics paper on the design of large-scale networks in an era where there were no such things, as far as I understand. So what was the intellectual foundation that led this to already have been a mathematically investigated research topic at some level?
That's a very complicated question. Norm Abramson's Aloha network had 3 or 4 users, which is a small value of infinity. But a key factor of this is that I had just finished graduating from MIT, and I took all the courses in probability and statistics, and I wrote simulators, and I was itching to build something. And the world was full of punch cards and dumb terminals, but PCs were coming. And that was my time machine. Oh, it's my answer, a real answer to my question, your question is, I had a time machine. And the time machine was Xerox PARC. So we filled the building with PCs, and we did what you do with PCs, and we went, this is good. Everyone who saw it said, this is good. So we, like others at the time, resolved to fill the world with PCs. Gates and Jobs, for example, debuted in the early 80s.
So speaking of time machines, if I can fast forward to the present, so now, what everybody's talking about. I mean, you go to restaurants. In the old days, you hear people on the other table, they would talk about their boyfriends and girlfriends and things. Now everybody's talking about AI, no matter where you go. And I'm not sure whether people are saying this is good anymore. That there's a lot of opinions out there. What does your time machine say about what everybody else is talking about these days? The AI that's here and coming.
Let me begin with an amazing fact. In 1968, it was time for me to graduate from MIT. And to get a bachelor's degree in electrical engineering, at that time you had to write a thesis. And I had taken all the AI courses that MIT had, that many, and
I bet they didn't have the 1,000 students that one finds today in these courses.
No, but I took the courses. And one of the people who stood out was Marvin Minsky. So it came time for me to do my thesis, so I signed up Marvin to be my thesis advisor. And then I wrote the thesis. Now, I should tell you, I wrote the thesis on a yellow school bus returning from a varsity tennis match. And the thesis was due the next morning. So I finished it and submitted it, and Marvin accepted it. But I could tell, because I'm a sensitive person, that Marvin did not like my paper, whose title was A Neuron Model and Some of Its Information Processing Capabilities. So Marvin made it clear that he was not going to hire me into the AI lab, which would be the natural step. So he sent me down the 9th floor of Tech Square, where he introduced me to JCR Licklider, who was the visionary behind the internet, and I got to work in his lab. So I switched from AI, in 1968, switched from AI to networking, and networking worked out for me. This is 68, so I've watched AI go like this since 1968. It's been going up and down, so it's going up now, I think.
So I hear.
And it's going to go down. Now it's a positive event. When it goes down, you stop calling it AI, and there's other synonyms. Like, people talk about the Internet of Things. They use the word thing. They use the word things because they don't know what it is that they're going to network. And you all call it AI because you don't really know what it is. So it's going to go like this. But AI is connectivity. I'm a connectivity person, so I'm claiming AI now. Because when you describe a neural network, what's the second word? Network. Okay, now here's a short calculation. The LLMs, is that what they're called, LLMs?
That's what they're called.
Have it on the order of 1 trillion parameters. Parameter being roughly analogous to a synapse in the brain. And we have 10 to the 11th synapses, each of which, well, 10 to the 11th, which is smaller than 10 to the 12th. So you might foolishly conclude that we should be at AGI already, but no. So there's a paradox. Transistors are 1 million times smaller and 1 billion times faster than neurons. And yet, neurons produce this brain thing. What accounts for that? The answer is connectivity. Transistors have on the order of 1 or 2 or 3 connections. Neurons have on order of 10 to the 4th. So 10 to the 12 times 10 to the, I'm sorry. So the 10 to the 12th is in the LLMs. We're going to need another factor of 1,000 parameters to get to AGI if you accept this connectivity model of intelligence. I think I have just emptied my AI folder. I don't know.
So there's one last topic I really want to get to, as we're about to run out of time.
2 more minutes.
Yep, that's what my clock says. And one of the greatest honors of my life is that you're in the Julia Lab at MIT. And I was hoping you would tell the audience what it is that you're trying to achieve. And what I'm secretly hoping is that some of the folks here might even help you achieve your goal. So please go ahead and tell everybody.
Okay, so I've chosen as a brand new computational engineer, this is my 6th career. These are 10-year careers. And I've chosen to look at geothermal energy because when I saw it, I could see the internet in 1980. The technology is underappreciated, it's going to change the world, so I'm going to do that, and that's how I became a computational engineer. And a template for successful innovation involves a platform typically. In my case, it was the Texas Instruments 7400 dual inline package, and you could assemble those into an Ethernet. I'm choosing Julia as my new platform, and so I'm going to do I am doing simulations of geothermal wells, and I'm doing it without much knowledge of Julia, and in particular, no knowledge of thermodynamics, which is a really serious problem.
It doesn't sound like you believe that needs to stop you.
No, it's hard, by the way. Julia is hard for me, but I will overcome.
And there are a few people here who might know a thing or two to help you.
Yeah. Scoping, I mean, global, local, And then I understand there's a community. You all have a community called sparse arrays. Wow, that's a whole community. Can you imagine how hard it is to learn the rest of Julia? My daughter's name is Julia, by the way, so I took 2 extra T-shirts for her.
So on that note, I think we can all thank you.
All that was written down here.
Good to go.
Thanks everybody for your patience. We shall now move on to our sponsor talk for the day, given by Temple Capital. Temple Capital is a diamond sponsor at JuliaCon 2025, and we're deeply grateful for their support. So I invite Dr. Austin Hansen to deliver the sponsor talk. Thank you.
Thank you. Yeah, so my name is Austin Hansen. As mentioned, I am a quantitative researcher at Temple Capital. Admittedly, I've only been at the company for a few months now. One of our co-founders, Safik Berry, he's I think attended some JuliaCons in the past. I think even gave a talk a couple years ago. Unfortunately, he had some hopes to, or he did have hopes to make this conference, but unfortunately he couldn't make it just due to some timing issues and things going on in his life. So you all are stuck with the new guy giving this talk. I'll definitely say I'm no replacement for Safik. So my talk will be very untechnical, just kind of an overview of what we do as Temple and my kind of transition from academia into finance and some of the reasons why we like coding in Julia. And I'll give some kind of personal, like what I've found really nice about working in Julia. So with that, just a little overview of my background. So I've kind of had a winding path before ending up at Temple. So I actually started my undergraduate degree as a classical guitar major. And I did that for around 2 years until having my first of many existential crises, which as every person naturally does, they then transition into mathematics. So I then finished out my degree in mathematics. I graduated, went on to work for a few years for an insurance company doing data analytics, got really bored out of my mind with that and said, let's do something a little more challenging. Went back, got my PhD at the University of California in Riverside, studying mathematical biology, and I just graduated around 6 months ago, and then started talking to the CEO of Temple, Vasily Andreev, and decided to make the transition into finance. And so far, I've been really happy with my choice there. As you can see from this graphic, I didn't actually start coding in Julia until working for Temple, so it's only been a few months now. In my PhD, I did computational modeling, and I was mainly using MATLAB and C++. However, I did hear about Julia in academia. So just a quick anecdote. My first encounter with Julia, I had this agent-based model of neurostem cell migration. It was coded in MATLAB. And you can kind of see in this graphic here, it was looking at the migration of neurostem cells in kind of rodent brains. So the green are the neurostem cells, and the blue-red scale in the background is chemical signals for chemotaxis. And we were kind of wanting to scale up the number of cells we were modeling, and we're running into some performance issues there. And so me and my advisor kind of discussed a bunch of different ideas. One of them was maybe we should just actually change coding languages to C++. So there's this thing in MATLAB, like an app or MATLAB coder that kind of helps with that kind of change. I had never used it, and my advisor had never used it. So she reached out to a previous collaborator and asked if he had any experience. And he unfortunately didn't have any experience with it, but what he did say to us was, hey, my go-to coding language these days is actually Julia, primarily because it has the writability of MATLAB and the similar speeds of C++. And I think this is a very common sentiment I've heard echoed a lot through here, but in my personal experience, and I think as Temple's experience, we found that to actually be true, which is a pretty rare thing. It really is delivering on that front. So with that, just a little bit about who Temple Capital is. Temple was founded in 2018. It's a hedge fund that primarily trades Bitcoin and Ethereum futures. However, we do have some commodities strategies in the works, so looking to kind of expand to commodities. Just some other key facts, there's around 17 people on the team. We have some long-term general partners at Bain Capital, Pantera Ventures, and Belvedere Trading. We have around 125 million in assets under management, and we run a fully systematic kind of pipeline for generating and trading strategies that are focused on like beta neutral strategies, which mean just the volatility of our strategies in comparison to some market standard is relatively low. So how does Temple Capital differ from other hedge funds? Well, in other hedge funds, there's oftentimes a lot of very discretionary components to it, and in that, some non-back-testable components as well. So a lot of hedge funds take a more individualistic approach, where each individual quantitative trader will come up with their own ideas. They'll research these, trying out different versions. They'll show these results to some portfolio manager who will then look at those kind of summary statistics, decide whether or not they want to approve or disapprove of that strategy and allocate money to it. If it's approved, the money will be allocated and that strategy will be deployed, and then maybe sometime later you'll reevaluate. Temple, on the other hand, really takes an automated approach to this whole process. So it's really a systems level viewpoint of this whole process, trying to make otherwise manual research more testable and scientific. So with this, we really try to value creating pipelines that are inherently adaptable and can adjust over time, that are not reliant on continuous research or continuous manual research or updating, and which are back testable from start to finish. So because of that, because of this systems level viewpoint, we really need an infrastructure that has a couple of key elements. Namely, we need an infrastructure that allows for researchers to make coding changes quickly and easily. We need pipelines for these routine backtest and walk-forward analyses. And we need this pipeline in general to be very computationally efficient so as to produce, to be able to test lots of ideas quickly for very little cost. So this is kind of before my time working there, but historically, a lot of Temple's infrastructure was built in Python. And as this kind of philosophy started to develop at Temple, we started wanting more control over numeric computations. And in particular, there was one pipeline that was coded in Python that had around like 200 hours of expert level work to really optimize and get every performance out of that pipeline. Still wanting more, we tested a number of other tools, some different compilers, and among that we tested Julia. So we took that pipeline, coded it in Julia, and in just a few weeks, with basically very little Julia background, they were able to take this pipeline, code it in Julia, and see a 14x increase in speed over the highly optimized Python version of this. So this really became a really motivating force for us to kind of start transitioning a lot of our processes to Julia. So Julia has kind of become this center glue that kind of keeps our processes rolling. So we can use macros to build graphs for efficient computation of time series, then take these time series, train a large number of models, walk them forward, decide which strategies to deploy, and doing this all faster and more easily means greater profit for us as a company. On the personal side, I've really enjoyed the easy syntax. So like I said, coming from MATLAB, it's been a relatively low or easy learning experience for me. And so basically with zero Julia experience and with zero finance experience, I'm able to like jump in and within just a few weeks of learning start testing my own strategies. So in general, I won't kind of give specific research projects, but in general, we can kind of think of this whole development of strategies as looking through a very high-dimensional space and trying to find certain strategies in that high-dimensional space that are both predictive and uncorrelated. And you can come up with many different algorithms for doing that. And so just like I mentioned, in a few weeks, I've been able to kind of jump in and start testing my own ideas. So again, like I said at the beginning of the talk, this kind of sentiment that the writability of MATLAB, but the speed of C++, we've really found that to prove out. So with that, I just want to say thanks to this community. It's been a real pleasure being here, getting to talk to a lot of you. And everyone's, yeah, just very collaborative and nice. Thank the organizers, thanks the developers and all the work that's gone into Julia. And yeah, for letting us speak. And lastly, we just want to say that we are hiring. So like I mentioned, we have a team of 17 people. And we are looking for Julia experts. We recently hired Jishnu, who's been kind of a major contributor to some core numeric libraries. So if you're a Julia fan and you are interested at all, please don't hesitate to reach out. You can talk to me afterwards, send an email here. We'd love to hear from you. So thank you all.
Thank you. Thank you, Austin, and thanks to Temple Capital for sponsoring. I think Austin is around for the rest of the day.
Yeah.
So please talk to him if you're interested. Thank you.
Thank you.
We will now move on to our next talk, so give us a minute to set up. Are you?
It was yesterday.
Yes. Do you have a USB-C thing? Yes.
Okay. That would have been a bummer.
He's just doing questions.
Mainly for question. Okay, for running around. Okay.
As the name suggests.
And are you going to be doing the time cards and that?
Yes,
or?
I'll do.
Is this the wrong connector?
No, it should be. Yeah. Yeah, that's the one. That's the only one.
Huh.
Yeah, there it is.
Oh, there we go. Great. Okay. Thank you.
Okay, we should get started with our next talk, which is Cody Tapscott, who's a compiler engineer at Julia Hub, and he's been, one of the core developers for the last couple of years, and he will talk about types. Up to you, Cody. Thanks.
Thank you very much. All right. So we'll be picking up off today a little bit near where I left off on Wednesday. For those of you who didn't see my talk, we were talking about type unstable code and how to solve invalidations. And I left that talk with a little bit of a cliffhanger, talking about, okay, well, to solve invalidations, we really want a little bit of hint from the user just about whether or not they're going to extend certain methods later or not. And that's really was like the important key detail to help improve our compiler's decision-making around avoiding invalidations for users. Today, I want to take that a lot further and say, okay, well, if we're already adding a little bit of information from the user, what would we do if we potentially added a lot more, and what would be what kind of user experience would we potentially be able to get out of that? So we'll be looking at types on the other extreme of the spectrum here, and I'll kind of show you what I mean by that in a second. So first of all, I just want to start with a really basic example here. We have a pretty straightforward function that's just doing some accumulation through some kind of abstract array. And the question here is what do we know about this function? And one of the basic questions here that the comment's kind of hinting at is, do we know, for example, its return type? And I think already a lot of Julia developers might feel a little bit torn by this question. It's going to depend on who you ask. I think someone new to Julia, who's a human, would look at this and say, oh, well, if they understand at least the types and the syntax here, they're going to say, it returns float 64. Maybe if they're a little bit more veteran, they might qualify that a little bit, and they'll say, well, it returns float 64 unless someone in the ecosystem made a mistake, and it doesn't actually return the L type of the abstract array. That could be a problem. Unfortunately, if we ask the compiler what's going on here, it knows even less. It just says, I don't even know where to begin with this code. What's each index? Where does iterate go? Everything's any. And you'll see on the next slide here, literally everything is any. The only 2 bits of information that the compiler actually managed to figure out about this function is that triple equals is an intrinsic that returns bool, And then if we negate a Boolean, it gives us a Boolean. Everything else about this function, its effects, its return type, where any of the calls go, any of the types, we were not able to resolve at all. We know basically nothing about this code. Of course, I think those who are veteran in Julia know that this isn't a very fair example, because Julia never looks at the function this way. Julia is always going to look at this function with concrete arguments. It's going to look at it for vector int, it's going to look at it for offset arrays, for a reinterpreted array, whatever you happen to throw this thing, code gen and inference are going to be done on a concrete type. And that's really essential for the way that we get our performance today. This talk, when I talk about being on the other side of the extreme, is asking the question, could inference still be useful somehow, even when we stop looking at just concrete types? And the reason that this is very interesting is partly to bridge that gap between the human and the machine on that last slide. And especially as we start to get technologies like JetLS, where we had a question at the end of that session on Wednesday, I think it was, where someone asked, if I have a method that's similar to this method, where it's just got an abstract type as its parameter, what can JetLS tell me about whether I wrote that method correctly? And the answer was not very much unless you provide test vectors. And even then, the test vectors will only tell you what went wrong from the specific concrete types that you saw. And so the reason we're trying to, that I'm trying to start asking questions in this direction is that it would be great if JetLS could look at this signature and give you general answers about whether or not you made mistakes for this function in general, without having to provide your own test inputs and finding out that mistake later when you get to the testing phase rather than the initial editing phase. Or to have that assurance before you have your users find it for the downstream library. You can find it earlier when you're actually writing the thing. Anyway, so that's the motivation here. And then the spectrum I want to set up here that we're kind of thinking about, the reason that this is so dramatically different than the way inference normally works is that Julia tries really, really hard to be monomorphic. And the really interesting thing about Julia is that you write it polymorphically, which is why the human was able to give us that reasoning, which was like, this function should return float 64, that's what I intended it to do, that's what I was thinking it was going to do when I wrote it as a human. But the way that Julia ends up compiling and inspecting that is always fully monomorphically, which means that it's always considering specific types. And the idea here that we want to explore is kind of that these are just two very fundamentally different perspectives on code. And they require different techniques if we're going to make progress, having inference know things about polymorphic code. Because in reality, like the design of Julia is that it shouldn't have to know things about polymorphic code, and we only ever let it see monomorphic stuff. But then the user wants to ask questions about polymorphic code and doesn't get anything back from the system. So as an example of monomorphic stuff and monomorphic statements, we have the types that you guys are used to in Julia. We have int, we have union, int, string, or we have parameterized types like vector, float 64, or, I mean, this is just a really small abbreviation of the kind of stuff you can get from SciML and MTK, but they double and triple down on this compilation mechanism that everything should be fully monomorphized, so we end up with huge types that are very, very specific about the full type and identity of everything in the system. Now, if we want to be able to conclude things like what the human concluded on the last slide, then we have to make very different statements. We have to start just talking about properties instead of this thing has a specific type, because we're talking about really, really large sets of types now. So this might be things like, oh, vector number, that's an easy one. Vector of anything that has a subtype of number, but still unbounded in size. There's no way we can enumerate that set. There's really nothing we know about it either. I'll talk a little bit in the future about a couple of the things we do know. But I mean, I think it's a common question for a human Julia user to say, what does abstract array mean? What's the interface? And we have a little bit of an implicit contract between users, but it is, the reality is that the compiler also suffers in performance if we allow it to dare to be a little bit polymorphic in how it analyzes things. The compiler suffers too for not knowing what an abstract array means. And so that's what we see here. And then any here is in gray because any is kind of the equivalent of bottom on this side of the spectrum. Like we don't know anything about the type at all. We have 0 facts in our database. We've managed to lose all of our information, which happens, and we still compile and execute successfully at that time. But at that point, we're not even polymorphically reasoning. We've just given up on reasoning, which is fine. You know, we just try to handle that as well as we can. So then we kind of get to the spectrum of the different consumers. Like we've already talked about the human side consumer of some of this information and the uses in the compiler. And one of the ideas that I want to set up here is that like we're heavily biased towards the monomorphic side of this equation for the benefit of code gen, for example. Inference is also really dependent on monomorphization, like we just talked about. Inference was the thing that really fell on its face on that first slide. But inference can do a little bit better. Inference can look at a function call, take the abstract version of it, dive in, and maybe recover a little bit of information. It just tends to fail. It's got a pretty low success rate at doing that. Whereas code gen, realistically, once you get to an abstract type, code gen can't give you many performance benefits at all anymore. If it's not a small set of types that it knows about, or if it at least knows where your functions are going to, that's kind of the bare minimum for us to get meaningful optimizations of the current system we have. Otherwise, you jump all the way over here to the right side of the diagram, and we're just in fully dynamic, boxed any land where we're operating basically like an interpreted language, so to speak. I mean, maybe you're lucky and different pieces of your function got optimized, but there's big chunks of it that are operating in that regime at that point. So that's basically the situation we're in here with these, and then we can't forget about the human either in this equation. And the human, I kind of see him as tasked with, oh, actually, sorry, I forgot. We also need to mention dispatch. Dispatch, of course, is the one thing that really does span the whole spectrum here. And I think Julia users are also familiar with needing to reason about dispatch both concretely and abstractly. And I think it's worth mentioning that that system never runs out of fuel. It kind of operates at all levels really successfully here. And then in theory, the human needs to do the same thing. They want correct code. They need to be reading documentation to make sure that they're doing the right thing with their abstract arguments, or writing down documentation to make sure that someone who uses their generic functions is able to use them successfully. Otherwise, it's just a matter of, someone comes by and tries something, you didn't think about what they might try, and it's a debate every time that you find a new user with an interesting generic use case. And I do think that happens a little bit here. So the human's going to be trying to reason about all this, but unfortunately it's going to be a little bit tough for them. I think the way that, at least if you have the experience I do, sometimes you end up feeling a little bit in the middle here. You have on the concrete side these nice test cases and internal types that you've just got like a finite list of internal types, and you're like, oh, well, I can just if else 4 times, and I know that I've covered all my cases because I'm not getting them from some user, I'm just the one listing them out and providing them. And then on the other side, I've got the stuff that really is generic and exposed to users downstream. It could be anything they throw at me. And that stuff, I'm just writing on documentation and a prayer to kind of hope that I stitch everything correctly together and got the assumptions straight. And I don't think there's a lot of machinery in the middle that helps you stitch those two things together, which is why we've got this poor guy down here, and every once in a while when he's trying to decode abstract array and understand what he can safely assume about it, he's, on the left-hand side we have a great time, on the right-hand side it's not too bad either, but the guy in the middle here, he's sometimes having a bad time trying to connect them two together. So then how do we fill that gap? Can we do anything to try to assist the user in bridging the high-level reasoning from the human and the low-level reasoning that the compiler is really good at? Can we give the compiler a little bit of high-level reasoning capabilities? We touched on this a little bit before in terms of the types of objects, but I think it's worth revisiting that idea of what kind of information can the compiler summarize about your code and the objects inside of it. So in monomorphic, this is stuff like, it really is the type of an object. So stuff like, is it a float 64? Is it bool? Is it maybe a union of bool or vector int? So it's either one or the other one. We even do fancy stuff in the compiler that's still very monomorphic in spirit, but quite powerful because it can depend on other statements, for example. So we know that you created some Boolean variable that depends on the type of another value. Maybe you checked whether or not x is or y is a string, and then we can correlate that, so if you ever branch on that in an if statement, we now know that the concrete type of that thing inside that if statement. So we're really, really good at this type of monomorphic reasoning, and we have a lot of fancy functionality to do it. The other kind of statements we don't really have in any native form in the compiler typically. Stuff like just saying that I don't know the type of x, but I do know that it has a field with a specific type. I don't think we have any real mechanic to do that in the compiler right now. Stuff like saying that base.hash, whatever implementation it's going to have, will return a uint. I mean, that's the way the documentation is written. That's the way all the functions should be written. But the compiler has to be weirdly pessimistic and plan for the case that that's going to return any, even though it does sound kind of like a better universe where the compiler reinforces the documentation, checking that your return type's correct, and gives you better performance because of it. Anyway, so that's some of the direction we could go in. I'm not taking a specific stance on how we make that change, but I just want to reintroduce these ideas to say there's another side of the spectrum that's maybe worth looking at. because it does tie together with a lot of the user experience side of the question. And then things like, yeah, does resize on an array actually return the same array or not? That is also something inference doesn't know, which it doesn't usually care about because usually it's so wide and knows so little that it doesn't mind anymore. But if you're writing generic functions, knowing that you gave some object into a function and got the same type back out is one of these really nice properties that's good for you to have, and that you use all the time when you're writing highly polymorphic code in other languages. But Julia can't do that kind of thing. And I think I even remember that Tim Holy at one JuliaCon brought up the idea of like, we have so many specializations for basic things that are really polymorphic functions that could be analyzed once, but we don't have this machinery and inference to be able to reuse that work. So for example, something pulling out of something out of a vector, in theory we could analyze that once because it's really just doing gets and stores. It's not really doing a lot of type-specific logic. You could just pipe the element type straight through, but right now we don't get to save that kind of effort because we don't do any of that polymorphic reasoning. And then there are two kinds of specific facts or kind of like actual statements that I want to hone in on today that I think would be very useful that the compiler can't really do right now, which is to be able to talk about the fields and contents of types like you have here, which it really just looks like a struct definition. And this is essentially just a partial definition of a struct that says you're guaranteed to have certain fields, or you can even have, I don't have an example up here, but you could label these, for example, optional, in which case you don't know that the field exists, but you know that if it does, it has a specific type, which is still very, very useful information for the compiler. So then that doesn't really tell you a lot about the data layout. You can kind of see here where some of this Julian tension comes in. Like, we're not really helping CodeGen anymore very much. But we are helping the user quite a bit if they're trying to look at JetLS and make sure that they didn't access a field that doesn't exist. Or that they want to be able to declare a simple interface up front to say, hey, I'm really expecting your type to have this field inside of it because that's the way I've written this generic algorithm. And so you should be giving me a type that looks like buffer. Otherwise, I didn't write my code for you correctly. And then TypeScript, for example, is an example of a language that uses these kinds of abstract prototypes of types everywhere. And they do it for exactly this kind of problem where they have a very dynamic language and yet they're able to reason very concretely and very intelligently over a language where you almost never know exactly what the set of fields and object that you're going to get in a function is. But the type system that they provide does allow you to explicitly lay out these concerns. And it's also probably worth mentioning, I know there are a lot of folks who are serious compiler engineers here in the room, TypeScript does cheat a lot, but I don't think, in the sense that they will allow their type inference to be unsound when they don't feel like it's likely to be a problem for the user. But I think that this basic mechanism here is not a case of them cheating. It's just a case of them designing to the type of information they care about tracking in their dynamic language, which is really quite similar to the kind of thing that we have to worry about. So then we've got, on the other side of the equation, we also want to worry about interfaces of functions. I think this has been probably brought up many times in 100 different variations. But the main thing I want to bring up here is just the fact that this is really essential to be able to reason without a concrete type on hand. And without this, we can't really put something into a function and get it back out and know anything about it. So we're kind of forced to monomorphize, which may be fine, but I think we're starting to feel that tension in the tooling. So in this case, what this interface does is it provides either constraint, or we could also talk about cases where it just provides a hint. Like the compiler can still do a lot of meaningful optimization with a hint that this return type really, really ought to be a uint, for example, on the hash function. But right now, we don't really have a way to tell it that. Like, I can only give the compiler a concrete implementation of a function. I can never tell it anything about implementations that might come into the future. And that's really what this type of statement is about. It's about saying, like, we know the code's not there yet, but I wrote this intending for it to come later, and here's what you can expect it to look like. And this is very useful to inference if it is enforced, but even if not, it's still very useful to users because something like Jet or JetLS, for example, might choose to say, okay, sure, it's an optional interface. It's not guaranteed to return uint, but I can reasonably expect that it ought to. The documentation says it should, and there's a hint in the source code that says it really should. So maybe JetLS's custom analysis wants to go ahead and operate on that assumption, and now you get to intelligently analyze your code polymorphically in JetLS and get better diagnostics. And then Rust traits are a great example of this, where they do all their reasoning polymorphically over their traits, even though they end up at the CodeGen level they end up fully monomorphizing, like a lot of languages do that are performance oriented. Great, okay. So and then the only other comment here is that these both kind of get, I'm being very hand-wavy here about the details here because I mostly just want to give a perspective. But in theory, the idea here is that somehow we attach this information to these abstract types so that later all you need to do is kind of refer to this, like we give meaning to the fact that it is an abstract type of some kind. And that specific meaning is that it has fields with types and it has functions that return specific types in return to them, in response to that. And so then you don't need to think about like, we don't need big unwieldy declarations, we don't need necessarily vtable declarations and things like that. I mean, we can consider those kinds of hints for more performance-oriented cases, but the idea here is that the most Spartan approach is just anything that would be able to describe to the compiler fields of multiple types at once and functions operating on multiple types at once before we actually get their implementations. Like that's the key piece of information. We can't have the compiler think about it, and we can't communicate it to the compiler either right now. So the two things that we can do polymorphically, and the reasons that inference sometimes succeeds, is that we can use the abstract type lattice to exclude certain methods, the implementations that are already loaded up in the method table, but which don't overlap with our abstract type. And so we know, like, it doesn't, like, what would be an example of this? An IO doesn't overlap with an abstract array, so I don't have to worry about IO methods being something that I might dispatch to here. And maybe I end up in a very generic implementation, so it's not an ad hoc polymorphic interface. And in that case, I can potentially get lucky, go into a very generic implementation of the function, and come back with some type information. So that's great. That's the part where inference does potentially succeed reasoning polymorphically. But the things it can't do is know about field accesses. And there's really, like, you just can't get started in terms of giving the user diagnostics about whether they wrote their function correctly if as soon as they type foo.x, you don't know anything. And that's where we're at right now with polymorphic reasoning about your functions, which is why we've accepted that premise, and we're like, you need concrete method signatures before we get started. Great. So yeah, so this is really about being able to reason about, your interaction with objects, and then be able to support ad hoc polymorphism and describe what those things are going to do when those implementations are provided later. So then if we go back to our diagram of specificity here, we can see how this might fill this in a little bit. And the main advantage is that it really gives type inference a big leg up. Like we talked about, code gen may not have the biggest advantage with this kind of thing, but type inference at least can potentially reason a lot more on this upper side of the spectrum, or at least that's some of the pitch, is that if we give it tools that can make highly polymorphic statements of this kind, we can start to do better reasoning up here. And then on the other side, our user's a little bit happier now because he can write things down in the documentation and have that correspond to something that means something in the compiler, and it means something to the language server when it talks back to him and says, hey, you wrote down this interface here, but then you violated it when you actually wrote your implementation. Like, what's going on? And it also really helps with downstream users where they say, you didn't document what the return type is supposed to be, and so I think I should be able to return anything. It's nice to be able to have a place to write down and already provide some consensus. Since you laid out the function that they're extending, it makes sense that you ought to be the one to lay out a bit of a standard about whether or not there's really any bounds on that type that you should return. And then there are some opportunities, I think, for CodeGen to optimize here. The vtable proposals that we've seen from a couple core team members in the past, I think, would fall under this bucket. There's probably other fancy stuff that we can do too, in the vein of different heuristics or different hints to the compiler. But I think that the reason I kept this so small is that we expect that the impact to CodeGen is going to be a lot smaller compared to the impact to type inference and the impact to the human user, for example. So there are some CodeGen benefits, but unlike most of the features that we put into Julia, this thing does not get booked in based on the benefit to code generation. It gets booked in based on all the other things. Anyway, so we can see that these facts actually aren't that hard to write down. Like, yes, there are extremely fancy like batteries included type systems out there that do really complex reasoning, but the kind of reasoning we were talking about, the kind of thing we couldn't do at all, was just being able to talk about fields and return types of functions before their implementations show up. And I don't mean to hand away a lot of the design details and technical details that need to be worked out there, but my main point is that with just a little bit of that machinery, we could potentially start to be able to successfully reason through some of these functions. And so that can be a boon to type inference when type inference hits these highly widened cases and hits this polymorphic fallback. Right now, it's not very likely to be successful, but this could potentially give it a much better chance of picking itself back up and recovering from those kind of scenarios. And then even if, and then also where, as I mentioned a few times, like I'm very excited for the potential that this would improve some of the user tooling experience, even if we're not exactly sure whether this would reap big benefits for CodeGen. The last bit I wanted to mention here, and this is more of a technical excursion to mention that there is like a lot of complex type theory behind this stuff, and a whole lot of work that would be required to figure out how to actually extend types in Julia. The one piece I want to touch on in particular is that, like, I think if you ask the question, like, if we had somehow started on the polymorphic side and said, I really want to be able to reason about the fact that the type I'm getting in this function has this field, or that it has an interface that I'm able to use it with reliably, then how do I do something like I do in Julia, where, like, the great thing about Julia is I can say I've got a type foo, or it's got a type bar, and then I can just union them together, and I can just have both foo and bar available to me, and I can compose that however I want. And inference understands it all implicitly well. The kind of composition you want to do with these kinds of facts about polymorphic objects is kind of the dual of that. You want to be able to intersect them. You want to be able to say that something is both hashable and an abstract array, for example. So this is where things can potentially get more complicated. I mean, we've seen designs in the community about multiple inheritance and user role dispatch and all sorts of stuff. But I think the main thing I'm trying to highlight here is just to say that there is a really interesting and detailed duality here, where we hop to the other side of the spectrum. Like on the monomorphic side, we wanted unions, and we started with lots of information about your object. We knew its exact concrete type, and then it only ever got generally worse as the function gets inferred. And the polymorphic situation is very much the opposite. We start with pretty much no information, and the user provides it, or your dispatch provides it. And then what we do is we try to preserve that information as you go through your function. And so we need to be able to kind of combine these assumptions and these facts together. And I think that alone may not be enough of a motivation, but the other thing that kind of pushes us in this direction is that subtyping has kind of seemed to converge here. So we might say, like, great, we might say that we've got enough subtyping problems with unions and existentials, and I totally agree with you. Subtyping has been a huge bugbear in Julia, and so extending the type system at all is really intimidating. But I think that part of what pushes us in this direction, unfortunately, is subtyping itself. Because if we look at the type operations we get here, we end up with unions and intersections, and the next logical thing is to say, well, why can't you just say everything except a type, like not int? And then you could intersect those two together, and you end up with you just end up subtracting one type from another. So all of this works, just to give a very rough sense of the semantics here, it works like sets do. So the unions are all the objects that would be of type T and all the objects that would be of type U are of the type union to U. The intersection is obviously the dual of that, so they're the things that are both type T and U. For concrete types, it doesn't make any sense. How can you both be int and float? You're just union. Your bottom. But for facts, that does make a lot of sense. You could be both hashable and an abstract array, or you could both have a field X with type int and have a field Y with type float, for example. Then the last entry here is a type subtraction, where you're saying take everything in set U and subtract it from set T. As a user, you might not think about that very much. This ends up being kind of useful for the compiler when it's reasoning about if statements and it wants to know what's going on in, like, an else branch, for example. But the connection with subtyping here is that this ends up being an equivalent analysis to subtyping. If you ask whether or not that type is inhabited, it turns out that that's equivalent to asking whether T is a subtype of U. Because the only way T is a subtype of U is if it's completely covered by U, which means that after you subtracted all of U away, you'd have nothing left over. So if this is uninhabited, then T is a subtype of U, which means that there's a weird, I don't want to say simplicity, because subtyping always ends up being wildly complicated. But there is an intrigue to this duality and a technical interest to this duality because of the symmetry here. Intersection and subtyping become very, very, very similar queries. They're basically the same query to the system. And then the other thing that kind of pushes us in this direction is, and you can kind of, well, yeah, I'll skip this slide for now. And then the other thing that pushes us in this direction is that there have been some very brave souls that have put in really valiant efforts into finding a decidable subset of Julia's subtyping. And and Julia Belyakova, for example, put together a thesis, and one of the errata to this thesis was that unfortunately we need negation and intersection in order to be able to get decidable subtyping in the way that it was formulated in that thesis. So even when we try to avoid negation and intersection, it seems like we end up wanting it anyway just to complete subtyping. So anyway, that's my talk. Thank you all. Oh, sorry, the last question I wanted to leave you all with is just, I think it's worth asking, who is our type system for? Traditionally, I think it's really been for cogen and inference, but I also think it's, and then we've had this whole dispatch system layered on top of it, but I think now we're starting to really get to use cases where we want to start considering these cases more seriously, which are static analysis, humans, documentation, and even cases like AI. Julia can't be very easy for AI to write if it doesn't get feedback from the editor. And so being able to provide this kind of feedback is useful for both man and machine in that sense.
Thank you. We might have time for one question only, sorry, while Andrew sets up. So Andrew, if you're here, please come and set up while I have one question. So I saw Jorge's hand first. So.
Okay, the question. So the question is, why stopped you to having this type system before, and when can I have it?
Yeah, I think we need to do the due diligence in actually turning this into like an RFC and a design document. Like the main thing I wanted to provide today was a perspective. I haven't even bothered to go through the checklist of what we'd want to consider in terms of details for actually rolling this kind of thing out. But the encouraging thing I would say is that, as was mentioned during the State of Julia talk, like we have been thinking about language evolution a bit. So I would recommend you go to Kenno and ask him what he thinks about the possibility of this kind of extension and how we might do that.
Andrew, are you here? Yes, please set up. While Andrew sets up, maybe we can get another question from Tim. Tim, you had a question?
So really beautiful talk. I'm especially excited about the type system stuff you talked about at the end. But to go back to an earlier point, I do want to point out that one of your two polymorphic reasoning things we can already do. And that is you can write get property methods that dispatch to get on taking an abstract type as the first argument and the field name as the second thing. For specific field names, you then dispatch to get field and you put a type assert after that saying it will return a pointer to, you know, C void, right? Or something like that. And then all subtypes of that abstract type they're required at that point to return, unless they overload get property again, right? You know, but as long as that method doesn't exist, then inference knows what that return type will be.
Yeah, that is a great point. I do think that type asserts are actually a great example of this kind of like user-provided ascription. So yeah, absolutely. Yeah, you don't have a clean way of doing that for methods that you're pointing out. Right. Yeah. I think it's the clean way and the fact that it can be picked up by tooling, which is very helpful. Yeah.
Thanks. Thanks, Cody. Round of applause for Cody. Thank you. Cody's around, of course, for the rest of the day and tomorrow. So there were a few questions, but I think we should move on. Thank you. Our next talk is from Drew Dalgert, who will talk about testing, which we are all very keen on. So over to you, Andrew. Thank you.
Thank you. Hi. This is going to be a talk about the packages that we use to test Julia. A lot of people have written packages to help us with the testing process. And when I say a lot of packages, what are you thinking in your head? Are you thinking 10? Are you thinking 100? Are you thinking 1,000? I went and did a survey of them because I was curious. And what I'm talking about here is the packages that we use in our test directory. Sometimes they're listed in your project.toml in the test directory if you're doing that version. Sometimes they're listed in the extras of your main project.toml. I went through and looked at all of those. And so I'm an academic, so I had review criteria, and I didn't want to give you my opinion. I wanted to go through everything that I could find. And so this is all tracked in my GitHub under juliatestdeps.jl. This talk itself is in the docs directory of that, if you want to take a look. But I went through the 12,000 packages, 12,000 plus, as you've heard in so many of these talks on JuliaHub. I went through GitHub. I looked at the most recent packages on GitHub that match the word test. I had to match the word test because so many of them have no tests. But just to see how the trends are doing. The ones that I excluded, I put little notes every time I excluded something that was used in the test directory. That would be things that don't install under LTS 1.10. That's the criterion. Or things where, let's say you had a package that figured out the nail polish colors that sell the best. If you also have nail polish colors test, that's just for you, didn't count that one either. There are a lot of those. It's a super useful pattern that people use where they have a test package for their main package, but you're not on this list. If there are others that are missing here, let's try to pick them up at the end. I'll try to end in time. Oh, by the way, on JuliaHub, when I went to search for which testing packages were used the most, couldn't really find that. JuliaHub does the thing that you most want it to do, which is to show you the packages that are in the main dependencies of your packages, the ones that you care about when you install. The test packages don't really get marked, and so their popularity, their usage doesn't really get shown there. And so that's another reason that I went through this, just to figure out what's going on and who knows something about testing that I'd love to know. So I'm here from the Software Engineering Institute. That's why I've been sitting at a booth. I'm so happy that they sponsored this year. I'm in the AI division. We're down the street. We're part of CMU. And I myself have used Julia since forever, as far as Julia is concerned. Really love testing scientific code. I have 3 packages, one of which I will try not to talk too much about today. So the organization of this talk, I'm going to pretend that I'm a person who's testing. I'm going to pretend that I'm a person who's really stodgy about it. The way that the International Software Testing Qualifications Board talks about testing. We don't often think of it this way, but you choose your system under test, then you generate test cases. You could generate a lot of them, and then you select a subset of those test cases. You decide how you want to run them, and then you report on them. I know that this isn't how you work for test-driven development, but it is a way to organize this talk as though we're walking through that today. So, first of all, there's a lot that happens in tests that isn't testing. And we're not going to count these as testing, I guess, but it doesn't matter. So the test directory is a great place to use your package for things that you need to do with your package. And so people build their packages with package compiler in test, as an example. They write documentation or papers in their test directories. It turns out, I'm just looking through what people have done. A lot of people do test-driven development, of course. And so their revise is often used in your test directory, but also one that I didn't know about called Infiltrator that will let you drop into a live debugger. Super helpful if you're running a test case, you see a problem, you want to debug it. Infiltrator is something where you put a little note in there, a little macro, and then it'll drop you into the debugger the next time you run. Oh, I'm not going to discuss every bullet because I don't want to go too quickly. And so these things are all there later if you want to see the PDF. The next question, what's our system under test, right? And so you should test all the things. Everything you show your user, you're going to test in some way, or you can, at least, given all the help that you have from the people who have written these packages. So docinventories.jl is one way to test the documentation. But of course, benchmarking happens a lot in your test directories. Your benchmarks are not functional tests. That's the tester's word for testing if it's correct. But benchmarking is the way that you determine if it's fast enough. And the most used benchmark tool from the survey that I did is benchmark tools. The most recent benchmarking tool is Chairmarks, and I've seen that used in a couple of these this week. AllecCheck is one that I didn't know about. It'll check that your function does or doesn't allocate memory when it gets called. And if you're hoping to write a function that's efficient in Julia, often you're trying not to allocate memory. I didn't know that existed. It's one of the surprises of the day. A bunch of the tests are testing the package itself or how you've made the package. As we know, this can be a somewhat delicate process in Julia sometimes. You can write a function that overwrites a function in something that you used without actually let's say you need to import base to use base.getIndex. There are packages that test things like this. The most popular of them is Aqua. When you create new packages, there's an option to install Aqua. It's nice. It catches a lot of things that would normally be caught later, such as your compatibility indexes on GitHub. If you use Aqua as a local test, then you won't have those compat problems later on GitHub. So much so that compat helper is no longer really going to catch anything on your code. Jet.jl does similar tests. It's a little more in-depth and used less frequently, but used by some of the largest projects. And, if you're new to Julia especially, interactive utils and stdlib, it contains a whole bunch of macros that will catch things about your code by using macros like @which looks for method names that take certain arguments. Take a look at what's in interactive utils if you are new to Julia and trying to figure out how to test a package. It's built in, but super helpful. Again, we're choosing the system under test. 3 interesting packages in Julia will test systems under test that are not library function calls. I find them very interesting. One will record HTTP traffic and play it back. That is the most used of these. The 2 others will test the GUI and test a terminal user interface as though you are the user. So the GUI one will click on your graphical user interface if you happen to be using IMGUI. The terminal UI will send character keystrokes to your terminal application. These are super inventive and great ways to do testing. This keeps going on finding the tests. There's a lot of different ways to find tests. So if you offer a README to the users, which we all do, might as well test the code in the README. Might as well test the code in the documentation with the doc tests. If you are showing a notebook to your user, there is Pluto test and NB include to test those notebooks. It all makes sense. When you do your tests, you often need to download files, and you have that moment. I don't want to check this into GitHub, okay, but I do need to get to the file. How do I do that? The ways that people solve this problem are varied. These are most of the most common packages that are used in your test directory when they aren't also used in your main dependencies. A lot of people use downloads. That's the most popular one. Downloads is sort of that one function package that has download. Really straightforward. The newest one on this list that I want to call out is datadeps, which tries to be more specific about the identity and the hash of the thing that you're downloading. So that's super useful. But people will use AWS, Google Drive, any way they can get to the thing they need to get to in order to use a file for their testing. And they use any kind of file format. This is actually not all of them, but it's just a panoply. In other languages, you might think a lot about fixtures for testing and how we use fixtures. Julia has one main mocking class that gets used. I understand it's going to be of more use in 1.12 when the world age is working nicely. And so mocking is a tool that will let you pick your function that you want to test and test that single function more specifically and less the collaborators of that function by swapping out some of the other functions that it might call. The next line is about ways to capture standard error and standard out. Have you guys ever heard, there's a paper on how to make functions testable, and it has principles that are SOCs to make it simple, observable, controllable, and knowable. It's not a really well-known acronym, is it? SOC. But if you can't observe what's going on in your package, you can emit text with @debug and then catch it with suppressor or IO capture and then use that in your test cases. Similarly, there are other useful fixtures like Scratch, where you can write temporary files, they'll be deleted, or .env, where you can load environment variables if your code is interacting with the environment. So you can try lots of different environments. 2 different kinds of tests. We're now in the test case generation part. I find this part really important. I think in a world where we're working with LLMs, they can, in their best usage, can reduce the burden, the barrier to using more complicated things that are also more powerful for us. Property-based testing is an example of a powerful way to generate a lot of tests that are going to be more effective, especially if you're talking about lower level functions in your system. Property-based testing is going to take the arguments to your function, you give it the types of that argument, maybe a little more information, and it will generate tests that are most likely to find corner cases in your function. That's the idea. Of these 3, there's prop check, randomized property test. I think supposition has the sort of the longest, most thorough documentation. And there's an example here. Property-based testing is a real boon to have in the environment. So combinatorial testing is another kind of test case generation. The easiest form of combinatorial test case generation is right there in the regular package test, the default package test. So if you write a test set, you can write a for loop when you generate that test set, and it will create, 1,000 tests in your for loop with 1,000 different arguments. Here in this example, there's a V in ITRV. We're assuming ITRV is some iterator over V. It'll generate a separate test for each of the V's and each of the W's. Unit test design, that's mine, so I won't talk about it too much, but it is a way to write tests for that top level of your application. So at the top level of your application, you have a whole bunch of options often, you have a whole bunch of arguments effectively. If you want to choose a few of each argument and then try to generate test cases that best cover all the possible options within as few cases as possible because it runs for a long time, that's what unit test design is for. It does in all pairs in this case, but it does other things. The branch tests, I had never seen before. I thought it was odd when I first saw it. It's a way that you create a normal test case, and then it's hierarchical. We often make hierarchical test cases, right? You nest them. In this case, when you nest the test cases, that forms a little tree. It will generate a separate test for every way to walk down that tree. It wasn't something that I knew I needed, but it's kind of fun to find. All right, testing scientific code. Most of what we do when we write scientific code is we write things where we don't know the answer, but they're often comparable to other things that are similar or other code that writes similar answers, right? How do you make tests that test scientific code? It's this parabola. It's a testing by comparison. So these get used a lot. So R call, Python call, people keep the R code in their test suite. They keep the Python code there because then their code gets compared to the code that it was originally copied from. Maybe you know yours is always higher or lower. That kind of trait gets tested. And there is a bunch of use of types in tests that are not the types necessary for the package. Let me explain. Let's say you write a package and it works for abstract matrix. You know that it worked in your trial for a dense abstract matrix. Well, you can put in strided matrices, sparse matrices, all the different kinds of matrices in order to do a comparison there. You can run symbolic versions through, thanks to Julia's interoperability, and use those to do your test cases. So there's a lot of kind of the weird and wild versions of containers that get used in test cases. Of course, people want their assertions to be as descriptive as possible, and it's not sort of hard to work on these. There's a whole little plethora of different ways to improve your assertions. Safe test sets, for those who don't know, gets used a lot. A safe test set takes your test and it puts it into a little module. And when it's in a little module, because of scope, it is a little safer from polluting the world and being affected by the rest of the world. At inferred from based is used a lot in tests. I'm saying this for the new Julia users. We talk a lot about type stability. The way that you make sure that you've managed to get type stability, at least maybe not sure, but you can test whether you have type stability, is to use at inferred in your test sets. It gets used quite a bit. And remember, at inferred, it will return its values, so people use it quite liberally. They just pepper their test code with at inferred. There are a bunch of tools here that will make your diffs better, so that if at the moment you do your at test, you say is A equal to B, it will tell you exactly why A is not equal to B. Deep diffs, struct equality, both do that kind of thing. The other one that I'll call out here is Uniful. You may think, okay, this gets used in test sets, and here's why. If you've written a function and it's meant to be science, it's meant to be chemistry, physics, whatever it is, and it's doing a calculation, if you use Uniful, you attach units to that test, and your output should have the correct units. If your output doesn't have the correct units, that's a good sign you did the wrong thing. I'm a physicist, I'm sure of this, but in the testing world, they call this metamorphic testing. They give it a really big name. It means if you scale A bigger, B should scale down, whatever. Uniful is a great thing to use in your tests. All right, we have a few minutes. We're going to talk about the frameworks and then how you judge whether test cases are good or not. So test.jl. all of the packages that are frameworks that try to replace test.jl talk about two things they're going to do for you. These are the two things. One, they talk about that they're going to be able to find tests in your test suite and then not run them immediately, but store them so that they can change the order of what's run, filter what's run them in parallel. They also talk about being able to test code that isn't in the test directory. These are the two features that most of the test frameworks that try to replace test.jl talk about. Of course, we know test.jl works for 99% of the things that you want to do in your testing. There are a bunch of test frameworks that don't load on 1.10. And I just want to salute these folks. I've used a bunch of these over the years. I really appreciate this work. Right now, you may be a person who likes having control over all the parts of your environment. There are tiny test frameworks that are just for you. I'll call out Pukeko, which is the name of a bird apparently, and they have a photo of it. Just for that, it's worth seeing. It'll give you parallel test execution without doing a lot else, and maybe that's what you're looking for. As well, TidyTest doesn't actually provide its own framework. It's a new subclass of the test set, which is an abstract base. TidyTest will let you do test selection using the regular test. Both small, nice additions. Here are the 4 big test frameworks. And I went and looked at how popular they are. So test items, test item runner, retest items, these are all associated with the Visual Studio Code plugin. These are really growing in popularity very quickly. Retest, XUnit, and Jute all have really similar claims to what features they do. Retest is the most used of them. They do that thing. They collect your tests, they select your tests, they run them in parallel. And they focus more on how hard is it to run my tests? How hard is it to filter and select them? Test item starts from this one big move. It says, we know that the code that is in your package is costly in Julia, right? You don't want to put tests in with your package because they need to get JITted, they need to get installed. Test items makes a macro for your tests. Tests always seem to use macros, but they make a macro for your tests that go in your package. By default, that macro evaluates to nothing, just the word nothing. And test items, when it goes to run your test, grabs them, compiles them, and then runs them. But by default, they don't pollute the test base. That's the big move around test items. And I'll say in all of these, there's inventiveness. XUnit, retest, Jute, test items all have some nice moves in there. There are a couple tools to run unit tests. I'll mention Eye of Ra because it's nuts. It will run your unit tests continuously. Just keep running them in the corner. It's a wild idea. Test Picker got mentioned this week as a REPL mode. Excellent idea. There's also a CLI for running tests, also an excellent idea. For seeing test case output, the Visual Studio plugin shows you what you see above. This is for one of my packages. There's definitely a hit when you see everything go green. It's really pleasing. It's worth writing more tests just to see more green lights, I think. But there are other things that provide other kinds of outputs. This, I also think, so I called out test case generation. I also think the test quality is important. And the more that we aren't writing our own tests, if that happens, the more that understanding the test quality matters. Julia always almost seems to measure your line coverage for lines of Julia. Oh, more than I thought. And your local coverage is a version of getting that coverage locally. Now, I've talked with a bunch of people who wanted to get coverage, line coverage that was more where they could get line coverage for an individual function, or they had a mono repo with a bunch of packages in it, and they wanted to do separate coverage to the mono repo. I know that it's possible to sort of hack the coverage mechanism in order to get better coverage. Right now, coverage and local coverage are the two most often used things that we have. Julia had, probably 7 years ago, something called VIMES, which did mutation coverage. You may not have heard of this. It is the gold standard It's not perfect, but it's still a gold standard for the testing community to evaluate the quality of your test suite. What it does is this. You have a test suite, you have your code, it makes a copy of the code, and then it finds a spot by random, and then it breaks it. Then it runs your test suite and sees if the broken spot was found. And then it fixes that, goes to the next one, breaks the next one. And so it just does that repeatedly, goes into the syntax, usually use it sort of a syntactic understanding of the code, breaks it over and over again. And Vimes did this. It doesn't run on LTS 110. I don't really know the state of it. But the story is that by the time you're done with this, you know the percentage of broken tests that were found. The problem with this is that when a test is broken, it might not really have been broken. They might have added a +1 to a loop index where that loop index was never really exercised anyway for another reason. There was always a break or something like that. So even so, the mutation testing is an interesting sort of gold standard. In addition, there are other kinds of coverage that we don't have. You can have branch coverage. You can have path coverage, function coverage, modified condition. Decision coverage is sort of the nutty NASA level standard. But there are other ways to do test quality that I think are becoming more important over time. So the end is, when I look at this, I think, what would I love to have, right? There were 70 to 80 packages I talked about there. There's a lot of effort that goes into making testing better, of higher quality, which I really appreciate. I'll note that one of the things that I've used in Python, was a way to measure test coverage per test. In our case, I guess we call it per test item. You figure out which parts of the code get exercised. When that piece of code is exercised, only the relevant tests get run again, which can really speed up your test case runs. And that's, in order to do that, you need test selection. You need a little bit of memory in your test environment. You need a number of things that we don't generally use. And another is randomized tests. There are no packages that help randomized testing. There's work in the frameworks. Specifically, I think there was a recent work in test.jl to make randomized testing work better. But there's sort of no packages to help make tests. For instance, for scientific coding, it can be super helpful to ask, when you ask not just is A equal to B, but how can I optimize the arguments to a test such that A is as far away from B as possible? That's the kind of thing that helps with scientific code. It's an optimization problem. It looks a lot like probabilistic programming. But if you have other ideas, I'm open. Or if I missed anything, open to that too. That's it.
Thank you. We have time for a couple of questions. Rachel?
Cool, thanks Drew, real tour de force here. I'm curious, maybe it's in the repo, do you also have like stats collated on all these things you went over in terms of like how often different things are used and all of that?
For myself, I rank them 1, 2, 3, 4, 5, but I don't have the percentage of times they're used. Even it would be nice to know the percentage of packages that do or don't test at all. Just where are we sitting? But I don't know what to compare that against. Right? If I go to the Java world, how often do they test? I have no clue. And do I care how the Java world tests?
Okay, there's a question here.
Very good piece of work. I truly appreciate. I'm wondering, I suspect that many testing framework will be used at the same times. And do you have some feeling about that?
Are you asking whether the test frameworks get used at the same time?
Yeah, I mean, I would guess so, but for one application, they will use not just one, but several testing framework. And they may, I mean, in our code base, at some point we were using relint and retest, and we were using the XUnit at the same time. And
you're right. You can write your tests such that multiple frameworks can be used to run the same set of tests. And I haven't looked for that. That's a really good question. Because it's a great way to go from one testing framework to another. Or, look, the mindset, I think, in the Julia world doesn't even include things like, what if I'm running several processes, and I don't just want to, you would want a separate framework, essentially, to test different capabilities of your code. I haven't looked. It's a great question.
So regarding for the test selection thing, I actually wrote a new package named testrunner.jl, which exactly does that and allows you to run per test case execution of test code. So yeah, it only works on 1.12, but you may want to try it.
It's called, you said testrunner.jl?
Testrunner.jl. It's not published yet.
Okay, good. But no, this is the right time. That's perfect.
Okay, thank you, Drew. A round of applause for our speaker, please. Thank you. Jorge. We have a couple of minutes.
That's good to know. No, we don't have it.
It's an extended mode. You need to mirror it.
No. I just need to restart the slide, I think. One, two, three. Okay. 1 minute? Okay.
Otherwise, the online streaming gets...
It gets off.
Yeah.
Fair enough. You tell me when.
Yeah. Can't start in advance. Okay, I think it's time to get started with our next talk. We have Jorge and Yuri from SML talking about how to put Julia in an expensive machine.
Yes, thank you
Over
very
to
much. Okay, thank you. Thanks everybody for coming. This is actually my first technical talk at JuliaCon. Not my first talk, but first technical talk. So I'm happy about this. So first a quick intro. So I'm Jorge Viera, in case you don't know. I'm a lead functional engineer at ASML. We call functional at ASML people that are into the domain knowledge, domain-specific knowledge, algorithms, physics, math, whatever. And Yuri here is a software architect, although his background is in neuroscience, I think. So he probably knows more about algorithms than I do. But he's on the software side, and we're usually, we're two sides of the same coin at ASML. He works on the software side of things, and I work on the algorithm side of things. And you know, with Julia, we want to blend these things together, but that's how it happened at ASML. I'm not going to introduce ASML because it has done it before. We have a keynote, very extensive keynote last year explaining what ASML does. So here's a link, you can look for it. But what I will going to explain is a little bit how a chip looks like. So I took this image from Wikipedia. And you can see this is a cross-section of a device. Well, it's a schematic of a device. And you can see it has several layers. That's how chips are built. They're not printed in just one soup. They're built on layers, upon layers. And usually the lower ones, what we call the front end of line, are the most advanced layers. The layers are made with the most recent advances in photolithography and process nodes and stuff. That's where the actual transistors are. And those are the most expensive layers. And as I said, made with the latest machines. In the case of ASML, there will be the EUV machines. Maybe you have heard about those. Then the intermediate layers are done in older, previous generation technologies. Also advanced, but not bleeding edge as the front end of line ones. And then all the way to the back, you will go for more mature technologies. And maybe you can see here that feature sizes start to increase as you go to the back end of line, as it's called. And at the end, you end up with a connector This might be something that you can actually solder into your computer. Those are your connection pins that you might be able to see on your package. So that's how a chip is built. And I know that in recent years, we have been talking about UV machines that have been on the news because they are the most advanced and blah, blah, blah. But we also have other very advanced machines that are previous generations, but still kind of good. So we have the twin scan machines, so the immersion machines. So that's our previous advanced machines. And we also have what we call dry machines. So I just put a couple of those over here so you can have an idea. And as I said, we usually talk about the nanometer resolution of each of the machines. So UV has this 8 nanometer resolution, took this from the website. The previous one has a 38 nanometer resolution and the all dry 110 nanometer resolution. That sounds big, but I mean, it's very small still. But the important part is not, the important metric for us is not the resolution, but this other metric over here on how many wafers per hour it produces. You can see that the very advanced machine is fast, but it's not the fastest one. Produces 185 wafers per hour. But the previous nodes produce like 310 in this case, or 400 in the dry system. So they're like producing pancakes. They're really fast. And why is that important? Well, if you focus on the immersion ones, which tend to be the ones that we benchmark with, they produce roughly 300 wafers per hour. I'm rounding things up. This, by the way, is an animation of how our twin scan system works. It's measuring one wafer at a time while it's exposing the other one. But each time it exposes one wafer, one field at a time. It has roughly 100 to 300 exposure of those. Each exposure might have 1 to, I don't know, 12 dyes, depending on the reticle size. And that means that each wafer is exposed roughly 12 seconds per, we have a wafer every 12 seconds or so, which means each exposure takes 400 milliseconds. That means that we only have like 330 milliseconds or so of calculation time. Where did the other 10 milliseconds go? We don't know. So, but we have, that's our budget. And we have to make all our calculations within that budget. Because, well, as I said, they have like, let's say 100 exposures per hour, 1 chip per exposure, $50 per chip. That's roughly 1 million or something, 1.5 million per hour. So this is basically printing, they're printing money machines. So we want to be able to make those exposures as fast as possible, increase the yield as much as we can. So that means that the algorithms that come into optimizing these exposures to increase yield, make things better, are becoming increasingly more complex. And we only have 30 milliseconds. So that's why we have to do this. And we, of course, customers want to have this not today, but yesterday. So we have to deliver as fast as possible. And that's why we look into the Julia programming language. Again, this slide has been shown in previous JuliaCons. We're just going to go through it. So we have an idea. It's usually the case that we have a prototype. And these prototypes are usually made in Python, Metal, whatever. Now we want to do it in Julia, because when you have the prototype, you want to immediately put it as a code, as a product code. And traditionally, that's rewritten in C, C++, whatever, and you put in an equipment. In this case, we're focused on these twin scan machines, and that's what we want to do. And we say, okay, fine, how can we actually achieve that? Can we make a proof of concept on how to make a Julia calculation that has to interact with the rest of the machine, which is already written in C, C++, so it doesn't come in a vacuum. The algorithm is in Julia, but we want to deploy there. And we have certain restrictions for that. So we have to be fast, of course, but also very, very important, has to be consistent. I mean, garbage collection calls are not allowed. We cannot wait for Mackie to finish compiling. So it has to be like, everything has to be pre-compiled ahead of time. We're not using Mackie, by the way, on the scanner. So everything has to be compiled ahead of time, no JIT, and everything has to be very steady, and we have to interact with our interfaces. So those are our requirements. We have an extra one, is that, okay, we can do that with package compiler, but package compiler has a large binary, so that's why we want to get away from that, and also we want to be able to reduce the reverse engineering aspect to it. So the package compiler also has a lot of metadata included in that. So that's why we look into using what we call JuliaC. Here we call it trim. XML, some other people call it the static call graph. I will use these 3 terms interchangeably, but we all talk about the same thing. So we have been working with Julia Hub for some time now. I think like more than a year and a half or so, almost 2 years, with this feature. So let me just show you one toy problem that we look at. We said, okay, let's use some Czerny polynomials. That's something that we use thusly at ASML. So these are, if you don't know, these are polynomials that fit round things, so like a wafer or a lens. So those are things that we have. Usually people just show these circles, which are the monomial terms for the polynomial, and they fit those kind of weird geometries on a wafer. So if you add enough of those, you can feel weird shapes on a round domain. So we usually use those. We thought, okay, let's use something that's kind of reasonable that we can just measure on the wafer. We can expect 100 measurement points and a 7-order Czerny polynomial. That's like 76 monomials of this. So we want to have something that's kind of representative, and we put that as a proof of concept on our machine. And we asked the software guys, and they say, okay, you have like roughly 1.5 milliseconds of budget to do this kind of calculation. So as it happens, I wrote some code for this some years ago and said, okay, here it is. Please, software guys, please take my very fancy fast Czerny code and in Julia and try to make a proof of concept. Say, okay, we need to make a binary size. At the time, they could not do it, but okay, we will say, okay, just make the Julia code. And one extra restriction I forgot to mention is that because these systems are also running on some legacy platforms, AVX512 is not allowed, among other things, because also if AVX512 overheats the CPU, and then this variability is quite high. So that's not allowed. It's like one restriction that we have, no AVX512, which is kind of sad. So I'm just going to quickly show you 2 kind of benchmarks, just benchmarking the Julia algorithm itself, and then when we interface it with the TwinScan, also benchmark that, because the interfaces, that code also might generate some overhead. So I will focus on that. First on the algorithm. So as I said, I gave these Czerny polynomials module to the software guys. They made a proof of concept. They came back to me and they showed, I don't know if you can see this plot. And they say, yeah, well, it's kind of on the budget, but it has these weird regimes on calculation times. It's usually fast, but then sometimes it's not so fast, and there are some outliers that go out of budget. So what's going on with your algorithm? It's like, it's not steady enough. By the way, this is running in a simulated system that has the same run characteristics. So if it's produced with this calculation time over there, that's what we expect. So this is what the scanner will see. Let's see. So like, okay, let me take a look. I cannot test it in these machines that are limited. I can test it on my Windows machine, so that's very noisy. So that's the noise. That's why you see the same. This is the same plot, but with my noisy Windows machine. This is also the scales a little bit different. It's logarithmic scale, but never mind. You see, that's also noisy. It has several regimes on the calculation time, and also has some outliers. On top of those outliers, I thought, okay, I'm just going to get from benchmark tools which ones are GC times, and those are the points in orange. So I thought, okay, if I get rid of those, probably I can get rid of those outliers. So start to work towards reducing those allocations, so reducing allocations, dynamic dispatches, and so forth. And eventually got it like, was almost there, and by myself, I was almost able to get rid of all of them. Hopefully Gabriel helped me, and then I was able to get rid of Baraldi from Julia Hub, and he helped me to get rid of all the final allocations, so it was no allocations done with this Czerny code. So I was really happy about that. So I said, okay, let's benchmark it, and it was kind of okay. So I was happy with that, but let me just quickly explain what I did to get rid of those allocations. So of course, I got rid of all the abstract types that were kind of plaguing my implementation. It was one of my first Julia modules. I put some tuples which had variable size, just made them fixed size, too bad. I was able to use infinite number of Cernica terms, but that was kind of unfeasible with my design, so okay, so if I have only 200 and something, that's twice the amount of Cernica that we use, so that's good. I convert a lot of broadcasts to loops because just using loops is awesome. And I remove several allocations, change things to if else instead of dynamic dispatches, and used one thing I wanted to use from the very first time, the very first thing when I wrote these things, used generated functions. At the time I didn't know how to write them, but now I know enough to write those, so I was quite happy, and that's how we got rid of most of the allocations. One thing I have to remark is that I used loop vectorization before. I was a fan. I'm not a fan anymore. For a very reason that it always forces AVX512, and you cannot get rid of that. And that was like, oh, super annoying. So I got rid of loop vectorization. I still use vectorization in base, but I still have to rewrite a few internal packages. I haven't upstreamed them, but I have to have my own implementation of CPU summary and host CPU features because it has a lot of dynamic stuff with evals. So I was very unhappy with it, but okay, that's what I'm using. And also found out that sometimes Vue generates inefficient code, so I have to get rid of some of the views. So maybe that's for the Julia compiler guys. And also, not super happy, but to get rid of some of the GC calls, I have to use pointer arrays, so it was some manual memory management. At least I was happy that I was able to do something about that. These are some examples of things that I did, probably you can see them. I remove some integer, abstract integer types that I had on my structs to just int. Also, as I said, I just made this tuple fixed. Also got rid of some of the allocations. Instead of using tuple, which returns a variable size, you use fixed to end tuple. And there are several examples of that. I will not go through all of those. It was basically what I did. How I found this, well, at the time I didn't know that Jet could do that, but I found all of these dynamic allocations and stuff with a log check, and that's how I made the thing also trim compatible. So I was quite happy about that. So now, these are just the things that we found for the algorithm itself, but we have to interface it with the machine, and for that, Yuri is going to explain what needed to be done.
Yes, and the first problem that we had with integration to the machine is actually a decision. Do we put it as a just algorithm that we can call, or it should be tightly integrated? And we have a lot of interfaces in our code base. It's a really huge code base, over 50 million lines of code. And we said, okay, it's unfeasible that we will rewrite everything to Julia. And it's also unfeasible that we will keep writing only algorithms which are endpoints, so they don't depend on anything. And because of that, we said, okay, Julia should be like first-class citizen in our system. So it's not only called by our machine, but it's also calling it back to call some other algorithm to retrieve some data in real time. And that was the first reason why we said, okay, it should also communicate to it. It's tightly integrated. And the other problem, of course, our tight timing budgets requires that we don't copy data too much. We process a lot of data we can't afford copying it around. So the memory's safety, if we pass data by reference, was really important for us. Second was biggest question from all software architects who didn't worked with Julia was like, okay, Julia is not similar to C or C++, that's the majority of our code base. It has garbage collector, so what does it mean for our performance? Can we even achieve reasonable performance, even if our algorithm works well? It still uses garbage collector, and indeed how Jorge showed, for some algorithms you can get rid of garbage, and so you don't need garbage collector, but yeah, in theory you cannot do this for any algorithm. So that was a big thing. And the third problem was, how do we actually implement the static call graph? It was the first time when we started this discussion, static call graph was on horizon, and we actually started doing this work, even didn't know that the static graph will work, and that was a really nice collaboration between ASML, Julia community, and Julia Hub to make it happen. Let's go from the problems one to each other. Memory safety and pass by reference. I had a talk about it yesterday. I will not go in the details. All right, let's wait for a bit. All right, so pass by reference, how we solve the problem, how we are able to pass data allocated by C directly in Julia and work with it without any copies. And by the way, if you look here, this is a real life example, and you cannot see any unfamiliar Julia instructions or syntax except the first line. Yeah, because it's also transparent for our developers. Yeah, I had a talk about it yesterday. Please watch it. It's online. Second problem, garbage collector. Well, it's the biggest thing. But actually, it's not. What we found through our testing that you can even live with the current implementation of garbage collector. It's quite good. I will show you results on the next slide. But our main intake of this study was optimizing for garbage collector is actually not really necessary. You should not really worry about this. You should worry first about your code, what kind of algorithm do you run, what's the performance of this algorithm. But if you will optimize for a garbage collector later in your process, you will get additional performance. But if you feel that you are not capable or you have no time for this or it's too difficult, you actually don't get probably too much. Anyway, there is a couple of other strategies how you can deal with garbage collector, and let's look at them. So this is the first one is exactly the algorithm that Jorge described, but we plugged it in our interfacing system, and as an implementation detail, our interfacing system actually always produces just a bit of garbage. It's just a few extra objects, but for every call. Here we have a lot of calls. And we see that some of them are actually exceeding our time budget of 1.5 seconds, but actually not that much. The amount of the calls is really minimal. For us, it actually doesn't really matter, so we can live with the existing garbage collector, and the average time was around quarter of a millisecond, so, which is totally acceptable. But we thought, okay, what if we have other situations? And we thought about this idea. What if we just disable, because our algorithms here is very small, it's very fast, it doesn't produce a lot, so we can just disable garbage collector, we can do our computation, and then we force garbage collection, right? So instead of having the random spikes somewhere around our code, we have a guaranteed spike end of our code. Okay, what does it mean? Here's the test for the full collector, right? So the garbage collector of Julia supports the full garbage collector and the short garbage collector. Here's our results. It's still fitting the budget. So which is actually a very interesting observation, right? If you look at these two graphs, the left one and the right one actually do exactly the same computation and produce the same amount of garbage, but because the garbage doesn't accumulate, you never have this full strokes which takes time over the budget, which is very interesting, except the outliers. What's about outliers? Well, we found it by experimentation that garbage collector takes time to settle down. This is the procedure that we use to preheat it. Apparently, even that is not enough. And I just decided, okay, we'll leave it here to warn you about this. The start of your system will require a garbage collector to settle down. Once it's settled down, it's quite reliable, quite stable. There is still some noise, but it's probably noise of the system, not the noise of the Julia, right? And in our case, we don't produce long leaf objects, actually. Everything which we produce can be disposed at the spot, and then you can just use short garbage collector, which is working really fast, which works much faster, and you get the really acceptable timings. There is a lot of extra space to put your more computations, to make your algorithm more complex. But what if you are not happy with that, right? What if you really need to produce a lot of garbage every call and you cannot deal anything with that? Well, there is an alternative strategy. You can stop, you can think outside of the Julia now. You can think about, well, my Julia is just a part of a bigger machine, and the bigger machine is doing client-server interactions in some way, right? And in this case, let's look at the timing diagram, right? The client is sending a request for the server to process, and the server is busy with processing it, and then it's busy with garbage collection. Let's assume it like this. Garbage collection can happen in the middle, but it doesn't really change anything. What if we say we disable garbage collector, right? We do the computation. What if we're able to return the data before we start garbage collection, right? What if our server allows it, and apparently most of the server implementations do allow you to postpone some action and return the result to the client before taking this action. Then you have such a timing diagram, right? Again, this is just an example. And the only difference is, well, you have this extra gap, but the client gets the result much earlier, so you actually don't see anything from the garbage collector on your client side. You just don't see it, and indeed server takes a little bit extra time, but usually with the correct implementation, this is like really peanuts. You will not see it. The only requirement for that is that your server is not overloaded, right? So if there would be constant requests, it will not really work. But in reality, we're all trying to design a machine which is not only responsible. This is not real-time system, right? We are not working in a real-time system. There's always some gaps which allows for some delays, some fluctuation in the system to just accommodate for it. So we actually have this situation, and this can really work for you as well. Other problem, static call graph. Static call graph is a funny thing. It's really nice. It makes small binaries. It works really fast. But it has some peculiarities. And here I'm just showing one example which I find is quite interesting to know because it's not obvious on the surface, right? What do we do here? Essentially, we're asking Julia what is the return type of a map which applies identity to the vector of int64. Well, you can't expect that we do nothing, right? We just iterate over the vector, but we don't change anything because it's identity function, right? And the result is what we expected. What if in our vector, we don't like abstract types for the static call graph, right? But the first approach when we think about this, oh, we need to mix several types. What if I have a union of types, right? This should work really well. Let's have a look, yes. What if we have vector of union of types? Actually, static call graph is very happy about this. It understands that there's only two possibilities, so we can compile. But surprisingly, it returns union of several potential vector types. And if you look here, the vector is now doesn't have union inside. It says signed because at a certain moment, Julia thinks, well, unions are too complicated. We need to compress them. And if you keep extending the type, then it thinks, okay, there is too many possibilities. And this is abstract type. This is abstract type. Static call graph is not happy. One potential solution, I'm not saying that the only one, is if you can use tuples instead, it will really work. So tuples are much better in that case, but that's not the only way. Let's go shortly through our struggles, right? As Jorge mentioned, abstract types in a struct's usually a bad idea. Functions with concrete types is not that nice for Julia or expandability. Multiple or dynamic dispatch is actually available even with a static call graph, but you need to be careful not to trigger it too much. Unions is a trick, and tuples is your friend. And there's many tools in Julia which can help you to deal with this. However, through our testing, we found that, running Julia C is more reliable. Sometimes this is hidden, but as we saw on this conference, Jet is really under development. The new versions are coming. The problems would be solved, I believe, end of this year. This is really nice. And some of the community packages are actually not compatible with the static call graph. This is the two that we were using. But we were happy to see that Julia Hub helped us to solve this problem. So a subset of HDF5 is now static call graph compatible, this subset that we use, and OM Einsam, I think, the fully compatible.
Cody, I'm still waiting for that PR.
All right, it's not yet delivered. It would be. Compilation-wise, well, we see that the binaries are really small. This is really nice. You need to still to study compilation flags of Julia, because if you compile it on one platform and deploy to another platform, it will most likely not work. So please study the CPU optimization flags. But you can actually work around this. But what we actually found that because the Julia C is just Julia code and Julia C internal is also Julia code, we're actually not using juliac.gl directly. We just learned how the Julia compiles, and we built our own pipeline, mainly because we need to inject extra meta information and do some extra pre and post processing during our build steps. But I'm just encourage you to have a look, and you will understand this much better after you have a look, and this is really small code. So as a summary, we found that Julia is feasible for our use case. We really hope that our next machines would be using Julia in control. So far, it's going well, and we're looking forward for it. However, timing performance-wise, you can solve all the problems, and there's not so many of them. However, the user experience of using static call graph can be improved, waiting for it being improved, I hope would be improved. And of course, the third-party packages, it's much more difficult thing, because not all of them are static call graph compatible, and probably some of them will never be for various reasons. So you need to be aware of that and vigilant. If you want to deploy something, you need to start static call graph compatibility from the very beginning, not at the very end, like we did. And that's basically conclude our talk. One last sign is at 12 we have a meet and greet session here. I think somewhere there would be some food, so please join us if you have questions. We'll be happy to answer them right now, but if you have even more questions, please join us at 12. Thank you very much.
Thank you, Jorge and Curie. As they said, they are around at lunch. Please go and ask them questions. We can probably do one question right now while Bill comes and sets up. Yep.
Thanks for the great talk. I have one question. Do you ever have a use case where Julia does need to create an object that then needs to get passed back to the upper layer that's in C and C++? And if so, how do you handle that?
So the question is, do we have a use case if Julia need to create an object which is not passed?
Which is then passed back
Which
up.
Is then passed.
Yeah.
Oh, it's a great question. Yes, we do a lot, right? All the input is actually going through that road and all the output as well. But the answer would be really long. Watch my talk yesterday because I was talking exactly about that.
Thanks.
Thanks. A round of applause for Yuri and Jorge, please. And do see them at lunch if you have any more questions. Thank you. Do you need HDMI or? Oh, there's one here already. Just use that. Oh, okay. We're all set up. Have faith, have faith.
Well, maybe. Okay, we'll see how Linux comes out of suspend. Is it showing up? No. Yeah, displays, here we go.
It's not picking up the display at all.
It's not picking up the display.
No, try yours.
Yeah. Okay.
Take your time, take your time. No.
Okay. Do not disturb us. All right. Does it work? Keep changes, okay. Oh no, that's a very bad Is the resolution? No, I don't think so. Okay. All right.
Hi, welcome to our next session, which is Bill Burdick. Bill is an engineer at Julia Hub, and he will tell us about how to debug 1,000 programs at once. Over to you, Bill.
Hey, okay, so this is the block diagram. That's a little noisy, but hopefully it'll be better. So, as Avik said, I work at Julia Hub. I do some fun open source projects. My handle on GitHub is Zot. This is part of a little organization on GitHub that I made called Leisure Tools that I've been working on since 2011, I think. But this part is very much a work in progress. It's not quite ready for public use, but the goal is to get there very soon. So one reason for the talk is to gauge interest, to see if anyone is interested in this stuff. It lives in the Leisure Tools GitHub organization. The two main repositories are monitor.jl, which is the Julia part, and Leisure Command, which is a Go program that integrates a whole bunch of Go projects. The motivation is debugging remote Julia programs is difficult. Large numbers of jobs is even harder and time consuming because, analyze logs, change code, log more information, redeploy, wait, go to A. Dynamically changing logging as jobs run would be a lot better. And targeting and interacting with problematic jobs as they run would be even better. So I'm going to show a couple demos of this stuff. Is this? Yeah, it's visible. Okay. So the first one. Okay, so this shows a basic, as Julia starts up, it's going to populate this with another block of JSON, YAML. I'm showing it. So the idea of this is the root. This block has 3 properties in it, and they're tied to variables off of the main.engine object in Julia. And I have a rename here so that when a program hooks up to this, it'll send its own block it'll like publish a block, but with its own name so that it is namespaced, so that you can get blocks from a bunch of different programs in here and they're not all going to try to overwrite the same one. So if I change this, you can see that it changes to 3 right here as soon as I set it to 3, and I can change it. And then also, I can change values in the document here, and then send them through, and you can see it changed right there. So if I so that's like a kind of a basic idea of what this what you can do. You can monitor values in Julia in a bunch of different, potentially hook up to with a bunch of different programs. And I'll go over how this all hooks up in just a sec. I wanted to also show, oops. Another one that's a little more complicated. Well, actually, let me show the basic. Okay, so this is the basic document. I'm going to show this before I actually run it. So the idea is we're still monitoring like an engine, but we've got this special property in there that actually runs a method in Julia, check temperature. And we're going to define that method in the document here. Here's the check temperature method. And it just basically says if the temperature is 2600 or higher, then we're going to create a new monitoring block and publish it. Right, so when this starts out, it's not, this block here, which is marked quiet, is just going to be dead. It's not going to actually do anything, but it will install a monitor in Julia that's actually running, but it's not publishing any results. So oops. I'm just going to wait for it to warm up here. So it printed defining check temperature because I have this code block that runs code in the Julia programs that receive it. And now if I set temperature to 3000, it's going to publish the block here, the monitoring block on that engine. And this is because of this check temperature method that was automatically running. And so you can see it's 300 here, or 3000 here, so if I just change it to 3001, it updates right here. Okay, so this is a basic, and I realize I didn't provide a huge amount of context for this, but this is just the basic flow. I just have a feeling that I have too many slides, so I'm kind of trying to plow through. So in the first basic engine, the basic example I gave, I showed that each peer has its own namespace, and blocks can target different topics, which you can see in this block here. We've got the engine here is tagged with the peer ID, and then the block targets this particular peer so that other peers aren't going to respond to this monitor. And the next one was just like how you find and interact with bad engines. So there's custom diagnostic code that monitor.jl injected from the document I was using to drive this thing. So here's the block diagram again, and we can focus on, blocks flow between programs. So the idea is, like, what if Julia programs could receive and respond to commands like a botnet, but not for denial of service attacks, but for diagnostics. So the idea is you can publish and subscribe with multiple topics. You can have read-only behavior if you want. You can have write-only behavior. You can have targeted commands and data like I just showed. And you can have a monitoring facility that reports and changes Julia values. Currently, this uses Redis for publish and subscribe. It uses Redis streams, not Redis pub/sub, because Redis pub/sub is not reliable. It's just best effort, but streams are reliable. Streams also will stay around forever if you're not careful. So one of the things this does is like trims the streams. You could use other reliable pub subsystems like libp2p, which powers IPFS, or and something like MQ. Pluggable. The transports are all pluggable. The second half of the block diagram shows communication going on between Julia and the JSON data, the pub/sub data. So this is kind of sort of a new but existing UI approach, because it's something that I was using at another company that I made like 2006, I think, but we never like publicized how it worked. And it's similar to some modern UI approaches. So it's been in use for about 20 years. Uses two-way binding for variable objects to bind those variables to paths within Julia. And some people say two-way binding is bad, but if you do it right, you can power a platform for 20 years with it. Binding variable objects is a common UI pattern these days. Packages like Vue.js use it. And you see observables.js or .jl uses something like this, or can use it. So monitor.jl implements this in Julia, and it's fundamentally front-end agnostic, because if you model, if your UI just reflects your state, you can build an abstract like presentation layer in data in Julia that doesn't actually know whether it's, whether a progress bar is tied to a progress bar in a browser page, or whether it's tied to a dwarf digging a hole in a medieval village. It's however you want to represent these things is you can change it. So you can hook it up to a terminal UI like I was just showing. You can hook it up to a desktop UI, browser. I once demoed hooking it up to Quake. And like, how is this new? It's different from observer pattern mechanisms. I don't use the observer pattern like in observables.jl. The observer pattern comes from Smalltalk, a mechanism called change update, and the idea is that when you change a variable, it informs the system that there was a change, and I don't do that. So instead, I use polling, which seems like it could be slow, but because I'm using polling, the system doesn't need to be informed whenever something changes, because the polling mechanism can tell that. It's actually very fast because it doesn't do much work. Our app at my old company had 12,000 or more active variables at once for a map-based interface where like every map square was had X, Y, and the image URL and all that stuff, and like there were a lot of variables, and it was very fast. Getting a reachable value doesn't require any modification of your code, provided that value is reachable. Observed code doesn't normally need to include monitor.jl or even know about it. There are a few caveats that I'll talk about. Another project, Leisure, uses this type of a UI system in the browser, and it combines handlebars, templates with JSON data, and that fully drives the UI. The whole thing's templated and based on JSON data, even the outer shell of the, Leisure's like a notebook system. So, idea is that, if you actually want to build a UI with something like this, you could make one peer handle the UI and then help you manage state for all the other 1,000 things that you want to monitor. There's a next-gen Leisure that's in the works, but it's not ready for me to demo, unfortunately, but I'm going to show a tiny demo of old Leisure. So old Leisure had, so this is a little cramped. Maybe I can zoom out here. So here is some YAML data, and I can change the value of it, and you can see these views update automatically here. And the views themselves are defined here in the document itself, and and so the entire thing is reactive, and so these, so you can see, like, if I change this here, it changes the height. So you can do something like that, and this entire document here is defined with a big template that is based on JSON data and paths and stuff. So you can do some pretty elaborate UIs with just templates and YAML data, or JSON data. It doesn't care. It supports TOML too for people who hate YAML. So scaling, Redis is already highly scalable, and MQ and libp2p are also. But you could generate a lot of spam with this if you send out, you publish a monitoring block, and then suddenly you get 1,000 more blocks that just suddenly appear in your document and are updating. So there are ways you can limit which peers emit monitor updates. So like I showed earlier, you can have you can trigger publishing a monitoring block if you want. You can publish to other topics that maybe the document doesn't look at. You can have a reducer peer that listens to like heavy topics and summarizes them, and then publishes to like kind of a dashboard summary. And it could, the reducer peer could publish monitor blocks on any aberrant peers that are causing problems. Some caveats. Sometimes values need to be made accessible because you might want to go through a global or something to get to them in the path. You have to have a way to get to your values. That's something that could require a change to your code in order to support monitoring. Even though it doesn't know about monitor.jl, it's still, you might have to like provide probes into your code. Safe access to thread modified values can require extra steps, so there's some simple patterns for doing these things, but not all the, hopefully you wouldn't have to adapt your program to deal with this, but I mean, I think, if you're suffering from the edit, compile, deploy, log analysis cycle, I think it might be worth it to restructure concurrency a little bit if it can help with monitoring. So applications for this are diagnostics, also just general user interface, and even messaging between Julia programs. So if you got 5,000 programs, you could use this actually to communicate between them. Something I didn't cover is that there are 4 different types of blocks that this supports for communication. There's monitoring block that monitors values. There's a code block that evaluates code. There's a data block that just holds data, which can be useful for summaries and stuff. And then there's just a delete block that deletes old stuff. Future directions. I didn't talk about this, but there was a rename property at the very beginning that let's see, in my basic one. So I have this rename property here that says to use name. So it uses the name variable in main engine to name the block, so that when the block, when this monitor updates, it'll actually produce a new block with that name. So it might be nice to have like a template for that instead of just hard-coded like append the peer ID to the name. I'm planning to use this as a dev tool in Julia Hub as like in our private development stuff that we, for the platform team. And I need to test this at scale. I'm optimistic about that because I know Redis is very scalable. Yeah, so that's what I have to present. I know I talked really fast, but I was worried I wouldn't get through it. So does anyone have any questions?
Do I understand correctly that this only captures the current state of the program? And if yes, could it be extended by exposing an OpenTelemetry or Prometheus metrics endpoint so that those current states get collected every couple of seconds and passed on to some collector later and displayed like in a span of time?
So it publishes, when you have a monitor block, it publishes a new value every time, a new block every time anything that it's monitoring actually changes. So right now it doesn't publish duplicate blocks. So there's not any kind of like a, you could make a heartbeat block with just a counter in it to do, you know, and that's all just published to Redis stream. So telemetry could easily tap into that. Anyone else?
It's kind of continuation of the previous question. How you deal with the like frequently changed values?
Every monitoring block can have its own update period if you want. The default is 1/4 of a second because I've found that's what humans deal with pretty well. But if you want, you can increase the polling value for a particular block for a monitor. Other than that, I mean, if values are, if they're changing really, really frequently, you know, like hundreds of times a second, I don't think you'd want to publish hundreds of messages to Redis every second. So what you might want to do is probably gather up some information and batch it, maybe something like that. So you could do that. The monitoring code is pretty flexible, and so you could actually probably even extend it inside of your, like in your control document in a code block and stuff. So I think you might even be able to do it without actually, maybe without actually modifying the code you're monitoring.
Any more questions? Well, thank William for a wonderful presentation. And I think at 12 there's also an ASML meetup or lunch and stuff with you guys. Okay.
start?
Yes.
Okay. Hello. I'm Oscar. I'm from Julia Hub.
And I am Jose Giordano from UCL.
We are going to be talking about fixed-sized arrays. This is a new package that implements a array that has a runtime fixed size, but is still mutable. So in terms of why we did this, in 1.11, Jameson and I gave a talk on the new memory type. And memory is really good, but it's only a 1D collection. So sometimes you want matrices, sometimes you want higher dimensional arrays. And in math, arrays are a very common abstraction. And like in math, you'll have like an Rn array, and those do not change their size. And furthermore, mutability is really hard for compilers to reason about. So if you take the size of an array at 2 different points in time, the compiler needs to know that nothing in between changed the size, because in our Julia array, that size is changeable. And also because array is mutable in Julia so that you can change what size it is, that means that the actual array struct needs some allocations in addition to the memory.
Yeah, so we created this package which implements this fixed size array, which has the same memory layout as the standard array. So it's also a subtype of a dense array. But the difference with array is that it's immutable instead of being mutable. So the fields of this type are memory. Memory can actually be any backend. It's not just the memory type. It can also be like a GPU array if you want. And also the size, which like in the standard array, it's an n tuple. But again, since this is a field of a immutable struct, this is always constant for the compiler. And this is a comparison with other array types in the ecosystem. So there is a base.array, which has the size set at runtime. The data backend is memory, and it's both growable, and the elements can be mutated. Instead, the fixed size array that we created also has the memory, the size that can be set at runtime is backed by memory, but it's not growable, so you cannot change the size. But the elements can be changed. Also very popular are the MArray and SArray from staticarrays.jl, but they both have the size that has to be set at compile time. The data backend is a tuple instead of a memory. They are not growable, but the SArray also cannot mutate the elements.
So now to showcase some of the performance you can get out of this, for this like relatively simple example, we're benchmarking creating arrays versus fixed-sized arrays of different sizes and testing how long it takes to create the object and to fill it with random numbers, or fill it with zeros, in fact. And you can see that one very nice thing is that for a zero-sized fixed-sized array, there's no compile time, or no allocations for it. That will work better. Whereas for an array, you have the 32-byte header, which is just like the array struct that wraps a memory. And then you can see that even for bigger sizes, the amount of allocation is not much different because it's only a 32-byte array header either way, but you do have one extra allocation each time, and that takes a couple extra nanoseconds. It looks like on this computer, it was about 4 nanoseconds to allocate the array that you just saved by not allocating memory.
Another case is constant propagation on length. So we take the length of an array, and then we call a function which creates an array and asks for this length. And if you use vector, the compiler has to generate all the, first to create the memory, allocate the memory, and then does lots of work just to get to the size which you should know already. Instead, when you use fixed size array,
code.
Yes, it's just 3.
Yeah. And these types of optimizations won't come up always, but they are the sort of thing that when you're building packages, it just makes it easier to write the code that you mean, and then the compiler will figure out what to do with it a lot of the time. You can also see that for a simple reshape case, we managed to prove with fixed-sized arrays that if you reshape a length 3 array to size 2 by 2, we're able to show that this just throws an error, whereas you can see it's marked for a regular array. It's not consistent because the compiler doesn't know whether or not that will succeed or not. And also, if you have a length 4, we can prove that it doesn't throw an error, whereas for a regular array, the compiler still doesn't know whether or not reshaping a length 4 vector to a 2x2 matrix is valid.
Another example is, thanks also to some work by Oscar, to improve the escape analysis. We can define a function which allocates a vector of 250 elements, fills with random numbers, and then takes the sum using the fold function. If you use as input a base.vector, this needs to allocate 264 bytes. Instead, if you use a fixed size array, memory allocations are just completely removed. But one important thing why we use fold instead of sum is because the interprocedural escape analysis is not yet implemented. So this is maybe some work for the future. So if you use sum, in this case, the memory allocations will not be removed.
And also, the size 250 is specific because if you made this 260, it would be bigger than the size heuristic that we're willing to move to the stack, and therefore it doesn't work. So we also need to implement, most of this work was Gabriel and then me sitting along and handing him more LVM that was failing to optimize and him spending hours digging through, figuring out what went wrong. But for a lot of the very simple cases, we now already in I think this is 1.12?
1.13.
Oh yeah, this is 1.13. So it's not coming for a couple months yet, but we eventually can get rid of the allocations in many of the simple cases.
Another example is using enzyme to compute the gradient of a function. If you use memory, the base.vector in this case, and then try with a fixed size array, you see that there is a 2x almost boost of performance. This is not something that you should always expect, but this was like the first thing that I tried and said, oh, this is already 2x faster. So that was fun. But yeah, in some cases you will get not better performance, but still.
For example, right before this talk, I checked whether or not an ordinary FEQ solve was faster. It wasn't. It's like 20% slower. So I need to debug why that's happening. But yeah, for our conclusions, we think you should use this. It's a very new package, but it is also very simple. It's only about 100 lines of code. I think we have 100% test coverage. But the array interface in Julia is not very well defined, so you might find a case if you try something out where we do not implement part of this, so there's like the minimal array interface, which is getIndex, setIndex, and size. And if you implement that, everything works. But then it turns out there's about 20 or 30 other things that you need to implement if you want it to be as fast as array for all of the cases. So we should probably document what all of those are so that other people can write arrays that are as fast as base.array. But we think this package is mostly here, and let us know if you find a case where it's not.
Yep.
And then also we want to extend the compiler analyses. So Shuhei has written a very nice interprocedural escape analysis in Julia that we've had in the Julia repo for about 2 years and is not used currently. So a great hackathon project, if you're looking for one, is hooking this up. And then also, after you've hooked this up, we need to teach Julia about the Julia escape analysis about memory, because it just doesn't really know that memory exists, so it can't escape that at the Julia level. It's only at the LVM level. And just as a personal note, I for a long time have wished that Julia had a separate array type that was a multidimensional fixed-sized collection and a list type, which would be a single-dimensional growable collection. We obviously can't change this in Julia 1.0. We probably can't change this in Julia 2.0. It would be way too breaking, even if we ever made a 2.0, because people, it turns out, like using arrays. But yeah, this gives you that if you're willing to not have the array syntax. And I think we have time for one question, maybe?
Yep. If someone has a question.
Thanks for the talk. I use static arrays a lot
because of performance. It performs way better in many situations. We do have this kind of performance and use this, or is not possible?
No, these are not static arrays. So specifically, these still are memory backed, so they still will be heap allocated unless the compiler can do intra-procedural, not inter-procedural analysis to delete that. We have some ideas for how we might be able to make the compiler smarter here, but they are mostly not implemented yet.
Okay, thanks.
In your last example, I noticed you had fixed array around RAND. How did you prevent RAND from allocating before it got called by the fixed static array?
I think it did allocate an array, and then the compiler is smart enough in some very limited circumstances to remove it.
Hello. All right, folks. Let's get started. My name is Daniel Risk, and today I'm going to be talking to you right now about TidyRDB, and at 2:30 I'll talk to you guys about tidyr.jl. And so I'll just jump right in. A little bit about me. I'm currently an internal medicine resident at the University of Maryland. If you don't really understand that, I get it. Basically it means I work like 65 to 75 hours a week in the hospital doing inpatient medicine. I first got interested in coding when I took Karandeep Singh's class back in 2023, the keynote speaker, where I met him when I was in medical school. In any case, let's just jump right in. So TidyRDB converts tidyr code to SQL, okay? And so dataframes.jl, tidyr, they're both wonderful, tidyr data, excuse me, they're both wonderful kind of packages, but if you're working with data sets that are, 50 gigabytes of compressed data, or possibly that live on a database, you'll kind of run into some friction where you may have to use SQL. And not everybody knows how to write SQL, and so this package tries to address that. So you get one syntax for both data frames and databases. So to jump right in, let's say you have this patient's data frame and you want to see if you group it by people that are still alive, so that's the vital status, what is their mean expense in healthcare in the thousands, right? And this is, relatively straightforward. We're going to group by this kind of new variable we're making with this if else missing, and then we'll get the mean before arranging it, right? And what does the SQL look like for that, right? And so if you're familiar with SQL, this is pretty straightforward. It's just like a single kind of unit. You're going to select it, make your case when, and kind of, finish the necessary SQL to get that. And while that's really accessible, I think a lot of people, that may be a friction point for them, or if they're doing, much more complex data manipulations, that could be an issue. So this is what TidyRDB looks like, and you can see that it actually is exactly the same with the caveat here, the aside show query lets us see the query, and collect is executing it, so you're turning that SQL query, you're running it, and you're bringing it in as a data frame, so you can do further manipulation with it. Brief history, 2013-14, dbplyr came out, and that converts dplyr code or tidyr code to to SQL, excuse me. Python came out 2015, it's the same exact thing, inspired by dbplyr. Rust has a version, now we have one in Julia, among kind of a couple other packages. So how do we go from the tidyr syntax to SQL? So we have our database that's connected, great. And then next up, we have to get the metadata from the table, right? So we're not actually reading in the table here. All we're doing is grabbing the column names. DuckDB is our default backend. That means that we can use, paths, URLs, table names, kind of whatever you need. I tried to make it very broad. And then it's going to be executed and turned to SQL. So here we're seeing that second step right here. This is what the actual metadata looks like. It's a data frame. You have column names, types, and table names. And then over here you have the functions that underlie it, right? So for every single backend, there's a computing, a parsing function, that will basically traverse the abstract syntax tree using macro tools and kind of turn this tidier code into SQL. And then eventually, you kind of get this lazy query construction. This example here is like a little bit inorganic, but it's just kind of for the sake of this example, or for this presentation. But like if we have empty cars, we want to group it by cylinder and then kind of see across the MPG what's the mean, minimum, maximum, how many cars are in each group. Make some new categorical variable. We can kind of do all that, and you can see here what the query looks like. And then if you had a second query, again, it's inorganic. You make the second query, you're kind of doing it, you see the code, and then ultimately you can join these two queries together, and you can even join 6, 7, 8 queries together to make your final query, and then you collect it, right? So recently, for example, I had to write a function that worked on multiple tables on a database that was about 50 gigabytes of compressed text data, and it works, right? So I wanted to stress too that, I wanted to bring the best of SQL and tidier together. This is a chaotic slide, but so on this side right here, you're seeing all the top level macros we have, and then here's the other tidier kind of package functions that it supports, but also it comes out of the box with support for every SQL aggregate function and every SQL function that exists, as well as window function and user-defined functions, right? SQL's been around for 30 years, 40 years. They have excellent gems that I want to make sure were included. So this is an example using kind of the pre-existing kurtosis function. You can see that we can calculate the kurtosis in this table without doing any additional work because it recognizes that function. We can essentially push this to the aggregate function list that is kind of stored within it. And again, you can see the exact same thing. You can now do this in a mutate call, which is not aggregated. This is like the nuance of SQL that I want people to be able to avoid if they don't have the time to learn it. User-defined functions, here we're just making a quick binomial, or like we're gonna multiply them and then we'll kind of push that to DuckDB. You can do it, you multiply it, that's nice. So you can see here it's immediately recognized. And then if you change the function, now you have a plus b times a minus b, and you redo it again, it's already updated, okay? This is just a quick example of leveraging pre-existing SQL, not only functions, but SQL syntax. So for example, DuckDB is my favorite of all the SQL backends. They do excellent work. They have the ability to dot chain functions together. TidyDB supports that. So if you want to dot chain your functions like you would in DuckDB, you can still do that. Here we're going to take the model, and then we are going to make it uppercase. We're going to split it. We're going to aggregate it. We're going to concatenate it. It will do all of that. And then we want to select if it starts with model, and then there are your two columns. We're going to grab the first 6 rows. So that was kind of a whirlwind, but thank you to kind of Karandeep. He iterated with me and brainstormed, Vittori and Mose, and this guy on GitHub who's helped me find a lot of edge cases. Thank you. Questions? All right.
And also, I guess I gotta, how many minutes do we have until 50? This one? This one? This one? Oh, okay. Cool. Hi, so I'm here to tell you about making histograms using GPUs. So, preamble to making histograms on GPUs is that making histograms on CPUs is mostly solved. There's not only one, but maybe probably 2 or 3 packages that does fast CPU histogramming. The domain I come from wants histograms to also accumulate variances for each of the bins. That's why we have our own histograms, but overall, it's a solved problem. So the motivation for making GPU histograms is, it's cool and we want to write Julia for everything. If you want a slightly more practical motivation, it's that we want to avoid moving data back and forth between your host memories and device memories. For example, when previous simulation or data processing are done on GPU, and then you make maybe binned distributions, statistics, and then you move on to something else. You don't want to move a lot of data off the device just to make histograms. So if you don't know what histogramming is, here's how it works. You have input data, and then some weights, because your data points may be weighted, and you have bin edges, which defines the buckets in your histogram. And the output is an array, which is one less long than the bin edges, where they just records how high each of those bars are, if you want to visualize it. So all of the actual benchmarks I show in this talk have weights, because that's most realistic for our domain. So if you make histograms on CPU, right, it's fairly straightforward. You initialize your output bins, and then you start iterating over pairs of inputs and weights, and you just compute where does this input corresponds to, and you increment that entry in the output array by your weight. So the question is how to parallelize this onto the GPUs. So on CPUs, if you want to parallelize, it's fairly straightforward. You partition the data into n chunks, and then you just make n histograms, and you merge them. If you pick a sensible n, for example, the number of physical cores you have, it's usually very good, and you would hit your memory bound way before you use all of your cores. This approach does not work on GPU because, first of all, we don't want to launch n kernels, if you think that way. And second, it doesn't answer the question, how do you do one of them? Because you don't want to view one GPU core as a CPU core, because that's just not the most efficient way to use GPUs. So we need a new approach. So I'm going to tell you two approaches, and I'm going to call them naive and shared memory. So we're going to compare them, and the naive is essentially the naivest thing you can think of, which is you let each GPU thread take one data point, and you directly try to atomically write into an output. The shared memory approach does something smarter, where the thread accumulates to a local memory, local histogram before writing to the global one. I'll tell you about that a bit more. And how do we measure the performance of these approaches is we have two dimensions. One is how do they scale as the amount of data you have increases, and the other is how does it scale when the number of bins increases or decreases. So here's what a naive kernel looks like. Basically, as I was alluding to, you have input where you take each of them, each value in the input is taken by one thread, and then you directly compute the bin index, and you do atomic addition into the corresponding bin. So this is straightforward. However, you already, at the back of your mind probably, you have an expectation that this works well only when the log contention is low here. So we can look at how well it works. So this is a performance as the number of inputs. So this is if you scale the size of a data set. And we see that asymptotically, it's about 70 faster than one core. Okay, that's not too bad. But what happens when we change the number of bins? So here's how the speed slow down. So the higher means more slow down. As a function of number of your histogram bins. So you can see here, if we go back down to about 250 bins from 1,000, we have about 2.5 times slowdown, which is not negligible depending on what you're doing. But this is what you expect from a naive kernel, because we see this structure where the smaller bins, the smaller number of bins you have, the more log contention there would be. So this is expected. And the question is, can we do better? So the answer is yes. We utilize something called shared memory. So this is mostly universal on all the accelerators, where they are thread block local. So we basically make a copy of the output histogram, and then let all the threads write into that first before we do a ON update onto the final output bins, which lives on the VRAM. So here I have a footnote that says this is number of bins smaller than n, because this picture, if you take it literally, does not work if you have too many bins. But in the backup, I'll show you how that works. There's smaller loops going on. So what do we expect from this? This basically avoids the heaviest contention because we have breaking it up into each thread blocks. So this should alleviate most of the log contention we had before. And first of all, it's just straight up faster, even when you have sufficient number of pings. So compared to 70 times speed up before, now we're looking at a 300 speed up. So that's first pretty good. And now if we look at how does this scale as number of pings, we see that it does not have the catastrophic slowdown when you have exceedingly small number of pings. So that's also good, because usually I think people are more likely to have 100 bings than to have 10,000 bings, I think, other than in particle physics, where we have 1 million bings in multi-dimensions. But usually that's not where people worry about. So that's good. So the conclusion here is basically you should always use the shared memory approach. So here's a summary plot where I put the CPU, the GPU, and for reference, I pulled the CuPy implementation of histogram here. And you can see that CuPy has a much higher kernel launching overhead because of Python probably. But here we can see that the crossover happens about at 2K, which is not that large for a data set you want to make histograms of. So this is pretty promising if you launch kernel from Julia. This is quite small. And some caveat is that we haven't flushed out the interface yet. We haven't decided if we want to make GPU a parametric type of existing histograms, or do we want a new histogram type? So if you are a stakeholder using histograms, let me know. The implementation itself is, in theory, backend agnostic because we use kernel abstraction. However, in practices, we run into vendor-specific capability issues. For example, Apple's Metal just does not have atomic floating point addition on the shared memory. They have that for the global memory, but not shared memory. And with that, I'll take a question or two. Thank you.
Any questions?
Okay, thanks.
Yes, we have a few minutes until Stefan's talk.
Does it do multi-dimensional histograms?
Thanks for doing it.
And I have the great honor of introducing Stefan Karpinski, and no introductions necessary. Take it away.
All right, thank you. All right, so this talk is about the collision-resistant splittable RNG that we use since 1.11, I believe, for structured parallelism. And that's a bit of a word salad, but I'll be explaining a lot of this as we go. I have tentatively named it bifold because it needed a name. So a little bit of RNG algorithm history. This is before what we're really talking about in this talk, but we used to use Mersenne twistor from the beginning of time. DSFMT specifically which is like a slight variation. It's huge. It's a very big random number generator, and it's not especially good. So it's not good by modern standards. In 1.7, we switched to Zoshiro 256++, which is a good modern generator. It's also small. It's 32 bytes. And this enabled a very cool thing, which is that instead of having a single global shared RNG that you have to lock to use, and locking is bad, but also if you have multiple threads using it, who knows who got what value in what order? It sort of becomes unpredictable. So in 1.7, with the changing to Zoshiro, each task gets its own local RNG that lives in the task object. And since it's only 32 bytes, that's reasonable to do. And this gives us reproducible RNG sequences even when we're doing tasks and multi-threading. And it only depends on the seed and then the shape of the task tree, which is predictable. It works great. And this is what I'm showing is in 1.7 through 1.9, except for this. So all I did there is I inserted an async nothing in there, and it changes the second RNG value. First one's the same, second one it's like, oh, what? Okay, why does this happen? All right, so the reason this happens is when you fork a task, the child's RNG needs to be seeded as well. You can't just copy the parent RNG because then they'd both go off and produce the exact same values, and that's not what you want. So the child was seeded by sampling from the parent RNG, and of course that modifies the parent RNG's state. And I don't show it here, but you sample the RNG 4 times. So you can get the same value if you can go back here and instead of doing async nothing, you replace it with just sampling the RNG 4 times, then you do get the same values. But still, this is undesirable. Surely someone has worked on this. So we go to the literature and we see, yes, in fact, there are some very interesting papers on exactly this. A paper called it's not called .mix, but the algorithm is called .mix. It's got this longer title. Leiserson et al. Out of MIT for the Silk parallel runtime. And this has been a huge inspiration in general for Julia and the way its tasks work. So it's not too surprising that they have thought about this. So like, okay, great. These are very smart folks. They've thought about this. Hopefully they have a good solution. And then Guy Steele of Java fame also has a paper about introducing a thing called split mix, which is derived from .mix. All right, I'm going to explain a bit how these work. I'm going to have to fly through these slides because there's a lot. So .mix has this cool concept, the pedigree of vector of a task. And it's recursively defined. The root task has an empty pedigree vector. And if a parent has a pedigree vector with these coordinates, k1 through kd-1, its children are at depth d in the task tree. So the root is up at the top and you're down at level d. So these are all of that task's children. The kdth child has pedigree vector that's just, you stick the index kd at the end of the pedigree vector. And so it's not too hard to see that every task gets a unique pedigree. Of course, the problem is this takes an arbitrary amount of data. We don't have that in tasks, so we need to compress this down to something of fixed size somehow. The core idea for .mix is that you take this vector and you take a dot product of it with random weights. The same random weights for every time you do this, but randomly generated weights. And you can prove that the chance of collisions between those dot products between distinct tasks is only 1 out of 2 to the 64 if you're using a 64-bit dot product. And then you apply a bijective nonlinear finalizer based on murmur hash to like scramble the bits and make it nonlinear. And then that finalized value is used to seed your main RNG that you use for actually generating values that you want to use. Very cool idea, very cool paper. They do a lot of this stuff very explicitly, and it's kind of heavyweight, and they actually generate a a vector that they keep in memory, and it's shared of like randomly generated weights, 1,024 of them. So it's not super optimized, but it's like pretty clever. The details of the proof, we're gonna look at this a little bit because it turns out to be important later. So this, this is the definition. I write chi for the dot product. I don't know, I just made it up. It seemed like a good letter. It's the sum of the weights times the coordinates, and then it's done modulo p, where p is a prime. This is crucial. It's necessary for the proof of collision resistance, and it is annoying because it complicates the implementation quite a bit, because you can't just use native arithmetic. You have to simulate this modulo p arithmetic, and they use the largest prime that fits in 64 bits, which is this. Okay, so here's the proof, very quickly. Suppose you have two different tasks and they have the same chi value. So these two dot products are equal for two different tasks. So they're different, so they have some coordinate that's different. So we can let j be the coordinate of one of the coordinates where they differ. So this difference here, kj minus kj prime, is non-zero. And we have the weight times this non-zero thing is equal to some difference, delta. We don't actually care what delta is. It's the difference of all the rest of the terms, but it is arbitrary. We don't actually care what it is. But the key thing here is that because it's a prime modulus, you can invert that difference, and you get wj is equal to the inverse of that difference times delta. And there's only one wj value that satisfies this, and that means that the probability of this happening is very unlikely. There's only a 1 in p, and p is almost 2 to the 64. Cool proof, very nice. All right, so split mix is the next paper. Funny story, I read this paper and the authors spent a lot of time on an optimized version of dot mix, and I thought that was split mix. It is not. But in my defense, they spend 12 out of 20 pages working on this optimized version of dot mix, and then they basically take a left turn and they're like, you know what? Forget that, we're gonna do something completely different. Doesn't involve dot products. Like, it's a cool idea, but it's not. They claim that it's derived from dot mix, but I don't think so. It has like none of the same properties as dot mix, but it is a cool idea. So what split mix actually is this. It's a very, very simple core random number generator transition. It's just the state plus gamma, where gamma is some odd constant. And then you do this, it's like a murmur hash type of finalizer, and that's the output. So the basic idea is it's an RNG where the state update is very simple, and you put all of the complexity into the output function. It's a little bit of a suspicious construct, but it passes tests pretty well, so like, okay, it seems to be okay. So each task has two words of state. It has the main S, which is the main RNG state, and then gamma, which doesn't change in each task, but is different across tasks. And the cool idea they have here is that the flow is different than I expected. It's a clever idea. It's that as long as you can have a collision of the S part of two tasks, as long as the gammas are different, you still don't have a problem. So you basically get better collision resistance. And one of the cool things is this thing is designed so that you can generate random numbers from it and also fork it, which dot mix is designed to be an auxiliary RNG, not the main RNG, where split mix can do both. So that's cool. Now, do we want a thing that's an auxiliary RNG, or do we want something like split mix? So dot mix is explicitly meant to be just to seed your main RNG, whereas split mix can do both. But the problem is that if you use split mix that way, because of the way it works, it samples from itself to fork its children, and that's exactly what we're trying to avoid happening. So the way they use it, they seem okay with that. We don't want that, so we can't really use split mix the way it's intended. Here's my proof that we need an auxiliary RNG. Okay, our requirement is forking children must not change the main RNG state. But something has to change, because otherwise every child would be identical. So that something is the auxiliary state of that we have to add QED. Like we have to add something. There has to be at least a 64-bit word that we add. What if we used split mix as an auxiliary RNG and then just used it to seed a main RNG? That's an option. It's not great because then we've got these two words, not just one, because it's got the S part and the gamma part, and it's 128 bits, and that's more than we want to add. And also, we should use all of the auxiliary bits for splitting, not generation, because we're not going to use it for generation, so that's wasted space. Like, we don't need that. Okay, so .mix does this, and it has a cool collision proof, so let's try using .mix. That was my thought. Okay, so in the split mix paper, they spend all this time optimizing .mix. Basically what they do is they note that you can incrementally compute the dot product instead of recomputing the whole thing constantly. And what they end up doing is like, so each task has the cached dot product in it, and then when you fork, this is what you do. You increment the cached dot product by the weight for your current task depth, and then your child dot product is a copy of that cached dot product. They also improved a couple other things. They noticed that you can actually get away with a cheaper finalizer, and then they used a different prime modulus, which, you know, who cares? Okay, so I looked at the .mix stuff and the optimized version, and I was like, can we do this? Can we be even better? Partly this was laziness. I was like, I don't want to implement this prime arithmetic stuff. It's very annoying. And so much effort is put into both of these papers and trying to make it fast, and it's not helped by the fact that the JVM doesn't have unsigned integers. That makes everything more annoying. It would be really nice if we could just use native arithmetic. So back to the drawing board. Why do we need a prime modulus? Okay, it's for the proof of collision resistance so that the difference between these coordinates is guaranteed to have a multiplicative inverse. But why are the pedigree coordinates arbitrary integers in the first place? Because the task tree is n-ary, because you can spawn, you know, many children at each level. But this feels a little weird to me. Like, forking tasks is inherently binary. One task becomes two tasks. Like, can't we do this binary somehow? So I thought about that for a while, and I came up with a scheme where you assign IDs to your tasks instead of pedigrees, and then you can get a pedigree back out of it. But basically, the root node has ID 0. This is immutable. The ID of a node doesn't change, but you maintain a fork index. And this is not quite the task tree depth. It's not the same thing. But it's sort of, it's the thing that distinguishes the first child from the second child from the third child. But it keeps going. You keep it going through the children. Okay, so now here's the idea. The child ID is the parent ID plus 2 to the power of the parent index. So if you start with 0, the root node 0, its first child, you add 2 to the 1, or 2 to the 0, which is 1. So its first child has index 1. Its second child has index 2. Its third child has index 4. Its fourth child has index 8. The root node's children are all powers of 2. But then the first child's children are all going to be powers of 2 plus 1. So basically, you're being like very frivolous with the space of integers, but this is an arbitrary precision, so you have infinitely many integers. This is a way to give everybody a unique ID. And then you can turn the ID back into a pedigree vector because it's a bit vector. It's already a binary vector. Totally different tree shape, but this is a way to do it. Okay, so now we go back to the proof. The difference between coordinates is now either plus or minus 1. That always has an inverse. We don't need a prime modulus, we're done. Plus, there's no multiplication, so it simplifies the dot product. Now the dot product, you have the weights, but the difference between the coordinate is always either 1 or 0. Those are the only things. So either do or don't add a weight at a particular level. So this becomes the incremental dot product computation. It's super simple. Child dot product is parent dot product plus the weight at the fork index. That's it. Okay, random weights. .mix does this thing where they pre-generate an array of actually random weights. It's shared between all tasks, so it's not terrible. It's 8 kilobytes, but like, I don't know, it's just sort of 8 kilobytes of random data hanging around. And if the task tree gets deeper than 1024, they just recycle weights, which seems nuts. Can't we do something else, like use a PRNG to generate weights? Okay, so that's what I'm gonna do. I'm gonna use a PRNG. Okay, so this is the idea. Use a PRNG to generate random weights. The state size is 64 bits. The output size is also 64 bits. You can't have duplicates, but that's bad for a general RNG, but it's fine, and it's actually good in this case because you don't want duplicate weights. Arguably the best PRNG for this is this PCG 64 one. So that's what we'll use. And the basic design of that, it's a linear congruential generator core, and then a pretty strong nonlinear bijective output function. Okay, so this is what Julia 1.10 does. I'll call it .mix++. Generate weights with PCG. It adds one word of state to the task. And you accumulate a dot product into the main RNG state. That's like a clever change that I decided to do. I was like, instead of accumulating this dot product in the task state somewhere else, we've got these random bits. Why don't we just accumulate into there? And this is this is translated into Julia. It's implemented in C, but this is roughly the code for it. So you can see you get your weight from the previous auxiliary RNG state. You update the auxiliary RNG. You use the previous value state as the weight because it's better instruction level parallelism. It's a classic trick. Then this bit is the PCG output function, and then you just update the main RNG state with that weight. And so you're basically accumulating the dot product into the main RNG state. All right, so there's a little bit of a complication. Our main RNG actually has 4 64-bit registers, not one, because it's a 256-bit RNG. So what we do is we actually do 4 variations on that with different constants, and we accumulate 4 different independent dot products. And that has the benefit of making our collision resistance 1 over 2 to the, 1 and 2 to the 256, which is great. Like, that's incredible collision resistance. Win-win design, right? We avoid extra task state for the dot product accumulation, and we massively increase our collision resistance. Great. This is roughly what it looks like. So you get the weight, and you advance the auxiliary RNG, and then for each register of the Zoshiro 256, you do the thing that was on the previous slide. But you're indexing into an array of constants that are different in each one. And the weight, you perturb the weight by some random constant so that they don't all start out the same. They're kind of in different parts of the space before you apply the PCG finalizer. Okay, so this might be suspect, this business of accumulating into the main RNG. Is it okay? So the .mix paper actually suggests seeding the dot product with random initial values. So that is okay. We're effectively seeding with whatever happened to be in the main RNG. You can actually make the collision resistance proof work even when people are using the main RNG in between these things. And it mainly comes down to the fact that we don't care what that delta number is in the proof. It doesn't matter. So if it's got random crap added to it, the proof still works. You also need to know that the RNG advance of the main RNG is bijective. All right. Is this all good? It seems nice. It's a nice design. But unfortunately, in February 2024, Foobar IV2, who regulars on Discourse will be familiar with, I don't know how he looked at this and was like, oh, it's got this problem, but he did. He noticed that there's an observable linear relationship between outputs of the RNG when you spawn 4 tasks in a certain way, which I will explain. This is the code that I made some code to do this because his explanation was a little inscrutable. Basically, you spawn some tasks and generate random values in them and then fetch them. And then this relationship down at the bottom holds between those random numbers. This only produces 9 different values. It basically means this is approximately 0, except there's like 9 different values of 0. Okay, so why? Here's the task diagram. Okay, so we start with task 0, 0. It spawns a child, and we add the weight 1, and that is added to the state of task 0, 1, 0. Then we spawn a second child and add weight 2, and that's task 0, 1. And then task 1, 0 spawns its own child and adds weight 2. Okay, so now we've got this relationship, and therefore the dot product of 0, 1 plus the dot product of 1, 0 is equal to the dot product of 0, 0 plus the dot product of 1, 1. Oops. So what that means is that if they started out with the same main RNG state, then they each end up in they all end up in different states. So the collision doesn't happen, but if you add their states in this certain way, then that has a relationship that is observable. So that's not great. I mean, it's like, who would be doing this? I don't know. But like, we still don't want this to happen. So we didn't like patch it on 110. 110 still does this, but we got to fix it. This leads you to think, is the dot mix thing broken? Did they screw this up? The answer is no. So the core dot mix dot product computation does have this inherently. It's a linear dot product. It has this property. But these people are professionals, and they obviously knew this, and they applied a very strong output finalizer function to it. Me, being not a professional in this field at all, I was like, the weights are random. That seems good enough, right? And like, no, obviously not. This was dumb. I should have realized you need to have that finalizer, and I just didn't do it. So can we apply the finalizer and still do what we were doing? Unfortunately, no, because in order to apply the finalizer, you're accumulating the dot product in the main RNG. You want to apply the finalizer before perturbing the main RNG, but at that point you've already lost your dot product. You could like undo it and keep applying it, but that would be a lot of extra work. So we'd have to accumulate the dot product outside the main RNG, and now that increases every task size by the size of the accumulator. So we could add 1 extra word for accumulation to every task, 64 bits, but then we don't get our like nice 1 and 2 to the 256 collision property anymore, because we actually need 4 accumulators for that to work. That's a lot of stuff to add to every task. So this kind of sucks. Is this recoverable? Can we fix it somehow? So my thought was nonlinear dot products, of course. The dot product is inherently problematic for this. Could we do something that's nonlinear? What is the very bare minimum property that we need to make the collision proof work? And so, okay, let's generalize plus. So this is the plus, this is the version in 1.10. What if we replaced plus with any, so it turns out we can replace plus with any doubly bijective reducer function. Doesn't have to be commutative, doesn't have to be associative, doesn't have to be linear. And what you're accumulating then is no longer a dot product, it's a left fold by this beta reduction function over all the active weights of the task. We can generalize the proof. The proof still works. You have to tweak it a little bit, but basically the general idea, and this is a little hard to follow on so quickly, but suppose 2 different tasks of the same reduction value. We start at the same place. You can rewind through all the indices where the task IDs are the same until you hit one where they're different. And you can do that because it's by S mapping, its beta is bijective in its first coordinate. You can also rewind through matching, through corresponding uses of the main RNG between the 2 tasks, so that works. That's the other part of it. And then you end up in one of 2 situations. Basically, you have beta of the state and weight of the first task equals this other beta reduction, or it equals alpha of some state where alpha is the main RNG transition. And so either of those is basically this beta of a state times a weight is some arbitrary constant. And there's only one value of W that happens for. So this is the essential part of the collision resistance proof. It still works. And it's a probability of 1 in 2 to the, over 2 to the 64 for each register, so we get the whole 2 to the 256 collision resistance. So collisions are practically impossible, and the nice thing about this is now we don't have to worry about the, we don't have to worry, we can accumulate in the main register basically, because we have this nonlinear reduction function, so we don't have the linearity problem anymore. So this is it. This is bifold. This is what we do in 1.11 and greater. So it's very similar to before. You have this like LCG and you get the weight out, and then you get the state of the main RNG for the register. You XOR it with a random constant. You do this doubly bijective multiplication function. This could be anything really. This could be plus or times, but I like this one. And then you do the PCG finalizer with a per register multiplier, and then you save it back into the register. Some design notes. We use the LCG state directly as a weight rather than PCG 64. Good enough for this task. It's too weak for a general RNG, but we're just generating weights that we want them to be somewhat unpredictable. They don't have to be perfect. We XOR the common weight with a different constant per Zoshiro register, puts you in a different part of the space. It's helpful there that XOR doesn't commute with multiplication or addition, because those are things we do around it, so that is nice. This bimul function, it's a little like non-obvious that this is bijective in both arguments, but it is. And then we finalize with a per register variant of PCG. And then we accumulate into the main RNG. So that is, and again, that's unsafe for dot mix, but it's safe for bifold because of the nonlinear accumulator. All right, so we wanted a task forking not to affect the main RNG. We need some auxiliary state, but we want to minimize it. So possible algorithms, if we use split mix, we need 128 bits of extra state. If we use dot mix, we also need 128 bits of extra state if we use it in a way that's not broken. With bifold, we get away with only one extra word, and we get really good collision resistance. The fork operation is fast and simple. The dot product is actually not a dot product, and we can safely accumulate into the main RNG and interleave it with main RNG usage. We have a proof that that is fine, and the collision probability is like astronomically impossible. So there we go. That's it. Thank you.
Questions?
I know, it's a stunning amount of material preparing these slides. There was at one point where there were 58 slides in this deck, so I cut it down considerably.
Thank you. This was also a really fun community story. I'm curious, what background does someone need to obviously see the linear relationship? Like,
I don't know how you see it, obviously. We'd have to ask him. Obviously, I didn't see it. People have amazing minds. I do know he does a lot of crypto stuff, so maybe that helps. I'm not sure. There's another question in the back.
Kind of a weird question, but the LCG that was implemented for this, is that callable anywhere, or like can someone like import that or anything?
Oh, the LCG is like one line of code. Okay. It is literally multiply the state by a constant and add 1.
Okay, yeah, I was originally going to ask about the PCG, and then at the end it's just like, oh, you.
Oh, and then the PCG is another 3 lines of like bit twiddling to output it. It's like not worth having a function for. Just copy pasta it.
Thanks.
Yeah.
Anyone else? Or is everyone just blown away by that?
All right, thank you very much. Oh, there's one more question.
Just curious if you're also publishing it somewhere.
I would like to publish it. It is, of course, it was a lot of work putting this deck together, but now that I've done this, I think we're one step closer to a publication. I also clarified a lot of things for myself about how these other RNGs work. So yeah, I think a publication would be really great. But yes, that might take me a while to get it all together. And of course, you have to like run simulations and formalize proofs and stuff like that. So, all right, thank you.
Thank you. Oh, and I'd like to introduce Daniel Rizk and tidier.jl. Great, thank you. Take it away.
All right, so my name is Daniel again, and today I'll be talking about the Tidier ecosystem about 2 years after we first released it. Basically everything in this talk you can just do if you say using Tidier in your terminal. So, you know, about me, kind of the same faces. I'm still a doctor. I'm still here at JuliaCon, and my first experience was still learning code in 2023. All right. So before Karandeep's keynote back a couple days ago, he gave this talk at JuliaCon in 2023 doing some myth busting around like the tidyverse, right? And at that time, we were introducing it into Julia, and the first thing is that tidyverse is not standard R, and I think that's a common misconception. It's actually more of a philosophy around tabular data wrangling, manipulation, and visualization, right? To the point now where it exists in multiple languages, Python, R, JavaScript, Julia, like really you name it, somebody's tried it. And so at that time, it was really just tidier data, and that was just kind of a manipulation that was based on dataframes.jl. And it's now grown to be more than 10 packages, and it's pretty comprehensive. It lets you work with data frames as well as you know, to do transformations, reshaping, visualization, databases, web scraping. Really, it's pretty all-encompassing. And so just to kind of take a step back here and kind of talk about my own path into coding, right? In 2023, I first learned how to work with tabular data using like dbplyr and dplyr and R in Karandeep's class. And I remember when I learned that, I was like, wow, I don't ever want to use Excel again. That is a horrible place to live. And so I really enjoyed that experience. And then, you know, a couple of weeks later, whatever, I had another class where I had to use Python to do some natural language processing. And I found at that point, I didn't know about these packages, and I was trying to use pandas to do my data wrangling, and it was a horrible experience. Okay, like I'm sorry to say, but it made me never want to use Python, and there was just like a lot of friction there, especially around packages. And then, you know, moving forward, you know, now we have tidier data and tidier DB and tidier plots, right? And so I think that really what is, I think, really neat and important here is that like a shared philosophy reduces activation energy, right? So if you know how to wrangle your data in R, you can now do it in Python, you can do it in Julia, and vice versa, right? So folks who may be interested in trying Julia can now kind of take out some of the friction and kind of resistance that they may interact with to get their data into the shape that they actually need, right? Because when it comes down to it, a lot of data analysis is like, it's a lot of cleaning data. So what are the core principles of Tidier? The first thing is that it's a comprehensive data analysis meta package, right? We want you to be able to, you know, jump into Tidier and have everything you need included, right? So it's batteries included. We want chainable, readable pipelines via chains and .jl, which is a kind of a great underlying package. And we kind of default to using a high level of abstraction that's done by leveraging macros. And then lastly, again, it's just leveraging this kind of shared philosophy across multiple languages. So to just jump right into some of the packages, Tidier files, it really just builds on a lot of the excellent work that people in the Julia community have done across, you know, I mean, CSV.jl, Arrow, JSON, like you name it, folks have built it and it works. And all we really did here was just harmonize the keywords across all these different file types. So that way, it's just kind of like one step of friction to get out of the way. And you can use the read file, write file, and auto-detect the backend needed, or the function needed, and dispatch it for you. So now to jump into tidier data. So this is built on the excellent dataframes.jl package, and it uses macros so you can kind of use bare column names, which I think is something that's a little bit atypical in Julia, but it is used kind of throughout various places. It also leverages auto-vectorization, and I'll kind of touch on that and why it's actually so important. And it's all encompassing, right? You can join, pivot, meaning like go to wide from long to wide. You can aggregate, nest or unnest your data. And really, I know this is kind of, again, chaotic, but these are all the top-level macros it supports. So we want to make sure that when users are using it, they don't actually have to fall back on dataframes.jl if they don't need to. And of course you can, right? You can throw in a dataframes.jl function in the middle of your chain. It's actually really nicely, easily integrated, right? And then we also have all these kind of helper functions that entide your data as well. So this is just an example. In this particular example, I used pipes to compare the data frames to a tied your data chain. But you can see that in the difference, right? That the anonymous functions are kind of happening behind the scenes. And so that's one thing that's happening, right? The vectorization is, again, it's implied within a lot of the functions. And, it's just a little bit more, I think, readable or accessible to people who are maybe less familiar with coding or less familiar with Julia. And, it's just can kind of take away some of that cognitive burden, right? So if you come back to your code later after doing some sort of data analysis, you can kind of jump right back in and figure out, oh, I was doing X, Y, or Z. And here you'll just notice that mean is we don't need to tell it not to vectorize it, it knows not to. So I think my understanding about the Julia community is we love benchmarks. And so just briefly on the benchmarks, looking at tidier data compared to dataframes.jl on like 9.4 million rows, give or take, there really isn't a substantial difference. I think the only place that we really see a difference is in this group by and then mutate when you're kind of putting in 2 new variables or more, right? But outside of that, there really isn't any sort of penalty that's significant, right? This is time in milliseconds, and I personally, I work enough at work that I can sacrifice 10 milliseconds, and that's okay. But it is something that we hope to address moving forward. And I think that logging is actually one of the coolest aspects of this entire package. So Randy Boys kind of kicked this off, and this was always something we wanted to do. This is based on the tidy log package in R. So when you're working with a data set, it's really important to have a foundational understanding of the content of that data set, right? You can't just kind of clean it without understanding it, right? So in this example, we'll use the movies data set. And the first thing we're going to do is we're going to filter by year, right? And of course, we've set tidier set data set to true, right? And you can see this filter right here has removed 85% of your data frame, okay? And that now you only have 8,700 rows remaining. That is a significant portion. If you didn't know that moving into your data while you're working with it, you can end up kind of eliminating large swaths of data or kind of having, for lack of a better word, silent errors occur, right? And so again, this is an option that you have, right? If you're mutating in a new variable, it's going to tell you how many unique values are in it and then what % of that column is going to be missing. If you're summarizing it, it's going to tell you, how many rows. So it's just really, it adds a lot of color to the process of data manipulation and cleaning and wrangling, which I think is important in good analysis. Now, as far as the auto-vectorization and why it's important. So tidier data uses a lookup table to decide what to vectorize and what not to vectorize. And the reason this matters is because it lets us, as we'll kind of talked about before, I'll touch on it again briefly, it lets us go to SQL, right? So if you, for example, have mean here and you wrap it as a new mean, new function, right? And you call it as a new column D, you'll see that it's wrong, right? Because that's just not how it should function. But if you want to, you can actually choose not to vectorize it by putting a tilde in front of the function. And then tidier data will know, okay, this function should not be vectorized. And on top of that, we wanted to make sure that users maintain full control. So if you like to use dot broadcasting and you want to see where your dots are, you can add all those to your data and it will still work, right? It's not going to be an issue. So as we talked about briefly, maybe there's a couple new faces in the room. If you don't have a data frame, it's not a problem, right? Once you know tidier data and you can work on data frames like that, you can now work on databases with no issue. And again, this is, I think, a kind of relevant picture because we see that the syntax order and the semantical order for SQL are not the same. And it creates tension, right? If you've done your initial kind of exploration on a small subset of your data, now you need to move to SQL because the bulk of your data lives on a database. You have to essentially start from scratch if you don't know SQL, or kind of work in a whole new way, right? So again, what is TidyRDB doing? It's converting your tidyr data code to SQL. This is not one of those like gotcha spot the difference pictures. I'll make it big so you can see it. It's really just collect. Outside of that, the code is identical, except for like reading in the data, obviously, or kind of getting it ready. But everything else, you can see is there is no difference. And I think this is one of the really beautiful things here, because once you can do one, you can do the other. And that can save people a lot of time as well. And so, to summarize again, it's lazily writing the query, right? So in this example, you might notice that there's a lot of common table expressions, and this was how I had to figure out a way to safely move from tidyr data code to tidyrdb. And I wrote about 100 tests with multiple step transformations comparing the tidyr data to tidyrdb to make sure that there was no difference in outcomes, right? And so they are all the same. And again, it supports 12 backends. I want to stress too that DuckDB is the only backend that comes within the package. The rest are all extensions to try and lighten up the overall dependency load. And then supports all the native functions, aggregate function, user-defined functions, and more. In this example here, we have the fish data set. Just kind of a toy data, but this is in the long format, right? So sometimes if you want to do kind of easier visualization, you have to go from long to wide. We can use pivot wider for that, and pivot wider we do, right? So here we're reading in the data. We can see we do pivot wider, names from station, values from value, fill, missing. And this is the tidyr data code. And then down here, we have the tidyrdb code. And again, there's no difference between the two except for adding this collect. The one caveat here I'll say is that pivoting is actually an inherently eager process where you need to know the distinct values for the column, right? And so what I actually did here is it's optional. If you already know what the values are, you can give it a dict and it will not do any kind of additional execution. If you don't know, it'll just run a simple query behind the scenes, pull the distinct values for the column it needs, and then it'll write that SQL query for you, right? But in essence, you have like the entirety of tidyr data at your disposal in tidyrdb, plus all your SQL functions. Moving into tidyr plots, this is Randy Boyes has done a lot of excellent work here. I should say Current Deep really did the incredible parsing that's in tidyr data, and so I want to shout them both out. So tidyr plots is combining the power of Maki with ggplot. Okay, so ggplot is kind of a very famous, well-known, well-loved, well-used package in R for data visualization. It's been re-implemented across the board, and it works in building layers, which we'll show in a second. Okay, and Randy gave a talk I think yesterday as well. So it has a lot of geom supported already. You can do kind of bar-like plots, scatter plots, lines, error distributions. You have all these different scales available to you. You can easily leverage color schemes.jl palettes. And this is as a quick sidestep here. If you're interested in contributing, I think geoms are a really nice way to kind of dip your toes in. Randy has an open issue on the tidyr plots GitHub that you can jump into. It's a nice self-contained project, and we would love some new contributors as well. But let's just go into it, right? So we have the empty cars data set. We want to make a scatter plot looking at horsepower against miles per gallon. We're going to start our chain, and you don't have to do that if you don't want to, but the chain will be relevant later. So you have your ggplot, and then your AES macro is to establish the aesthetics, and these will kind of go for all of your subsequent geoms, but you can also do individual geoms by just putting that AES within it, right? We want X to be HP, we want Y to be MPG, and then we want this to be a point, or like a scatter plot. And then for our labs, we want title to be equal to fuel economy, Y is MPG, X is this, and then have a minimal theme. Okay, but what if we wanted to add like a smooth linear regression line to it? We can do that. The only thing we're going to add here is just plus sign, geom smooth, method equals LM. And then now, right, we now have our line you can see, and it's right there, and it looks great. Okay, but I know there's a lot of folks here who don't use miles, and I wish that we used the metric system in America too. So what if we wanted to convert MPG to kilos per liter? You can do that, right? The AES macro uses tidier data under the hood, so the anonymous functions all happen behind the scene. MPG times 1.61 divided by 3.78. Now we have kilometers per liter. We change it in the Y title, and there it is, right? So now you can see the graph has changed. And if you really like anonymous functions, you can still use the AES function. Randy has functionality for both, and you can write your anonymous functions that way. All right, and the reason I've been using chain in these examples, even though I didn't need to, you could have just started with ggplot, empty cars, and go from there, is because one of the things that's really nice is when you're doing data exploration, you may need to make changes, and you're kind of making changes to your graph, making changes to the actual wrangling that you're doing. And the nice thing is when you say using tidier, you can do that all at once, right? So in this example, we'll use the flights data set, and we're going to clean the names. We're going to mutate in, you know, we're going to floor the hour per day, and then we're going to get the days of the week. And we'll kind of continue on to we use cat relevel, which is from tidier cats, just to kind of like make sure the order of the categorical variables are all in the same. And then finally, we'll group by, summarize, and then get to our plot here. And we have a nice tile plot that shows when are flights most likely to be canceled. And again, like, I think what's really nice here is you have this really nice interplay between tidier data and ggplot, right? And this is also, I mean, this applies to TidyRDB as well, right? If you use TidyRDB to do your data manipulation, then you collect it, you can just jump right into a plot, or plotting from that same code, right? And the only other thing I forgot to mention is that in TidyRDB, or tidier data, CurrentDeep wrote some really cool metaprogramming under the hood, so that way these are dispatched all the same. Like the macros actually know which one that needs to be used. You don't need to do any additional decorating when you're using tidier data, or tidier, excuse me. So, we continue. Randy, he took it one step further. Machi's it's an excellent place to plot as well, and they have a lot of cool functionality. So if there's a particular geom that hasn't been implemented, you can implement it yourself, right? So here he shows an example. You want to make a rain clouds plot that already exists. You can do that, and just with this one line of code, you've now created your own geom, and then there it is. You can now use it and immediately jump into using additional features from Machi. He also made it so that it works nicely with plots, right? So here we have an example where if you want to kind of leverage this idea of patchwork as well as plot layouts, you can do all of that. Tidier dates, I'm just going to be brief on this one. This really just leverages dates.jl plus some kind of custom parsing under the hood. If you all have ever worked with survey data, sometimes people will leave the date box as a free entry text, and then it's a nightmare to clean that, and you wonder, why would you do that to me? And Tidier Dates hopes to kind of address that on some level, right? So it will basically try and figure out what the most likely dates.jl format it is, and if it can't figure it out, it has a custom parser on the back end to actually clean that up, right? So like if somebody had written December 3 RD, 2020, it'll know how to clean that up and get that. I did some benchmarking as well on this, which I don't have here, but it really is, there's no significant penalty for it as well, right? So there's not a sacrifice here. Tidier Vest. This was Jose Diaz. I think he's out in Denmark. He made this really cool web scraping package that's based on the RVest R package, okay? So this is an example where we are taking the highest grossing films, and then we're going to look at the HTML elements, and then we're going to make it a table. And again, this is an example where like, oh, hey, I know I need to get this turned into a data frame. You can do all of that kind of within Tidier, and it's like in a nice, neat, easy to kind of read and follow way. And I think that most of these movies are mid. This is another example that Jose sent me to include. He actually made a website, he made a website that leveraged Tidier Vest. So he wanted to take the Steam games website and like make it so that way you could have another website that has a list of all these games. And kind of this is an excerpt from his code base, and you can see that they're actually, scroll and get was a custom one he wrote, but HTML elements and like the parse HTML, these were things he wrote so that way, these are both from Tidier Vest, excuse me, but this he wrote. So that way you would kind of scroll down and would click, and then now he has a website that has basically done the web scraping for him and is making like lists based on countries. It's pretty cool. Where you can check it out. Tidier iteration. This was by Vituri da Silva. He's out in Brazil. I'm grateful for his work as well. This is based on the per package in R, which albeit I'm a little bit less familiar with, but it is very well loved and really powerful for like applying functions across different objects. And so now it brings that to Julia, so you can kind of easily do arrays, dicts, and more. And so you can see here he's flattening nested dictionaries, and there's another one that's not defined up here, but it's kind of taking out maybe some of the pain points as well. Here's another example. There's a function there that's called possibly, where instead of a chain or a pipeline failing, it will kind of have a predetermined value it puts in for those failed ones. Tidier text. This is a package I wrote kind of as a challenge. And this is based on the tidy text package in R, which is used for text mining, right? Sometimes when you're doing text mining, like let's say you have a whole bunch of different books or like, I don't know, news articles, and you want to clean them up and you need to get your data into like a tidy format. This will tokenize your data and make it into a tidy format. And so that you can more easily plot it, right? So we're seeing here, like leadership laboratory, you have your ID, it's made to lower, and there's just like that, so you can kind of do whatever graphing you need to do. A couple of honorable mentions, tidier cats. This is just for working with categorical variables, particularly when plotting. Sometimes you need to lump your categories into new categories, you want to relevel them, you want to reverse the order. There's various reasons that you'd want to do that while you're plotting, and this is just trying to simplify that and kind of take out some of that cognitive burden associated with remembering things. And tidier strings is a convenience function for working with strings. So what's on the horizon? Tidier 2.0 is hopefully coming out soon, in the distant future when we get tidier DB plots and data to their 1.0 releases. Current Deep has been putting in a lot of cool work to tidier course to familiarize folks with the kind of thinking that goes into it and some of the gems that we have tucked away in these packages. And then we're translating, hopefully soon, a well-known epidemiology handbook from R to Julia as, again, just like another point of entry for folks. So with that, thank you to all these different people. There's been a lot of contributors, and we're grateful for all their work. I won't name them all. You can find us in the Slack channel, or you can go follow us on Blue Sky and become a contributor. Thank you.
Okay, now, let's see, any questions for Daniel? Oh, okay.
Thank you for the talk. From an outsider view, tidier and Julia just appeared out of nowhere at some point. Do you have some elevator pitch for the story of how this happened? That's a lot of people, and the Julia community is not that large.
Yeah, so this kind of, so Current Deep is the one who started it all off. He's the one, the guy who gave this speech a couple days ago, or like the keynote talk. And basically, he's always really liked R, and he's used it a lot. And he was trying to find a new language, and I don't think he loves Python. And so I think it was December 2022. He read the entirety of Bogomil's book, Data Frames, the introduction for data analysis. And he was like, "Wow, this is awesome." And then he started playing around with it, writing tidier data, and just to see can we kind of bring this to Julia, because Julia is a lovely language to write in. And then shortly thereafter, I think Randy kind of connected with him and wanted to work on tidier plots. And at that point, I was a student waiting for some data to come through. And I was just like, I wonder what I can contribute to. And then the next thing, we kind of just rapidly, it's kind of snowballed. And so our hope is really that we can just give people a new point of entry for Julia, because I think that there's a lot of people out there who would really like the language. I know for me, when I've written it, it's much nicer to read than both R and Python. And I think that there's a lot of people who might be more interested in trying things out if they know they don't have to learn a whole new way to wrangle data.
Hi, thanks for the talk. Every time I install data frames, I install data frames meta because it's way easier, and it seems something related to this. Can you please provide some small comparison about the two approaches in tidier data and in data frame meta. And the second question is, this repository, tidier data, depends only on Julia's 100% Julia code, or it has some external dependency of other libraries?
Everything is written 100% in Julia. Obviously, we use the dataframes.jl package for that, but everything is 100% Julia. So thank you for reminding me to say that. I totally forgot. As far as the dataframes meta, I think when Karndeep started, he took inspiration from it, but there was some challenges to it, right? Like, for example, I think that if you want to have it use a vectorized macro, you have to use like R transform, for example, versus like the transform macro. And then on top of that, you're still using symbols, I'm pretty sure, for the column names, and you're still having to use anonymous functions. So early on, our goal was really to stay as true to our syntax as possible, which meant bare columns and no anonymous functions. And that was something that was not actually possible with dataframes meta as well.
I'm starting to see the need to store tables in some maybe non-traditional formats. For example, HF5 or JLD in the Julia.io organization, or maybe things like SAR. I was wondering, where's the best place to kind of start making these connections to these other kind of binary formats?
That's a question I think Karndeep would be able to answer better than me. I'm less familiar with those file formats. I'll just be upfront about that. I think that, is there a tables.jl interface for those or no?
I don't think so.
Okay.
So and on one hand, I'm tempted to just start it by myself and kind of figure out how to do the mapping there. I'm also trying to be conscious of like what might exist beforehand, but this is just something that I've started to see recently because I'm using these for like n-dimensional or chunked data. But then people want to put tables in these formats for some reason. So.
Yeah, I think that probably the best place, or like the ideal, would be if there's a tables.jl interface. I know that was actually one of the pain points with TidyRDB, right, is that there wasn't a tables.jl interface for SQL. So I had to like custom write everything, and I ended up just abandoning trying to write the tables interface because there's like SQL complexity and nuance that I couldn't capture as fast as I wanted to. So maybe that would be the first place to start. I think that would be it, yeah. Sorry if that's not satisfying. Yeah.
Anybody else? Oh, I have a question myself. You have a medical background in this.
Yeah.
I spent a lot of time with databases that are actually from Epic. Actually implemented a lot of the database that they use, Cache or Iris.
Oh, incredible.
Database. But I didn't see any connections to that, the Cache or Iris database. Or is that something that maybe someone could come up with that might be useful?
What are those written? You use SQL on those?
Well, most of the EHR data in the U.S. is stored in those databases.
Okay.
That Epic Air uses.
Right, because I know for us, the Epic databases, I think they use SQL as well. Like we're at University of Maryland. I'm not totally sure. But I think that, how about this? I will learn about that, and I'll open an issue.
Well,
yeah.
Maybe if you're hackathon tomorrow, maybe, or we can talk about that.
Sounds good, thank you.
Thank you so much. Minutes, and then Stefan's coming back at 3.
thanks for doing it.
Are we ready? Okay, I would like to introduce Stefan Karpinski again. No introductions really necessary. Talking about Resolver. Should be very interesting.
All right, thank you. All right, my third talk of the day, so I'm happy to get the third one done. I'm Stefan Karpinski. I am the Chief Product Officer at JuliaHub. You know, check out our wares at juliahub.com. I'm talking about something mostly unrelated to work. It's called resolver.jl. It's been a long-running project of mine. And it is a new SAT-based resolver for Julia package. You know, it's going to end up in the package manager eventually, but currently it's in a separate repo and hasn't been integrated. So just some background. What is package version resolution? What's the problem? Why is it interesting? The setup is there are packages. Each package has versions. Each version depends on a set of other packages. And there's some subset of pairs of versions of different packages that are incompatible with each other. And there's, you know, this is basically the same problem in most package ecosystems. Go has an interesting way of avoiding this problem being hard, but it seems not ideal in my opinion, but everybody else basically faces this problem. Actually, just briefly, the way Go avoids the issue is that they just don't allow things being incompatible. They just don't have a way to express that, and that does actually make this problem easy. A valid solution means that every dependency is satisfied. You know, you can't depend on something and you didn't pick a version of it. And there's no incompatible pairs of versions that you picked. So you need to pick, you know, a version of every package in such a way that this is satisfied. And it satisfies a set of requirements when there's a version for each required package. Okay, so the decision problem version of this, if you're in, you know, talking about complexity theory, is there a valid solution to this? And this problem of package version resolution is actually somewhat well known to be NP complete. This is a hard problem. And in particular, what it means that it's NP complete is that if you have a thing that solves this problem, you can solve SAT problems, which are also hard. So you might want to use a SAT solver, because if you don't, you're going to end up badly implementing a buggy, slow SAT solver, in effect. Of course, we don't just want any solution. We don't want to just know, is there a solution? That would be very useful. It's like, is there a solution to this? Yes, there is, but I won't tell you what it is. No, you want a solution, and in particular, you want an optimal solution in the sense that you want the latest and greatest of every package to the extent possible. Sometimes conflicts make it impossible to have the latest and greatest versions of 2 packages at the same time, but you'd like to do as well as you can. Yes, that was this slide. Okay, so, but it requires some notion of what makes one solution better than another. And we start by putting a preference ordering on the versions of each package. And the standard version preference order is that newer versions, bigger version numbers are better, right? We want the latest version of each thing. But sometimes you may actually want to do a different order for various reasons, and we'll get to that. Extending the order on versions to orders on solutions is actually a little subtler and more tricky than expected, but that is also something we'll get to. So what we do now, the current package.jl includes a version resolver. It uses a thing called belief propagation. It's heuristic. It does not always find solutions that exist, and if it finds one, it might not necessarily be optimal. But it works remarkably well. It's very good. And we've had it for like over a decade. And Carlo Baldassi implemented it, and occasionally, if we put up the bat signal for Carlo if there's something wrong with the resolver, and he shows up and he will still fix things, even though I don't think he's doing any other Julia stuff these days. And we're very, very grateful for that, for the decade of service maintaining this thing. Okay, so one of the big issues with the existing resolver is that the structure and meaning of version numbers is deeply baked into it. And that sounds fine, right? We're resolving versions. Why is that a problem? Well, the issue is that it bakes in this idea that higher version numbers are better. It also can't support pre-release versions, and it can't support build versions, so we have build numbers. So we have these this horrible hacky ways to sort of work around that. But it'd be nice if we didn't have to do that. So why would newer not be better? One thing is you might want to fix versions. So you might want to be like, look, for example, let's say you're adding a package. By default, what happens is that we add that as a requirement, and then we go through and re-resolve everything, and it changes everything. That used to be how it originally worked by default. That's kind of annoying, because you're like, look, I just added this thing. Why are you changing the version of every single thing that I'm using? Can you just leave them alone? Okay, so what we do right now is we go through and try fixing them. So we actually pin them and say, you're only allowed to use the version that's in this manifest, and then if that can't be resolved, I think we just give up and do the thing where we change everything. But it would be really nice if you could just say, hey, could you just prefer the current version, but otherwise, if you can't prefer the current version, feel free to, if you have to, go ahead and change it. Because then we wouldn't have to do this pinning hack, and then, if something can, it's all or nothing right now. It's either you pin everything, or then you're like, oh, you know what, we couldn't pin everything, we give up, we'll just change everything. It'd be nice if you could, maybe, if it's necessary to change this one thing, just change that one thing and leave everything else alone. Another thing is you might want to avoid downloads, so you could prefer versions that you already have downloaded and installed, and that would avoid downloading new versions if you have one that you could use. There's also this concept of downgrade resolution. So instead of taking the latest and greatest of everything, take the oldest and shittiest of everything. And it's useful for testing lower compat bounds, because people have these upper compat bounds, and you kind of know those are right because you test them. But the lower compat bounds, are they right? Who knows? We don't know. We don't test them. Some people do test them. So Chris Rakakis has been very good about testing lower compat bounds. And he had a hacked version of this, and he just changed it to use my script that uses this resolver code. So lower compat bounds don't sound very important. Why do we care? The reason you actually care about lower compat bounds being correct is because what will happen is everybody's tootling along and everything's fine until some incompatibility gets introduced in the ecosystem. And then what will happen is the resolver will say, oh, hey, I can't use these two new versions together, but here's this ancient version that claims to be compatible with everything. I'll just use that. And it doesn't work. It's a lie. It does not actually work with everything, but now the resolver will try to use it and everything breaks. So if the lower compat bounds are actually correct, then you can trust them, and you can, if the resolver decides it can, says it can use something, it actually will work. So that's why we care about those. Okay, so here's what we do now. This is the new approach. First of all, architect the thing to avoid coupling details of packages, versions, and registries. Resolver.jl doesn't know about these, even as types. It doesn't mention them. It actually uses parametric types everywhere, and the type of package is just capital P. The type of version number is just capital V, and there's a couple other things that we need to have, but it truly knows nothing about these types. And the only requirement is, I think, packages have to be sortable, which we could probably eliminate that requirement, and then you're given an ordering on versions, so those don't even have to be sortable. We use an actual SAT solver. We're not gonna make that mistake. It's a one called PicoSat, and it has some nice features it's very small, very compact, pretty fast, not state of the art, but good. And it has some nice features that are very useful. SAT solvers are very sensitive to problem size. So one of the key strategies here is do a bunch of pre-processing to make it so that the SAT problem that you construct is as small as possible. Don't just like make the biggest possible SAT problem you can and hope that the solver will not fall over, because it does if you make a big enough problem. All right. So some emergent features that kind of come out of this is, since it doesn't know about version numbers, you can give it an arbitrary preference ordering, because it's got no structure baked in. You just tell it, like, this is the order I prefer these things in. It generates optimal solutions based on a lexicographical ordering you give it of packages. It's like a priority order of the packages. And it gives you the lexicographically first optimal solution first, and then it can iterate more if you want more solutions for some reason, which you might want for compat bounds checking again. It has this semi-internal SAT problem API where you can basically say, look, for this resolver with these, with this registry, these registries and these requirements, give me a SAT problem. That API is generally useful. Like, you don't have to do resolution, you can do other things with it. Okay, so what is a SAT problem? It has a bunch of variables, and it has a number of clauses that reference those variables, and all of the clauses have to be satisfied. And in each clause is a disjunction of variables or negated variables. So obviously, if you have A and not A, and it's or, that's always satisfiable. That's a trivial clause. You could just delete it. It doesn't do anything. But you'll have an example here is like, A or not B or C, and then also that has to be satisfied, but also not A or B has to be satisfied. I didn't spend a lot of time thinking about this. I think this is satisfied by just like making C true, but maybe not. I'm not sure. I didn't think very hard about it, like I said. If you have a not and an or with something else, that's the same as implies. So in our encoding, we'll use that equivalence quite a lot. So this is equivalent to B implies A or C, and A implies B. Okay, so here's how we encode a package problem. We have the variables that we use are we have one variable per package, which indicates is this package installed. One variable for each version of each package, and the letters we use are P and Q and V and W. And here's some notation for properties. The packages that belong to a version, capital P of V. The versions of a package, capital V of P. So that's, those are kind of complementary. The dependencies of a version are D of V. So the dependencies belong to a version, not a package, because different versions can have different dependencies. The set of conflicts is just a set of pairs of versions. And then the conflicts of a version, sometimes it's convenient to talk about them as pairs, a set of pairs. Sometimes it's convenient to be like, the conflicts of V are these, and it's a set of other versions. Okay, so these are all of the clauses that we put in the SAT problem. The first one is set of clauses is a version implies its package. So if you selected some version of a package, that means the package is selected. And that's written as V implies P of V. A package implies some version of it. So if you've chosen a package to be installed, that means you had to choose one of the versions has to be chosen. So for all packages, the package implies, and this big V is an or, it's a n-ary or. So one of these versions has to be true. Could be, this encoding means multiple could be true, but right in the next one we say only one version of a package can be chosen. So for all packages, for all pairs of versions of that package, either not V or not W. So you can't have V and W both be true. So that says that you can only pick one version of a package at a time. There's situations where you actually want to relax that when you're using this as a tool for other stuff. So a version implies its dependencies. So these are the interesting ones. The first three are kind of Okay, yeah, like normal setup stuff. This is a version implies its dependencies. So for all versions and all dependencies in, Q in the set of dependencies of that version, the version implies the dependency. So if you pick that version, you have to install some version of its dependency. And conflicts are exclusive. So if V and W are a conflicting pair, they can't both be chosen. That's it. That's the whole encoding. What does this look like in code? So we loop over all the package names and we look up V underscore P, which is it's actually represented as an integer. The variables are just integer indices. And you look up the number of versions and then you generate clauses. And so the first set of clauses is that the version implies its package. So you call, you iterate over all of the number of versions of the package, and then you do picosat add. And this notation here, negative integers are a negation of that variable, and positives are the positive of that variable. It's like a cute little encoding. It's all just, you pass integers to a C library. It's nice. So this clause is not P at version I or P. So that means P at version I implies P. That's what that says. And then you have to end the clause by passing it a 0. So the 0 variable says like this clause is over. So this is a clause that is always exactly two things. Here you have a clause with variable length. So the clause is not P. And then, oh, you know what? This is not negated. The negation here is wrong. So it's not P implies, and then you have a variable for every version of the package. So this will be, you'll have the P itself in there, and then you'll have like one variable for every version of the package, and then you end the entire clause. We do the same thing for exclusive. We do the same thing for dependencies. We do the same thing for conflicts are exclusive, and then that's it. That's the whole encoding. And so this part is like remarkably clean and simple. So again, pre-processing, SAT problems are sensitive to problem size. This is where the nastiness comes in. This code is just like horrific to read. It's very, very confusing and hard. So we use two strategies to minimize the size of the SAT problems. So one, we only include reachable packages and versions, and I will define what reachable means. And then we eliminate redundant versions that can't possibly be picked, and I will also explain what makes something redundant. So reachability, the concept is you start with the best versions of all your required packages. Those are reachable. You could consider installing them because it's the best version of a package that you need. You only consider the next version if a better version, if all the better versions have some potential conflict, right? Like, we don't know if that conflict is going to happen, but if there's no conflict, there's no reason to ever consider a worse version. So, for example, if a package just has no conflicts, why would you ever pick anything but the best version? There's no reason. So you don't have to even consider those versions. You also consider dependencies of any reachable version, right? Because so this thing, you consider this version is reachable. It depends on this other package. Okay, well now the best version of that is also reachable. All right. So in terms of this is an actual recursive definition of it, and the last one is quite subtle. So if P is in your requirements, then P1 is reachable. If PI is reachable and depends on Q, then Q1 is reachable. If PI is reachable and it has a reachable conflict, so that's like there is a reachable version that it has a conflict with, then PI plus 1 is reachable. And now this last one is a mouthful. If PI is reachable and it depends on Q, and Qn, which is the last version of n, is reachable and has a reachable conflict, then PI plus 1 is reachable. So what this is saying is that it's a very subtle, and this one took me a while to figure out. Like, it wasn't working, and I was like, why is this not working? Okay, you have PI, it doesn't have a conflict, but it depends on something. Q. And it's possible that we've been forced down to the like very last version of Q, and that could also have a conflict. So now we could be in a situation where Q just isn't installable, but PI depends on it. Okay, well now we can't use PI because we can't satisfy its dependency. And so therefore we have to say like, okay, well, we might have to consider PI plus 1, which might have the same problem, but then we'll apply this logic and keep going down until we get to a version of P that doesn't have this problem. Okay, so this does pretty well. This like really cuts down on the number of versions of packages that you end up having to consider. And now there's this redundancy idea, and this cuts down even further on the versions that you have to consider. So suppose V and W are versions of the same package. Now, and you prefer V. It's a newer or better or whatever. It's whatever preference order you've chosen, V is better. And if the dependencies of V are a subset of the dependencies of W, and the conflicts of V are also a subset of the conflicts of W, there's never any reason that you would choose W over V, right? Because if you chose something that conflicted with W, either it also conflicts with V or it doesn't. Like this basically says like V is just strictly better than W in every way. So we can just forget about W. We'd never pick it. So this actually eliminates a lot of versions too. So now you go through and you filter these out and you just delete them from your data set. Okay, so you do those two things and you get a pared down SAT problem that is really like truly just the packages and versions you might actually have a good reason to consider installing. All right, so this is the overall process of constructing a SAT instance. Parse registry data for explicitly required packages, parse registry data for recursive dependencies of all the versions of those. You just kind of recurse until you've grabbed everything. I used to interleave this with reachability, but it was too gnarly, and then it turned out that like these first two steps are pretty quick and it's not that much data, it's fine. Like just load it all, and then once you've loaded the whole thing, do the reachability analysis and delete stuff. Then do the redundancy analysis and delete more stuff. And then you construct your SAT problem. Okay, so SAT solvers can find some solution or tell us that there is no solution, but how do we find an optimal solution? There are, a lot of systems seem to have gone for like stronger things like, modulo theories, solvers, and optimizers, and I was worried that I was gonna have to do that, and then I was like looking at Z3, and Z3 is big, first of all. It's going to be a big dependency to add to the package manager, and it's very complicated, and I was like, oh, this seems powerful, but like more than we need. So then I was happy that I figured out a way to optimize with just a SAT solver. So PicoSat has this cool feature where you can push and pop sets of clauses. So you build your basic problem, which the only thing it tests is this a viable solution? Like, not is it good, is it the best? It's just like, is there a solution that's viable? But then you can add more clauses onto that and then pop them off later if you don't want them anymore. So given a solution, you add a clause to improve some package version. You're like, okay, can I improve this package or not? And then at some point you get it, and the answer is no. That's no longer satisfiable. And then what you know is that the last version that you actually had a solution for of that package is optimal. That's the best you could do. And then you move on to the next package and you do the same thing. And when you've done that for all the packages, you have an optimal solution. Pretty straightforward. And yeah, then you're done. And you repeat this for each package. And once you find the best version, you lock it in, right? And then if you want to find multiple solutions, because there can be multiple Pareto optimal solutions. So when you find an optimal solution, then you look at that optimal solution and you add a clause forcing future solutions to not be strictly worse than it, basically. They have to be better in some way. There has to be like, why would I consider this if it's like this other solution I already found, but like worse. So basically there's some package where like there's a newer version than this other solution I already found. And then you stop when that's no longer satisfiable, and you found all of the solutions, or you've found enough solutions and you don't want to find more. Because there can be situations where there's like a lot of solutions. All right, so changing version preferences is now completely straightforward. The resolver doesn't care what order versions are in. You just give it an order, and when you're loading versions, and it does what it wants. So downgrade resolution, just reverse the normal order. Download avoidance, just look, sort the versions that you already have installed at the beginning, and that does it. Version fixing, look in the current manifest, put the version that's in the manifest at the beginning. And this can be done on a per package basis, so you can do things like, fix all the JLLs but try to upgrade everything else, or fix my direct dependencies but try to upgrade my indirect dependencies. You can change the priority ordering of packages, so the choice of like which package do I try to optimize first, you can configure that. You can be like, okay, well please try to optimize JSON before anything else. So the user can just pick this order. One thing that's kind of weird is that there's no sane way to prioritize indirect dependencies over direct ones. And that, it just has to do with the fact that if something is an indirect dependency, there's an ambiguity about whether is the newest version of that better or is no version of that better. And if you try to lock it in, it doesn't work. I've convinced myself that there's not a good way to do it. But then I kind of forget the details and come back to it, and I'm like, wait, surely there's a way to do this. And then I think more about it, and I'm like, no, there isn't. So, but I think this is okay. Like, do we care that much about prioritizing our indirect dependencies? I don't know why that would be that useful. So this is an open thing, improved error feedback. We have all this powerful machinery. How do we give better errors when something isn't resolvable? Right now the errors are a lot of work has gone into this, but it's still very confusing when you get a not resolvable error. One possible approach that I'm thinking about is don't try to explain why it's impossible. I don't really care. What I care about is how do I fix it? So, and that's much more concrete and actionable. Like, what requirements could I remove that would make this work? Oh, I didn't actually need that, so okay, I'll delete it and now I don't have the problem anymore. Or, if you're a little more ambitious, what conflict could I eliminate? Can I go badger some developers to eliminate a compat bound with something, or release a new version of some things that are compatible? All right, that's it. I was gonna do a demo, but it's currently broken. I don't know how that happened. I'm not sure what the issue is, but it's broken. I'm wondering if I can show. Oh, yeah. There was a pull request. Where would I find that? Yeah, please ask some questions. Would I find that on Slack? Does anyone know? I mean, I can't just look for pull requests by Chris Rackauckus. That's like 12 million things. Julia Actions? No, I don't think so. You know what? I'm not going to try to find it. Let's just ask questions. All right.
Yeah, great work. The point you made about the resolver errors telling you what to do, one of the best uses of AI is taking a resolver error and putting it into ChatGPT and asking what I should do about it. Because it really does just say, 3 options are 1, remove this dependency if you don't need it, 2, do X, or whatever. And short of taking the text output of the resolver and just, maybe PKG could hook in if you have an OpenAI API key, just chuck it out, get it back. Is this going to be able to make us write better English language advice?
I think we can, because one of the things it can do is it can give you a set of partial solutions. So and actually this is how the API currently works. It gives you, if it's solvable, it gives you full complete solutions. And if it's not solvable, it gives you partial solutions where the version is nothing for some of the things. And so I think, you know, if there's two partial solutions and they each have like one requirement missing, that's very easy to interpret. You're like, well, delete that dependency or delete that dependency, and you have a solution. And if you want to figure out what conflicts they could eliminate, you can basically like look at those two solutions and be like, okay, well, what would it take to merge these two? What things in here and here are conflicting? There's got to be some conflict, or you could merge them. And so that it could also be. So I think we can do it. I just haven't done it yet.
I have two questions. One is, how is resolver.jl integrated with pkg.jl? Does that
currently not at all?
Okay. Is it going to be like pluggable? Could we have other resolvers if we wanted?
I don't know that we like really want other resolvers, because I think this one just is the resolver. This just does it. And it's pretty hackable. If we want new features, I think we can put them in here. It's very straightforward. One nice thing, and I guess this I will show, is that the types are like completely parametric. This is kind of cool. So like the package info struct is parameterized on the package type and the version type. And it's just, versions is a vector of versions, and depends is a vector of packages, and interactions is a dict from packages to integers. The other part, you don't have to like pay it to like understand that, but it's just like nowhere do we mention it. So one of the nice things about that is that there's no logic in here that understands anything about registries or how the registry is laid out or anything like that. You basically, there's a kind of funky but like not that hard to use a callback API that lets you like show it how to do let me see if I can find the callback API. Oh yeah, here's the file. All right, so yeah, so this function, this file here uses the resolver API and the package APIs and kind of glues them together and does everything that's needed to get the resolver to know how to load packages. But it's not terribly long. Like it's a little bit gnarly, but this is it. Like this amount of logic is like strewn over thousands of lines of code in pkg.jl, whereas here it's just like it's all here and nowhere else does it know anything about registries. So that's kind of nice.
My quick last question is, can I use this to fix the resolver issues with Python?
I mean, yes, it doesn't care about it being Julia stuff. You could like teach it how to read Python registry information. Do they even have registries? I don't know. But if you can come up with like the right data structure for Python, then it will give you answers. So, yeah.
I have a question about reachability analysis on, I think it was slide 24, with the dependency. It had to be all of the dependent versions had conflicts. Why does that not need to be Q1 when it says QN is reachable with reachability conflict?
Oh, so basically, if PI is reachable, that means that everything higher than it had to have some sort of conflict, right? Like you wouldn't have gotten to QI. So you don't actually have to, you only care that PI is in the set, but if PI is in the set, then everything above like PI -1 is in there, PI -2, PI -3. I don't know if that was your question. Am I misunderstanding? Okay.
And we're unfortunately over time, and I would hate to cut you off because
no,
that's
really totally fine.
This is such great, useful stuff. Thanks so much, Steph.
Thank you, everyone.
And then we have Diego and Luis Eduardo with Julia's, are they running it? Are they running it? Yes, I'd like to introduce Luis Eduardo and Diogo with GC Reimagined.
Okay, so good afternoon, folks. My name is Diogo. I work as a software engineer at Relational AI, and I'm also one of the maintainers of Julia's garbage collector. Today, I'll be co-presenting with Eduardo Souza from the Australian National University, and we're going to be talking about our work on creating a GC interface in Julia and using it to integrate a third-party GC framework called MMTK into the Julia runtime. This work is a collaboration of several people listed here from ANU, Relational AI, and Julia Hub. We also published a paper at this year's International Symposium on Memory Management, ISMM, on the work we're going to be presenting today. You can scan this QR code if you are interested in taking a look at the paper. To motivate the need for a GC interface and support for multiple GCs, I think it helps to start with a high-level description of Julia's existing memory management. This background will help us understand performance issues like fragmentation, which we aim to address by supporting multiple GCs, in particular, moving GCs. Julia's memory manager allocates small objects in object pools, and it uses a mark and sweep collector to reclaim unused memory. Object pools are sets of large memory blocks, 16 kilobytes in Julia, that are used to allocate objects of the same size. However, a memory manager in a language runtime needs to not only allocate memory, but also reclaim memory that is no longer in use. Julia does this with a mark and sweep collector, which approximates the concept of liveness, that's it, whether an object might be used by the program, through pointer reachability. A mark and sweep collector starts from a set of roots like registers, local variables, on-task stacks, and global variables, and it computes the set of objects reachable from these roots. All reachable objects are preserved in memory. In a subsequent phase called sweeping, the GC scans allocated memory, including pool-allocated memory blocks, and reclaims objects that were not reached during the mark phase. As you can see in the slide, it is possible to end up with large memory blocks that are underutilized because they contain few objects in them. These blocks can't be returned to the operating system because they are still in use by the program. This is called fragmentation, and it is a major source of wasted memory in the pool allocator. For some of Relational AI's customer workloads, fragmentation can exceed 8 gigabytes on a 64 gigabyte machine, which is very problematic because wasting so much memory increases the chances of getting killed. We originally ran this customer workload that has 8 gigabytes of fragmentation in a 32 gigabyte machine, but the memory pressure was so high that we ended up switching to a 64 gigabyte machine to be on the safer side. And of course, running on a larger machine in the cloud translates into higher costs. Fragmentation was not the only factor contributing to the excessive memory pressure in this workload, but it was a major one. A moving GC can help reduce fragmentation in some cases, but it wouldn't deliver optimal performance for all workloads. This is true for any GC implementation, actually. Different applications like servers or compute-heavy HPC workloads often have conflicting performance requirements. At Relational AI, we experience GC issues like long pauses and fragmentation, which could be mitigated with the concurrent and moving GC. But this kind of GC would not be ideal for compute-heavy workloads that rarely trigger GC. In the end, if you want optimal performance in multiple workloads, like Relational AI's servers and compute-heavy HPC workloads, and across multiple metrics, like GC latency and GC throughput, then you need multiple GC implementations. But maintaining multiple GCs is complex, and that's one of the main reasons we created a GC interface in Julia. We found it to be a good way to provide the infrastructure needed to support multiple GCs while keeping the code complexity manageable. The interface also makes it easier to plug other third-party GCs because it reduces the coupling between GC and compiler and GC and other parts of the runtime. Although the GC interface has been used to integrate MMTK into the Julia runtime, it is not specific to MMTK. It can be used to plug other third-party GCs into Julia as well.
All right, thanks, Diogo. So let's first talk about MMTK, which is the first external GC that we try to plug into Julia. So MMTK is an open source GC framework with multiple GC algorithms, also known as GC plans. It comes with a well-tested interface that since it has been ported to many different runtimes. That makes it the best fit for us to try to add to Julia when trying to support multiple GCs. MMTK has a clean design approach with a modular structure consisting of 4 components. On the left-hand side, you have the VM. On the right-hand side, you have the VM, in this case, Julia. On the left-hand side, you have MMTK core, which is language agnostic. And you have 2 different pieces of code called the binding that connects MMTK core to the language runtime. So the first piece of code is written in the same language as the VM, in this case C for Julia, and for performance reasons, it contains MMTK-specific code that needs to live close to the language runtime. This includes, for example, write barrier fast paths or code to discover routes. The second part is written in Rust, and which is the same language as MMTK core, and again, for performance reasons, need to live closer to MMTK core. This includes, for example, code to do object scanning. So again, with this approach, the core remains language agnostic, and whenever you want to support a different language, you simply repeat the same recipe for the new language that you want to support. That's the case for example, JAX RVM, OpenJDK, Ruby, Python, and Haskell. And the biggest advantage is improvements to MMTK core benefit all of the languages that support MMTK. So today we have JAX RVM and OpenJDK being the most mature ports, but Ruby and Julia are not far behind, with MMTK being upstreamed into their development branches. Another advantage of MMTK is that it bridges the gap between industry and academia. So industry can try research ideas in real-world workloads, and for academia, they get to work in an industrially relevant and high-performance setting, making research more visible, impactful, and faster to deploy. So take, for example, these 2 PLDI papers that were built using MMTK, and they contain cutting-edge research that are now on the way to make into MMTK core, and should be available for any of the supported languages to try. So now that we talked about MMTK, let's talk about how we used MMTK to support multiple GCs in Julia. The first thing we did was trying to add the simplest GC possible. This is called no GC, and it actually never collects anything, and it only allocates memory. It's similar to OpenJDK's epsilon collector. Even though this is very simple, it's very useful for us because it can isolate, we are able to isolate allocation from all the other GC concerns and try to implement the allocation interface that Diogo mentioned earlier. Next, we try to add support for emix. Emix is a marked region collector with optional opportunistic copying. For this part of the work, we disabled copying altogether and implemented a non-moving version of emix. With this, we implemented all the necessary functions from the GC interface, but also we used some of the Julia's current GC infrastructure, such as save points, weak references, and finalizers. Next, we added support for sticky emix. So sticky emix is a generational version of emix that uses sticky mark bits. And for this part, again, we used a non-moving version of sticky emix. And at the thing about the sticky emix that it's very close to Julia's current GC. At the end, we had a working GC interface that supports multiple MMTK collectors alongside Julia's current GC, which is important to mention. So we built the prototypes for these MMTK collectors in Julia mostly in 2023. And you can see that without a proper GC interface, it took quite some time for us to understand all the assumptions that lived in the Julia runtime with respect to the GC, and that lived in the GC with respect to the Julia runtime. In 2024 and 2025, we started upstreaming the GC interface and upstream the GC interface and non-moving emix. And non-moving sticky emix is still in the process of being upstreamed. But for now, if you follow the QR code, you should actually be able to download and try building and using Julia with MMTK. Now let's talk about supporting moving GCs in Julia. Again, as Diogo mentioned, moving GCs are especially important to reduce fragmentation, especially for long-running programs. So it does not matter how much we try to improve Julia's current GC, we might end up with a non-optimal result, especially with respect to fragmentation, since it's a non-moving GC. Take, for example, this application that fills up all the blocks of all the size classes for the green, orange, and yellow sizes. Then imagine that GC happens, but only the first object in every block is kept alive. At the end of GC, you end up with a heap with very few objects alive, but lots of unused space. A single object is keeping a block alive. If the program never allocates objects of the same size again, the space will remain there, with, again, live objects occupying just a small fraction of it. What we see is an increase in memory usage by the program, and when in fact it's using just a small % of that memory. Note that this is the worst case scenario for Julia's current GC, and we try to emphasize that this is a problem when you have a single GC implementation. So the idea with a moving GC is that you are able to relocate objects, compacting the heap, and try to reduce that fragmentation. So take, for example, take the same example as before. If you're able to relocate the objects that remain alive in each block, you are able to potentially free up all the blocks that had a single object, reducing the amount of used memory. The other advantage is that you're able to explore different allocators. In this case, for example, a bump pointer allocator in which you don't necessarily need to segregate the heap anymore into size classes. So combined with a moving GC, you get a better allocation performance, but also better space usage. There are different types of moving GCs. So for example, semi-space, in which you divide the heap into different spaces and copy every object from one space to another at every GC. But those might not be suitable for languages like Julia, where you have an interop with C, and some objects might not be able to move at all. So that's the reason why we try to use emix, so full-fledged emix, moving emix, because emix allows for opportunistic copying, meaning that it only copies objects judiciously, keeping objects in place whenever needed. So now that we know how, in a very high-level way, how moving GCs work and their advantages, let's talk about support moving GCs in Julia. How can you do that? So we saw from the timeline that non-moving GCs, the work that we did on non-moving GCs, was mostly completed in 2023. So we actually spent quite a lot of time trying to understand the assumptions in Julia that prevented a GC from moving objects. It's really challenging. Why is that? Well, there's this assumption that if an object is kept alive, then all the references should be valid. This is true by definition from non-moving GCs, and even allow for some optimizations, but that's not true for a moving GC. So let's see, for example, how skipping identifying roots can be problematic. Take this example of code, of piece of code from the Julia runtime that it's actually a pattern that happens quite frequently. Here you have two different roots, new CI and code, that point to the two different objects in the heap, expression and code. Here we see a glgc push macro, which the meaning is essentially telling the GC that new CI is a root. So it registers new CI as a root. This is sufficient when thinking about liveness, because new CI points to expression. So keeping points to code, points to expression, which points to code. So saving new CI as root makes sure that expression is kept alive, but because the liveness analysis is transitive, keeping expression alive is sufficient. So expression occurs as the dominant node on the object graph, and keeping only the dominant nodes is sufficient for a non-moving GC, of course. For that reason, there's an optimization in which you can actually omit the second glgc push, and your program should run just fine. However, for a moving GC, skipping dominated roots is problematic. Here, again, the GC knows that new CI is a reference from native code into the heap, and you can tell emix, for example, keep that object in place. There's a reference from native code. Don't move that object. But the GC doesn't know anything about the code object. So when doing the transitive closure, it sees the code object and it moves that object. The code root that we had in the runtime now becomes dangling. And again, that violates the assumption that if an object is valid, then all its references should remain valid. So how can we solve this problem? We can think about it by trying to make the GC move as many objects as possible. So in this case, again, emix is crucial because it can move some objects, but also you are able to leave some objects in place. One way to maintain the assumption that we had before, that all references should be valid after a GC, it's what we call transitive pinning. So the idea of transitive pinning is that anything reachable from a particular object is kept in place. So you're not only keeping the object in place, but anything in its object graph. So it traverses all the objects in the object graph, keeping everything in place. That's what happens here, in which you keep the code object as well. So this is correct, because it satisfies the assumption. But if we do this only for the roots that appear in the runtime, you end up pinning most of the objects in the heap. So this is not an ideal solution. However, this is still a useful mechanism for implementing Julia's FFI, which we'll talk a bit about later. So there are other different places in the Julia runtime that do not report the dominated routes, and identifying which one allows us to move from transitive pinning into pinning, which pinning is just a single object, which means that we can move more and more objects. So for example, for routes on the stack, for routes from the runtime code, you can do conservative stack scanning to pin any references from the stack. Note that this is not the only solution, but for us, this is a solution that enables us to achieve correctness, and as we'll see later, it also doesn't seem prohibitive in terms of performance. Now let's look at Julia's FFI. So one of the main characteristics of Julia is its interop with C, which allows native code to reference heap objects. The problem is that the current FFI focuses only on object liveness, which means that if an object is alive, you can take a pointer from it and use it to store freely in native code. You might have seen these things, such as gc@preserve, or even stored some object in a global variable to make sure that that object is kept alive when executing native code. This works just fine for non-moving collectors, but when we consider moving collectors, this is not sufficient. So Diogo wrote recently a proposal for a new FFI which accounts for object movement, making routing explicit. So you need to tell the GC root this object and unroot this object. So this is still a proposal, and if you want to know more about it, just follow the link on the QR code. So back to our roadmap, we have prototypes for moving mix with and without transitive pinning, and we have the proposal and proposal for the FFI with support for moving GCs, still as a work in progress. Now let's talk about some preliminary results that we obtained when using a moving GC in Julia. So here we used a small subset of benchmarks focused on fragmentation from Julia's own GC benchmarks. So we tried to gather some fragmentation and some performance numbers based on these. The first benchmark is the one that I showed before in the example, where we allocate objects filling up the heap, but only keeping one object alive per block after each GC. The second is a slight variation where we keep every other object alive. And the third is actually a real-world workload, a real-world benchmark involving the Julia compiler itself, consisting of part of the compiler that does type inference. So as we seen earlier, for the first benchmark, it leads to a lot of fragmentation, which here is the difference between the size of the heap and the size of live objects. For non-moving mix, we get similar results. We are actually able to reuse some of the space left after a GC in what's called holes to allocate new objects, but after some point, these holes become too small to allocate objects of larger size. So you get some fragmentation that increases, but at a lower rate than Julia stock GC. Here, moving mix fragmentation is significantly lower. It's even hard to see from the same graph, so let's look at it with a little bit more detail. It's important to note here that we used a version of emix called max moving emix that tries to copy as many objects as possible, just like semi-space does, for example, but it keeps objects in place when necessary. This is useful for correctness, but also gives us an upper bound in terms of the number of how much we can reduce fragmentation. Again, this is not surprising that there's such a difference with these fragmentation numbers, because we are looking at the worst case scenario for Julia's current GC. Note that max moving mix may not be able to move all the objects in the heap, so it still gets some fragmentation, but again, grows at a much slower rate. So for the second version of the benchmark, fragmentation is much lower for the stock GC, since half the objects in a block remain used. For non-moving mix, fragmentation is worse, though. Here, what happens is that the holes left after each collection cannot be reused to allocate objects of larger size. Here is an example that there's no silver bullet GC. Non-moving mix behave better for the first benchmark, but with a slight variation, it starts to behave worse for the second version. Moving mix, however, unsurprisingly, we get way better fragmentation numbers. We get a reduction of about 6x in comparison to the stock GC. Finally, for the inference benchmark, which is, again, a real-world application that is part of the Julia compiler, both the stock GC and non-moving mix produce quite similar fragmentation numbers, around 600 megabytes. Moving mix, as we saw again, we saw again a reduction of about 6x in terms of fragmentation. Here, max moving mix does more GCs because it needs to use extra space to copy objects all the time. This is a promising result, and we believe very impactful because it shows that there are fragmentation issues, even in Julia's own compiler. And it does not matter how much you try to improve the current GC, fragmentation is a problem that is very intrinsic, and it can only, in general, be fundamentally addressed by a moving collector. So far we focused mostly on correctness, on how to support moving GCs in Julia and how much we could improve fragmentation, but we also saw that the results are not prohibitive in terms of performance. With max moving mix, we saw only a slowdown of about 3%, and we haven't even looked at performance yet on trying to improve performance. So that's very promising. So in the end, we would like to know how regular mix would work with opportunistic copying in the inference benchmark, but the problem is that it does not do a lot of GCs. So we'd like to keep trying and investigating performance and other real-world workloads. So evaluating performance remains as future work. So there's a lot that we want to do as future work. We want to improve our work on moving GCs, try it in more realistic workloads, such as relational AI workloads, for example, exercising workloads that exercise Julia's FFI, and trying to use making the most of emix opportunistic copying. We want to evaluate and improve performance, both for non-moving and moving emix, and continue upstreaming our work so it's available for you guys to try out in your own applications. The final thing is that we also, with MMTK, we want to try support for more advanced GCs, such as LXR. So in summary, we have defined a GC interface for Julia, which allows anyone to plug in a new GC implementation. We use this interface to integrate Julia and MMTK, adding support for various collectors. The work has been mostly upstreamed, and again, it's available for anyone to try. Just follow the QR code. We experimented with support for moving GCs in Julia. Even though it's still in progress, we think that the results are very promising and should open up using Julia beyond its current capabilities in workloads that the current GC is not able to handle. So go try it out. Try to build Julia with MMTK and use it in your own applications. Thank you.
Thank you very much. Do we, maybe time for one question, which is the most important person here?
So absolutely awesome work. Thank you. Thank you so much for this. I love it. So my question about fragmentation is, so clearly fragmentation causes you to use way more memory than necessary, but after you GC, the extra space is still usable for new allocations. So what's the intuition behind why the fragmentation continues to grow over time without bound?
Right, so I mean, for the stock GC, the problem, the example that we have, we never allocate any objects in that space, right? So you should be able to reuse, but you should be able to reuse that space to allocate new objects. Do you have any answers?
No, I was just going to say that for the stock GC at least, if you have a new spike in allocation, then you are able to fill up these holes and to reduce fragmentation again. I think for Emix, Eduardo might be in a better position to answer it.
Yeah, so for Emix, what happens is that you have the holes, And the holes might not be able to be reused to allocate objects of larger sizes. And that's why you get fragmentation.
If I can quickly, I agree. I think in principle, yeah, you should be able to fill up the holes left with your fragmentation. So you would expect to see something like, let's say your fragmentation spikes, your memory usage also spikes, or your memory usage spikes, then your memory usage goes down and your fragmentation spikes. Then eventually your memory usage starts to go up again and your fragmentation should go down commensurately, and at some point you end up mostly full again and with lowish fragmentation is what you would expect. Weirdly, it's not what we see, and I think the best explanation we've had before is that the allocation pattern has changed, and since we have a size-classed pool allocator today, it may be that as your application moves from one phase into a second phase, you make a bunch of allocations of a different size, and your pools that got fragmented don't get reused because those aren't the ones that you're filling up new slots in. That's our best guess, which is kind of lame.
Just to add to it, I think the more you allocate, the more of a chance of one single object or just a small subset of objects keeping a page, a block alive. Right? So if you allocate a bunch of memory and then collect, there's a chance that you end up with like very few objects keeping a whole block alive, and then and that leads to fragmentation. You can keep reusing memory, but if you allocate a lot and you require new blocks, well, you never return those blocks, depending on the workload, of course.
I mean, it just seems like for that to happen, you would have to, your allocation sizes would have to be constantly changing and going up so that you never try to allocate an object of the same size again, which is possible, but that seems very strange to me.
Right, but if you allocate objects of the same size and keep getting new blocks, and those objects remain alive after a GC, you can never return those blocks, right? So the more blocks you allocate, the higher of a chance of those blocks being kept alive.
Yeah, but you can reuse them. You can reuse the space inside them.
Sure, but if you keep allocating on them, right? If the space that you need to reuse is less than what you need to allocate, you need to acquire more blocks.
So I guess like the workload size is constantly increasing as well.
Yeah. Yeah.
Well, okay.
And that's the case for long-running programs, right? Where you keep allocating and, well, the program never ends. Or, well, until you die of
Well, it seems unusual to me, but anyway, thank you.
I think it's about time for the next, the closing of the JuliaCon at 4:10. Wait, did you have a question? No, okay. Thank you so much, Luis and Diogo.
Is starting, and then Alessandro and I are doing something, and I don't know exactly the plan.
It's been ready.
It's rhetorical?
Yeah. I mean, you guys can do it or anything. I'm going to talk with these people real fast. So.
Alrighty, folks, we're going to go ahead and get the last session of the week started here. If everybody could please make their way to their seats and we can finish this up and send you off to your evening festivities. All right, so for the first part of this closing ceremony, I'm going to invite our two fantastic local chairs up to talk about, the first section of our closing ceremony.
That's what I'm talking about. All right, so it's been an immense pleasure and an honor for us to host JuliaCon this year. So we want to first and foremost our heartfelt sort of thanks to everybody who came, and it's been an absolute sort of delight to hear the amazing talks that we had and see all this energy. I'm sure we all going back home with a lot of ideas and energized and obviously in great spirits for the state of Julia, right? So we want to thank everybody who came to the baseball game. It was definitely a JuliaCon miracle to see the Pirates win a game, so we absolutely think it was, because of all of us, so thank you very much for that. But we also were able to get this view of the skyline of Pittsburgh, which I think was worth the struggle to actually see the Pirates play. Also, thank you for everybody who attended the poster session yesterday. We had a blast. This is one of the pictures. We're still kind of cleaning them up, so we will share all of them into the Slack and on the social media, so you will be able to see if we actually managed to get a decent picture of yourself, because it's really hard to coordinate. But we did have the Julia logo on tables, which is something that, it's an achievement which I will always be proud of, personally. Also, let me just say a couple of words about the posters. Amazing work. I was blown away by most of the posters, actually by all the posters. So, fantastic work. And lastly, but certainly not least, we want to thank, obviously, the University of Pittsburgh for hosting these first 3 days of the conference, and Carnegie Mellon University for hosting the hackathon tomorrow. And obviously, none of this would have been possible without all the support from everybody on the local. So let me just say thank you to everybody. And then I will pass it on to Rachel for some more.
Yes, so definitely would be remiss in not thanking all of our sponsors, Julia Hub, Temple Capital, AWS, ASML, Jeffrey Sarnoff, Puma's AI, yes, ANSYS/Synopsys, Relational AI, Carnegie Mellon University Software Engineering Institute, as well as the libraries, SciAm, the Center for Quantum Networks, and the APS Division of Computational Physics. So can we just get a quick round of applause for all the sponsors? Thank you. And I'll also throw in there informally the several local restaurants that I know folks have been taking advantage of the discounts this week. I saw a bunch of people over at Hello Bistro for lunch today, so I'm glad we were able to sort of push some business their way in the student light season, so thank you all for that. And of course, this takes a whole village to put together, and so we have to acknowledge the whole organizing committee. So Ray and Ranjan, our wonderful co-chairs. Katie and Luca, who have the unenviable job and did a fantastic job of putting together the program. Alessandro and I led the local committee along with Leticia and Ethan, so very much appreciate it to all of those people and a few other people who kind of popped in and out of various local meetings, so thanks to everyone involved on the local side. Sure. And finally, of course, our finance committee, chaired by the fearless Mark, and also Helmut, Ray, and Avik, so thanks all of them as well. Okay, and oh yes, definitely also to Margaret, who was our University of Pittsburgh point person. So you have her to thank for all of the wonderful rooms, and I think what was really relatively seamless coordination with our wonderful AV team. Let's have a round of applause for the AV folks as well. But yeah, Margaret has been a huge champ behind the scenes. We're giving her, I think, a nice package of like Julia swag and probably some sweets and other things too, a little bit TBD, but she's been fantastic. This absolutely would not have happened without her help. Volunteers, all of our wonderful volunteer team, thank you to all of them. And I'll throw in so all the volunteers, absolutely fantastic. I'll throw in a special shout out to a couple of times when on very short notice we needed people to step up for volunteer stuff, and really without fail someone jumped in, whether it was carrying something or jumping in as a runner or a session chair at the last minute. You were all just fantastic and really on point and great. So thank you all the volunteers. And okay, so the hackathon will be over at Carnegie Mellon tomorrow. So if you put in the CMU, the Cohen University Center, it's Cohen, C-O-H-O-N. That's just up Forbes Avenue from here. So if you put that into your Google Maps or preferred navigation app of choice, it will get you there. The Rangos Auditorium is on the second floor. So it's basically a bunch of giant rooms. We have them all merged together. We'll have a ton of tables and extension cords and all of that good stuff, and university quality Wi-Fi, all the things that you would want for a hackathon venue. So that starts at roughly 9 a.m. And we have the room until I think 5 or 6 or something, so hang around more or less as long as you want. We're excited to see folks there hacking away and spending some more time deep diving into Julia. Maybe some of the stuff you learned this week can be put into practice a little bit. Okay, and I think that is my last slide, and I will turn it over to Ray.
Another huge round of applause for our local committee, especially Alessandra and Rachel. They've done an immense amount of work. So. Alrighty, so just a few other technical bits, and then we have some community prizes, and then we'll talk about some future events. So the first is the stream recordings are already available on the Julia Lang YouTube channel. You can check those out. If you're having trouble with ads, please know that we have no control over that. You can, I think, join the channel to remove them for 1 month if you'd like. That's probably the easiest way to get rid of them if you're trying to watch the streams without ads. We will, as we receive the edited footage from the AV team, who have also been wonderful once again, I'd like to mention that, we will post them as we receive them. So look forward to your videos, and then once you receive them, I hope you send them out to all your friends and family and colleagues. I'd be remiss if I didn't mention JuliaCon proceedings. We've had a couple questions about that already. If you have a talk, a poster, a lightning talk, I think a poster, you are welcome to submit a paper to JuliaCon proceedings. You can go to the website and there's a ton of instructions about that. It's run a lot like the Journal of Open Source Science, if you're familiar with JOSS. And I think there have been some talks today about the internals of JuliaCon proceedings and how to submit. So you can probably check those out on the YouTube as well. With that, I think we want to go ahead and announce the Julia Community Prizes for the year, and I'm going to introduce Tim and Curtis for that.
All right, so first of all, thanks to everybody who filled out the survey to nominate members of the community who've made really deep and important contributions. As all of you know, Julia would not be Julia without the many, many contributions from tens, hundreds, and thousands of people. And so first and foremost, thanks to everybody who has made this a better and happier and just more fun ecosystem over the years. Yes, absolutely. We always have way more nominations than, and deserving people than we can possibly award. It's important to keep in mind that the contributions that people make span so many different sort of formats, right? Some people write code, some people write documentation, some people organize events, some people answer questions on help forums. You know, I mean, these are just, and all of these are eligible for the community prize, and we're always trying to figure out how we make the decisions about who to honor. That said, this year I'm extremely pleased with the 2 individuals that we've been able to honor, and I will do the first one, Curtis will do the second one. So this individual is a long-time contributor to Julia. One of the earliest packages that she's really famous for, together with Andy Ferris, is creating staticarrays.jl, a package that a lot of you know. but in more recent years, she has been the main force driving two packages, Julia Syntax and Julia Lowering, that many of us hope will really revolutionize Julia's tooling. So please, unfortunately, she was not able to attend JuliaCon this year in person, but please, let's give a very hearty congratulations to Claire Foster.
For the last JuliaCon Julia Community Prize, we have Stefan Krestenar, who does this month in Julia World. It's on the Discourse Forum, and it's a good place to look if you want to kind of get caught up in Julia and see what's kind of been happening over the last month. So let's give him a round of applause.
Next up, I want to invite Chris Rakakis down to give the SciML Contributors Award prize. Excuse me.
All right, thank you. We were starting a new thing with this to basically say, you know, there's many people who in the SciML community who are contributing to the packages. I think, you know, within a given year, we're now seeing more than 100 unique individuals giving pull requests. And so we really wanted to highlight those individuals who really helped improve this community. And this is a specific individual. You might know him if you've ever been working in anything biology or in Catalyst, because he's been, you know, one that really makes sure that this community continues to thrive. In fact, I think he's probably opened the most MWEs across the SciML organization, probably more than 100 this year, trying to make sure that everything keeps on working. And that contributor is Torkel Lohman. And so, and that contributor is Torkel Lohman. So, I mean, everyone give Torkel a round of applause. He was not able to... Yeah. Yeah. He was not able to make it today, but you know, we will be shipping your prize over to you over in England. So thank you very much.
All right. It was brought to my attention, I thanked our AV team, but I want to be clear, it's Massive Media PGH, led by James Ferris, who have been fantastic. So if I could get another little round of applause for them, they've been wonderful. All right, I can't actually recall what the next slides are, so let's see. So future events. The first event that's upcoming, hopefully you all are aware of, but especially those watching from Europe, is the JuliaCon Local happening in Paris in early October. I believe talk acceptances have already gone out, but tickets are now available. I really encourage everybody to attend. We really want to make JuliaCon Locals just as dynamic and fun and powerful for the community as the annual global event. So yeah, be sure to check out the Paris Local. Coming up soon. The next one is we had a sparse mini symposium, and one of our keynote speakers sort of wanted everyone to be aware, if you're in this area, of network algorithms, graph algorithms, and sparse arrays, of the workshop on network algorithms, analysis, and learning for science. I get to cheat here a little bit. I'm in this community, so if you want to attend this event, just check out this website, and we'd be happy to see you there. And then finally, we want to announce the next JuliaCon Global 2026 location. So yeah, drum roll please, I guess. We will be holding JuliaCon Global 2026 in Germany next year. So we don't have a specific venue quite yet. That takes a little bit of time, but we're already beginning to get things organized. And please look forward to the more announcements on that. And I believe we typically start submissions in, November, December area. So please be sure to join us next year as well. With that, I hope you all have a great evening, and I will see you at the hackathon tomorrow.